parameter, like the coefficient of drag, which is very difficult to accurately get. And we also need to have the accurate weather condition. The weather condition is usually changing all the time, so that's also very difficult. Another approach is to change the drag profile of the rocket by using the variable airbrake. To do that, we need to have an accurate dynamic model, but once we have that, we can always set our target apogee to, our real apogee to overshoot the target, and then we can shave off some altitude to get a very accurate apogee in the end. Next slide, please. And here is the solution we have. It's a variable drag airbrake. The goal of the airbrake is to approach a 1% of the target apogee. How we do that is by using the sensor data we get from the IMU and the barometer. We will feed that sensor data into a dynamic model, which have a real-time prediction of the apogee. We then compare that predicted apogee with the actual target apogee. That gives us an error signal. This error signal will be then feed into the control loop as a feedback to actuate the airbrake to get an accurate target apogee. The airbrake changed the drag profile by changing the cross-sectional area. As you can see on the right of the screen, there is a radial flaps that can be extended symmetrically. This will change the cross-sectional area, which then will change the drag profile. And by doing that, we can get a very accurate target apogee. And next slide, please.
Yeah, so the general solution concept and the loop that's going to be running on our airbrake will be just a set of steps that's going to be run continuously. So the first thing the airbrake does during every loop cycle is collect sensor data. With that sensor data, which we're getting from barometers and IMUs, we can then reconstruct the state for the rocket. This just estimates like the position and the velocity of the rocket. This is then fed into our dynamics model to predict apogee. And then with that apogee prediction, we can refer that to a reference signal and create an air signal, and then set the airbrake's actuation using a PI controller based on that air signal.
So the concept of operation of the airbrake consists as follows. First is the pad arming. When we put them on the launch pad, we press the arming switch. That's when the system will power up, all the sensors will start running. This is the time when the system will do a self-testing sequence to make sure all the components are working as predicted. And after they finish this testing sequence, the system will extend the flaps all the way out and then retract the flap all the way in to signal that it's ready to go. And this is the time when the data is going to log the data. And then after that, when the IMU detects an acceleration of 5G over 4 consecutive control loops, then the launch will be detected. This is when we enter the powered ascent stage. After that, there's a timer that indicates the time of the motor burnout. And then after the timer runs out, and the IMU indicates that the rocket stopped accelerating, then we enter into the third stage, the coasting ascent stage. This stage is the only stage that the airbrake will be allowed to actuate, and it's when the control loop will be constantly running and predicting the apogee, actuating the airbrake to get the target apogee. And finally, when we reach the apogee, which is also indicated by the IMU when acceleration changes, then the airbrake will disarm, which means retract all the way back in, and then it will log all the data and just wait for the landing. Next slide, please.
So in order to predict our apogee, we have developed a 3 degree of freedom rigid body dynamics model. This dynamics model factors in a number of different forces on the rocket, including the weight and then the drag of the rocket. The main portion of our dynamics model is used to estimate into the future the position and velocity of the rocket. However, we do not factor in lift coefficients, lift forces on the rocket through our dynamics model. So we rely on RAS aero simulations that we do beforehand on the flight, and then subsequent curve fits in order to get the pitch angle of the rocket throughout the flight. The model is extremely nonlinear, which makes it hard to control. We'll discuss that later. And then we've extensively tested this model against open rocket simulations and proven that it's been able to get within around 1.2% of the simulations consistently, and proving that it's accurate. Next slide. For the drag portion of our dynamics model, which is probably the most complicated portion, we previously used an airforce.com method, which is sort of a set of hand calcs in order to calculate the drag of the rocket. And we've since moved to using CFD and test flight data in order to predict the drag of the rocket. One of the main assumptions of our drag model is that it assumes zero angle of attack, so only drag forces when zero angle of attack are assumed. And then deviations from the zero angle of attack assumption only occur near apogee when the rocket's at low velocities, and we don't have very much control authority over it anyways, so it's not really important, these errors in our dynamics in the drag model. Next slide, please. And then as I previously discussed, the pitch angle approximations are done using a set of RAS aero simulations that we do for the flight beforehand. Essentially what we do is we run the rocket in like a series of simulations under a number of different launch conditions, including different pitch angles and then different wind conditions. And then beforehand with the flight, the IMU detects the pitch angle, and then we enter the wind speed, and based on that, it selects a curve fit to use for pitch angle approximations during flight.
So here is more in detail of the mechanical design. The mechanical design consists of a radial cam driven by a shaft. This extends the flaps radially, as shown in the video above. This mechanism is driven by a high torque servo at 7.4 volt. The 7.4 volt is a separate power supply to maximize the store torque of the servo to make sure that the flap can be successfully deployed. On the right, you can see an assembly model of all the critical components of the air brake systems. Next slide, please. To make sure the air brake can function properly, we did mechanical analysis on the flaps. First, we considered the loading case under the worst condition, which will be when the rocket is traveling the fastest. And this happens at the end of the motor burnout. And based on the simulation, at the end of the motor burnout, the Mach number will be 0.881. And in addition, we also have a wind speed of 25 miles per hour. And these are the worst conditions that we expected. With that, the coefficient of drag for the vertical flow is set to be at 1.5, and the coefficient of drag of horizontal flow is set to be 0.01. These are characteristic of a flat plate in a vertical flow and a horizontal flow. Next slide, please. Based on the loading case we developed above, we did a FEA analysis on the flaps with the thickness of 0.19 inch and the width of 2.5 inch. Under these conditions, we conclude that the maximum tip deflection is about 0.1 inch, which is good enough. And the factor of safety is 11.8 at the worst case stress concentration on the flaps. Next slide, please. In addition, we analyzed the torque on the servo to make sure the flap can be extended successfully. To do that, we consider three different forces. The first force is the force that's on the flaps when extend based on the loading case from the wind. The second force is the friction between the flaps and the linear rail when it extends. And the third force is the force that's needed to overcome the inertia in the beginning of the extension. With all these taken into account, the maximum torque we calculated is 8.8 kilogram centimeter, and the stored torque of the servo we selected at 7.4 volt is 7.2 kilogram centimeter. This gives us a factor of safety of 1.95. Next slide, please. And here we show a assembled version of the air brake. On the left is the assembly model, the middle is the assembled air brake, and on the right is the air brake in the coupler. Next slide, please. And for the electrical system of the air brake, we have a Raspberry Pi 4 Model B with 8 gigabyte of RAM. We select this microcontroller because it is critical for us to be able to have enough processing power to run the control loop at 10 hertz. And we have two barometric pressure sensor to get the altitude, and we have a IMU sensor to detect the acceleration and estimate the pitch angle. In addition, we have 4 BMP390 pressure sensor that's mounted at the top and bottom of each flaps to measure the pressure gradient. This is going to help to get a better simulation data in the future. 3 lithium-ion cells is used to power the system. This gives us at least 8 hours of battery time. And in addition, we have 3 separate power supplies. A 3.3 volt LDO power supply is only for the IMU to minimize the noise to get a better data for the air brake control loop. In addition, we have a 5 volt for all the electronics and a 7.4 volt just for servo to maximize the stored torque of the servo. Next slide.
For the Airbrake controller, we're using a PI controller. So essentially what we're doing is we're predicting in real time what the apogee is going to be, refer that to our reference, our target altitude, and then we feed that as an air signal into our controller. One interesting thing about our controller is that it's an under-actuated system. Essentially what this means is that the Airbrake can only reduce altitude from the apogee, and it can't actually add anything. So it's really important that we don't undershoot the apogee, like take off too much altitude, otherwise we won't be able to regain that. The control authority of the Airbrake is proportional to the velocity cubed. What this essentially means is that the rocket has most of its control, the Airbrake has most of the control authority over the rocket during the first few seconds of its flight when it's at the highest velocities. So we've shown this with this graph here, or this table here. Essentially what we did is we ran a simulation in MATLAB. So we deployed the Airbrake during the first 10 seconds of flight, and we were able to shave off nearly 300 meters from the apogee. But then when we only did it during the last 10 seconds of the flight, we were only able to shave off around 28 meters from the apogee. Now basically what this means is that we have to get the dynamics model right during the first 10 seconds of flight, because we really don't have much control authority during the last 10 seconds. Next slide. Okay, so we did run a number of different flight tests on this Airbrake. So this was the results of the first flight test, which happened during our 2024 IREC testing schedule. So during this flight, we were able to collect a lot of good data from the Airbrake. However, one thing that did happen is that we had a typo in our code, and we set the Airbrake to 100, like a factor of 100 less than what it should have been. So essentially, as you can see, these blue dots are our dynamics model predicting what the apogee should be. This is our target apogee. Obviously, the apogee was higher than our target, and the Airbrake did want to extend, and that's what the controller was commanding with that orange line. However, this is what the Airbrake was actually extending to, just because of the typo in the code. However, this proved that our dynamics model was pretty robust and able to produce good values. Flight test 2 was our 2024 IREC competition. Unfortunately, during the flight test, we had higher than expected wind gusts, and as a result, we had a structural failure of the rocket during the flight. So the rocket was unable to achieve its predicted apogee. However, the dynamics model in the Airbrake predicted that the rocket would only get to 8,000 feet since it was in 2 pieces, and then as a result, it did not deploy the Airbrake. Next slide. Our third flight test, which happened during this year's testing season, was our first successful actuation of the Airbrake. One of the really important takeaways was that we proved that our Airbrake does have control authority over our flight. So during the flight test, we expected that our altitude, if we didn't deploy the Airbrake, would be around 4,800 feet. However, with the Airbrake deploying, we were able to shave that down to 4,600 feet, which was about 100 feet away from our target altitude. Now, one thing that did happen is that we had oscillations in the Airbrake extension. This was due to unexpected mechanical interference with our pressure sensor. Essentially what was happening is that every time our Airbrake was being extended, it would increase the pressure inside of like where our pressure sensor was reading, and then the altitude would be a lot higher than expected, velocity would increase, and it would mess with our dynamics model, causing the Airbrake to oscillate. So Looking to the future for IREC 2026, one thing that we want to change is we want to move our control strategy to model predictive control. Basically, this is when we simulate a few seconds into the future on our hardware what the rocket's going to be doing, and then we optimize what the airbrake actuation should be in order to get the rocket to a desired trajectory. Another thing we want to do is improve our actuation hardware. Right now we're using a custom off-the-shelf servo to deploy our airbrake, and we can improve this by buying a motor and possibly using an encoder to directly read airbrake position. Also, we want to use CFD to get lift coefficients so we're not completely dependent on RAS Aero for pitch angle estimations, and possibly use an adaptive controller to use live data during the flight in order to feed into our drag model to update it based on inaccuracies that we might have had during simulations. And then another cool thing, I'm sure you all have seen like the SpaceX flights with live data telemetry and video overlay. Getting live data transmission from our airbrake is something we think would be cool and our team wants. Next slide. So just a summary of everything we've done. We had our goal of getting our apogee within 1% of its target. This would be done in a variety of different launch conditions and a bunch of different uncertainties regarding different parameters of the rocket. So our solution for this was real-time apogee prediction and correction. So we have a 3-degree of freedom dynamics model predicting our apogee in real time, not using a lookup table. This is something really unique to this team. And then we have control over the apogee using a PI controller. A PI controller, which is deploying a set of radio flaps to change the drag profile of the rocket. Now, we have proven the control authority of this system over a number of different test flights, and we're really excited for tomorrow. We'll finally get to test it, and hopefully it gets within 1% of our target apogee. Thank you.
The mechanical parametric with the barometer, like you said it was
Yes.
blocking the barometer. Is there any way around getting around that, or?
Yes. So essentially what was happening is that every time the airbrake deployed, it would cause the pressure inside, like where we're measuring pressure to increase. So that would mess with like our altitude readings. So what we did to change that is that we had like a bulkhead separating the mechanism from the actual pressure sensor. And we just did a better job of machining the bulkhead to seal off the pressure, so it's no longer interfering.
Yes. Yeah.
Can I go? Or
Can we take
can I
that?
ask questions?
Yeah.
So it looks like you have 3 tail fins, correct?
4.
Oh, you're 4. Okay. So why did you decide to go with 2, I guess, plates or pedals to extend out versus 4? I mean, I guess other than a space issue, or was it just a space issue?
Yes, it's just a space issue. We can get a flap much bigger. And also another concern is the cutout we have is on the airframe. And if you have 4 cutout, it's going to impact the structure too much.
Right.
So 2 is a better choice.
Okay.
Can you guys talk through how you guys estimate your velocity, your state estimation? I guess your prediction of apogee is pretty based on position and velocity. How do you find the velocity?
So for that 3rd test flight, what we were doing is we run our pressure sensor. You can convert your pressure to altitude. We convert it to altitude, and then we run that through like a Butterworth filter just to like filter out any noise, and then we just take the derivative of that. That's what we were doing for the 3rd flight test. Right now what we're doing is we're just like doing a weighted average between the Butterworth filter, like the derivative of the altitude data, and then integrations from our IMU. We're not using a common filter or anything. That's something we're definitely looking forward to doing in the future though.
Do you have any adjustment for your barometrics while you're on the pad? Because the barometer changes daily.
So you're saying, do we adjust like what the barometer is like?
Yeah. So there's like a.
Is it already programmed in your program to adjust for the barometric pressure as you're standing on the rail?
Yes, so in the sensor, there's also a lot of calibration that's given by the manufacturer we do. which is always constant. And then in the code, there's like a parameter we enter into based on the weather of the launch day that's going to adjust for that.
In the event of an electrical failure, is there some sort of failsafe that would retract the air brakes into the rocket? Or are they, like, let's say they're deployed and then you lose power, and then will the servo lock, and then they're just stuck outside the rocket? Or is there some method of bringing them back into the rocket?
We don't.
I think currently we don't have that. If that's the case, then the server will just stay outside.
Gotcha, okay.
However, that wouldn't cause any like instabilities in the rocket, just because like if the air brake is extended, it means we're already in like coasting ascent. And if it's extended during descent, it's not really that much of a problem.
Yeah, I was just curious.
Yes.
What was the process you guys used to create your freed up dynamic model?
So we have like a free body diagram, like I mean, just deriving the equations of motion for just obviously force of the weight, and then obviously the force of the drag, and then from there, obviously we don't have the pitch angle stuff, but we just use RAS0 for that. It's just from like standard forces on the rocket.
Were there any like main assumptions that you guys made in that model?
Yes, angle of attack is 0 was the biggest assumption. Just because like if angle of attack isn't 0, then you have to factor in lift coefficients, which is extremely hard to do, and we're just using the RAS0 simulations for that.
Yeah.
How close did you match up to what the CFD was giving you with the actual flight data?
So we ran the flight data first. How do I explain this? I'd say around like 5% off, but we ran the flight data before. So the third flight test is when we finally got data regarding like the drag model. Before that, we were using the DATCOM method, which was also around 5% off, but it all came up pretty accurately.
How quick can you deploy from 0 to pop and fully out?
You looked that up.
I think if it's fully deployed, that should be like around 0.1 second, yes. And that's why we have the that's why we have the control loop set around 10 Hertz. So that's the reason behind it. Yes.
I noticed that the profile of the air brakes is not necessarily like flush with the body tube of the rocket. Is there a reason for that when it's fully retracted?
Not flush.
This is a good question.
Like, if you go back to your picture.
No, I know what you mean. It was something we kept constant from last year, but no, I know what you mean. It causes us to lose a bit of control authority.
Like it's not a tight fit through the slot.
He means like you know how the end of the air brake is like a semicircle, but it's not flush with the face. So you could have added a little bit more air brake in that space.
Yeah,
Oh,
that's the
okay.
last question.
It's like how it isn't flush with the red part on that cover.
I think that's just easier to manufacture and easier because it's like the first time we made it, and it's easier to put into the coupler. That's the only reason. Next year we can definitely make it flush. It probably will improve the performance too.
That was good.
Ready?
Mike's here.
All right. Good morning, everyone. I'm Pranav,
I'm Jeremy.
and we're members of Kent State's Golden Flash's Rocket team, and we're here to do a presentation on oblique shock waves and pressure gradients across a von Karman nose cone. All right, so a quick overview of this project. Our aerostructure team did an analysis on various different types of nose cones and picked a von Karman nose cone, 5-to-1 von Karman nose cone to be exact, mainly due to their availability and also their stability and efficiency in high transonic and low supersonic speeds. We're looking to understand oblique shockwave behaviors and pressure gradients, and we chose a low supersonic regime about 1.02 Mach, mainly because at our test launch, before we integrated the system, we got very close to Mach, about 4 feet per second off, and we thought this would be a good regime to test our research on. The objective is a theoretical and computational fluid dynamics-based pressure characterization across the nose cone, and this has importance in aerospace and defense applications. Okay, so our design rationale. On the right, we have an image with the first image being an unspiked body, which is a blunt object flying at supersonic speeds. And as a free stream flows past, it forms a bow shock, which is detached from the body itself. And this creates a lot of drag and has very high temperature transfer to the body, which is very inefficient for supersonic flight. On the right, we have another, where's the pointer at? Okay, it's broken. It doesn't matter. Okay, so on the right, we have a blunt body, but this time with a spike. And when this goes at supersonic speeds, we get what we call an oblique shock wave. And there's a recirculation region, which is basically an area of low pressure in front of the blunt body. And the shear layer is the boundary of this. And as the shock goes down, it reattaches at the reattachment point to form a semblance of a shock wave, but it's nowhere near as strong as a detached bow shock. So it has less drag and also lower heat transfer onto the blunt body itself. So now we still want to study the shock wave in general. High-speed regimes, they lead to pressure spikes due to pressure divergence. This affects aerodynamic stability. It affects sensor performance and our air intake efficiency. Oblique shock waves and flow separation are also key concerns for our aerodynamic stability, and we would like to validate the pressure models that are out there to make better design decisions for the future.
Onto the physical characteristics of our nose cone. As seen to the right here, we have 3 static ports drilled 8 inches apart from each other, starting from the top. Each of these holes has an inner diameter of 3/16 of an inch with an outer diameter of 1/4 of an inch. Into the simulation aspect. We used a program called OpenFOAM CFD, CFD meaning computational fluid dynamics. And the key benefit of using a program like this is that we're able to simulate a physical world in a virtual environment. And this allows for more precise and cost-effective means of simulation. And another great benefit of using software like this is that we can simulate our different densities, temperatures, and velocities rather more cost-efficient compared to a wind tunnel.
And now the modeling of the simulation itself. So we have a pressure equation on this slide. Okay, we have a pressure equation on the slide. I'm not going to go over all the variables. They're defined on the right. But a subscript of B for any of these variables basically defines that variable at sea level. So P with a subscript B is pressure at sea level, so on and so forth. So using this equation, we can calculate the theoretical pressure at different altitudes. And then we get data from our pressure transducer embedded system. We put these together on a MATLAB script to get a gradient of pressure from the tip of the nose cone all the way down to the base. Our predictions based on already published research is that the peak pressure would be at the tip and it would decrease as we go down the body.
Now to the actual simulation. Like I mentioned before, we use open foam and we use compressible low supersonic flow at 1.02 Mach. And we simulate a condition based here in Midland, Texas at 350 meters per second and a temperature around 320 Kelvin. And the models we have here is our solid von Karman nose cone without the static pressure holes, and we have with the holes. And the results, we found that we have a tip pressure of around 170 to 180 kilopascals and a base pressure around 110 kilopascals. And that's around a 9% deviation from our MATLAB predictions. Now, surface pressure disruptions. On the chart to the left, we have our model with the hose simulated with a coefficient of drag of 0.135. And onto the right, we have the model simulated without the hose, and we have a coefficient of drag of 0.115. And this is around a 15% deviation from one another. Now onto the meshing and the results of this meshing and simulation. So the simulation ran into converged to a value of 10 to the negative 4, and we had 2 meshes during this process. We had a hexahedral mesh on the nose cone itself, and we had used a tetrahedral mesh on the boundary box, free stream box. And the reasoning behind these choices is that the hexahedral mesh is better suited for round curvature, small curvatures, just like the holes we have. And tetrahedral is great for the boundary box, which is just a boxy pattern. And we found that the oblique shocks form at the nose tip, and there's smooth nose pressure drop along the nose cone contour. And there is no unexpected flow separation, and this concludes that the sensor ports do not significantly disrupt the airflow with the difference of coefficient drag of 0.02. Now on to flight validation. So the onward pressing transducers will log real-time data. And this enables post-flight analysis with the key benefits of confirming our model accuracy, it validates our CFD approach, and it optimizes our future designs. And to the chart we have to the right, we have the length of the nose cone of 0 inches to 33 inches, and 0 inches being the top of the nose cone, and the 33 being the base. And as mentioned before, we have a pressure prediction of between 170 and 180 kilopascals at an altitude at 3,000 feet. And we can see we have it on this plot 3 increments apart, but based on our hole placement, we can expect the pressure gradient between 130 to 160 on the 3,000 foot range.
All right, so we just explained the theoretical and simulation aspect of this project, but how are we planning on doing the flight validation? So we have an integrated system in the nose cone itself. This is Arduino based, mainly because it's cheap and readily available and easy to use. We have an array of 3 pressure transducers, which are connected to the holes in the nose cone via vacuum tubing. And we're using Arduino's programming language, which is C and C++ based, to account for variations on the transducer readings due to manufacturing, error handling, and also to store the data that we get for validation later. So, post-launch goals. Once we do our launch, we will be combining the data from OpenFOAM and MATLAB with the sensor data that we obtain to corroborate results. If there is a difference between the obtained data sets and our theoretical predictions, we would like to dig down to see why that happens exactly, get a reasoning to that, and this would help us better understand not just oblique shock waves, but also our sensor design and what to take into account for the future. All right, what is the impact of our research? We'd have, first things first, we'd have much better data for applications in high-speed aerospace nose cones, and this would also trickle down to applications in defense, space, and commercial rocketry. And for us specifically, the data analysis of these data sets would be very beneficial for future development of better nose cone designs for, in our case, SRAT rockets, and it would be the foundation for air intake sensor integration work that we are planning to do down the years. A quick summary. So we started this project trying to understand oblique shockwave dynamics and its properties, but in the process we also got a good understanding of placement and the holes in the nose cone and its effects on aerodynamic stability of the rocket as a whole. And while we explain computational fluid dynamics, it is a very complex process and very new. And this was something, especially because it's terminal based, which on a 12-hour cycle, very difficult to run with the computational power that we have access to. And we spent a lot of time trying to optimize and learn this to validate flight results and simulated values. Thank you.
Turn off the screen share. So it looks like we have a little bit of time for questions. I have a couple. One, I'd like to know a little bit more about your data measurements.
Yep.
Specifically, what was your data acquisition rate and how does that integrate with your time scale on the simulations?
So we're looking to hopefully measure data at about 100 hertz, which is what we have right now. So about 100 times a second. And since we have 3 sensors that's at different parts of the nose cone, that gives us enough data. So throughout the flight, as we go across the sonic boom, we should be able to see the spike and the dip in the graph.
And what if you could increase that, do you see any value in having a higher density in time?
It would be very good to have a higher density. It's just the power of the Arduino system that we have currently is not strong enough, if I should say that, to get like, let's say 1,000 hertz or at peak 1,500 hertz would be great. But we would be looking into doing a custom microprocessing unit just for stuff like this.
And to add to that, it's not just the Arduino itself that's limiting us to the 100 hertz speed. We have the pressure transducer itself has a limited data throughput, and the ones we have has a maximum of 100 hertz.
Are those digital or are those analog sensors?
They're analog, man.
Okay, so what you're talking about is the response frequency
Yep.
of the electronics within the sensor?
Mhm.
Okay, all right. So are there ways that you can improve that?
Well, I guess we could go into a digital one. That way there'd be a lot less conversion from analog to digital, but also just looking at better, more expensive analog ones for future,
Okay.
possibly.
The other question I had was in regards to your sampling ports. You spoke about the locations. I saw some modeling analysis to see about the impact of that on the measurement to a degree and also on stability. The one thing I didn't hear you address was the orientation of those ports. What led you to get the orientations of the port to the nose cone surface?
So initially we planned on doing a straight 90-degree angle, but due to like manufacturing issues, we could not do that. So we have it 3 statics ports, and we had the top port angled at 55 degrees, the middle one is angled at 50 degrees, and the bottom one angled at 45 degrees.
Okay.
That should just go along the contour of the nose cone.
And what impact will that have on your data?
We anticipate very little impact since the pressure transducers itself should account for that angle on its own.
In just stagnation of the air?
Yeah.
Okay. That's all the questions I have. Does anyone else have questions?
Go for it.
Do you plan on testing other nose cones, conical power series, kind of see not just like the gradient, but the like shockwave formation and pressure?
Yes, that would be something great for us to do. It would require a lot more funding and a lot more time, but if we could get access to different nose cones, it would be really good data for us to have, yeah.
Anyone else?
You said that there was a big difference between the round tip and the pointed one. That's kind of obvious, but is there a point where the rounded tip is like negligible? Like you can't have an infinitely sharp tip. Of course.
No,
What's
but
like
because you give it a gradient, especially like on the von Karman shape, it goes from sharp to blunt on a curve. It gives you a better, it forms, and again, the sharp tip forms the oblique shock, which by itself is a weaker shock than just a bow shock, because the bow shock is detached from the body and it's ahead of it, causing a lot of drag, heat, and stuff like that. The sharp point, you could assume, kind of like cuts through the air, so the shock's a little weaker, and it gives us more efficiency for supersonic flight. It cannot be infinitely sharp, but the effects of having a sharp tip are relevant to flight.
Anyone else? All right, thank you.
Thank you.
Yes. Yeah, I wonder if
There's no GUI or anything, it's very terminal based, but it gives you, that 3D model that we got was right out of that. So the terminal program gives you a 3D model, you just have to have something.
Yeah. And then, sorry, do you get, I think I saw pressure, but did you get any kind of thermal reading from the software as well? Is it just so you can, but we just sit in pressure based? Okay.
Yeah.
Right. Yeah, it's just like 12 hours to run per. Yeah.
And we also only reach conversions of data.
Yeah.
Want to reach level 7. We just
mic will turn on here, it's turned on, so I can see it being streamed. So,
Yeah, you need.
I don't know if you can see this, but like, the guys did this presentation, just did the presentation before. It's so viewers online, on the stream, you can see. You shy away from the mic, it would make more sense. Whoever with your team to stand in front of the mic, it's not for loudness or nothing, it's for the streamers to be able to hear you.
We launched Rocket in March.
It's not about being loud, I'm controlling the volume, it's me.
Open phones are pretty good for
This
that.
wall, I had no way
Open
to.
Rocket's okay, but
I'm so
I
far away.
try to modify an open phone, so you get an idea.
Y'all have a laptop or you?
Yeah, my,
Yeah, your team. That's fine.
Then you should have to do it. But that's something our structures already have. So take that data, plug it in, you say, oh, we're using solid order, we're using variables, run the script, gives you everything, gives you a graph, gives you even log, make sure you can look at the data. Again, no GUI, but like Open Rocket has a GUI, but there's none of that.
If I wanted to, I have software that recommends CC. Yeah, I never even.
No, Kelsey's coming in. I don't know what everyone else is.
We have a calculator.
I don't know.
Maybe I'll send a message right now.
No.
You don't verify whether or not.
Let them forget Kevin.
Well, yeah, there will always have a little bit of a difference.
Hey, he has your laptop.
You have to account for that, but close enough.
Sufficiently nervous.
Yeah, that's awesome.
No matter. But I would prefer,
And it's that pressure, so it's fine.
And if our data is really
Check it
different,
out if you guys really
we
want to.
can confirm that our sensors were working right, then I could even hit up the developers, Progetto, Jupiter, they're working on that, college is working on it. So just, they took up development of it, so just get them up with the new values and they can integrate that. That's the cool part of community-based.
I mean, that'd be cool, you can do, like, that's like mine. Did it work better than, there's nothing, there's just right, so like, you have no idea, the Avon car was not actually Failsafes. Well, yeah, it's actually very ideal. Car surgeon, not if shop. We just think we're trying to, we weren't able to get
Conical would probably be your best bet.
We were wanting to Yeah, that's awesome. No, we didn't actually get a whole lot to get a further questions.
We're talking about cars, and they won't move unless one person
Yeah,
moves.
it's just flipping a coin.
So no one's here but Kevin, because they're all cheap. I want to be on this side. Is that gonna mess you up?
So, like I said, if
Yeah.
you stand right here, they can't see you.
Okay.
So either I can move this way,
Cool.
but when you answer, this isn't for volume, it's for the
Okay.
people to see.
stream.
Okay.
So you need to get over here
Yeah.
and talk. Okay.
Can we both be on the same side?
Yes, you can.
Oh,
That's what-
okay,
That's what we're
perfect.
trying to say.
Oh, okay, cool. I thought we had to like split the screen.
No.
Then we are chilling. Yeah, for sure.
I think it offset off the screen a little bit.
Yeah, I think so too.
Microphone.
I said just.
Yeah. This works for us. It's not gonna throw you off?
No.
Okay, sounds good.
Speak up, it doesn't.
Yeah. Locked in. I like how it's like 10 minutes. I don't know why we're standing up here. We're ready. Yeah, we're uber ready. Gary! Gary's right at the door. Gary's ready.
I connect this.
I don't know, is it connected?
Yeah, let's see if the mouse reaches from here as a. Yeah, okay, cool.
Hi, friends.
It was supposed to be.
Yeah, I know. Color.
You'll kill it.
Thanks. Gary, are you gonna sit right in front? Oh boy. Gary, I think you're the only person that would make me nervous sitting in front. I don't even care if the Astro Judge is in front. Like, I can't disappoint Mentor Gary.
Do I have to go all the way?
No. Okay. What's with the? Do you guys like not like each other? I see. Okay. I was gonna say, do you guys like? That's true.
Is that the 15-minute class?
No, that was the last groups. I believe they're gonna reset it. Now we stand here awkwardly for another 3 minutes.
I was thinking we should go around.
Kevin, water. Mom, Kevin. I'm gonna hit that. What's going on? Oh God, so many of them parked at once. Oh no, who Slack messaged? No, you could have just forgotten. You guys suck. Hate you all. Nothing. Love you, Tony. Why are you guys all in front, bro? It's fine. As long as it doesn't bother Kuba. Kuba's more important than I am. Yes. Hi, Gary. Hi. They told us to stand over here, so. Yes, I'm going to be live streamed. I'm sorry. Should I have not said that?
No, it's fine.
Okay, cool. We still have 3 minutes. What's What's my name? Nothing. I fear I'm only gonna look at this side of the room. Like I'm. Hi, Carl.
Are you guys presenting this one?
Yeah.
No, they're just like.
Yeah, no.
Why don't you guys close the door?
I didn't.
No one ever opened it.
Carlita.
Did someone open it?
No, I don't think no one ever opened it. I don't want the laser pointer. I don't want it.
Thank you.
Just remember to keep it open on the way out.
Yeah. Fancy dancy. Bye, Carl. I'm fine. Both University of Minnesota.
Yeah. Don't start until you get here.
Oh, yeah, sure.
That would be. Our judge gets here. I mean, we could. Flawless. Neither of us stumbled once. And our information is beautiful. Hi, Gary.
Yeah, they're live. Yeah, we're live. 10,000.
Thanks, Carl.
I'm on TV. You're live, but are they available? Are they available for later?
Yes, they will.
But hey, no pressure.
Right.
I'm not having any service in here. I don't know if they're actually.
Truly. What's our judge, bro? We should just be unjudged. That's what I'm saying.
Yeah, he's on there.
Are you staying? Are you staying?
No.
Please don't.
We can get started with that round so we can, let's get this up by safety.
All right. Hello, everyone. We are here on behalf of Team 407 from the University of Minnesota Twin Cities. My name is Kuba Kedzer, and I'm the team software lead.
And my name is Mackenzie Steiner, and I'm the recovery sub-team lead. So it is very common in rocketry for people to have telemetry receiving flight computers. This year on our rocket, we have 4. We have the AIM Extra and the Telemega, which are both telemetry receivers, as well as in charge of our black powder. And then we have the Featherweight GPS just as an extra tracker for our nose cone, and we have an SRAD avionics flight computer that also does telemetry readings. These are all made by different manufacturers to mitigate any internal errors that might come from a manufacturer in a certain kind of flight computer. One issue that we have with all of these flight computers is the amount of base stations that we need. If we have them all run on one computer or one device, then we would have to switch between interfaces, which makes a lot of problems with either missing information when you're not looking at one, or possibly having like one team member read one and then they misinterpret it, and then we only have the one interface so we can't go back and check. Also, we could have 4, but that also introduces problems of having 4 different devices out at launch sites with, batteries possibly running out and people getting different information, which could also lead to issues.
This is where our team's software application project comes in. Monikered Wings, the project is a cross-platform application, and it is telemetry agnostic, meaning that it is the same application for every single COTS flight computer and telemetry stream. We can mix and match different flight sources specifically to create a ground station for that specific flight based off of user input. The project is also open source so that other teams can learn from the technology and build upon it to create their own ground stations and help benefit themselves. For the design of the project, we have specifically pursued hardware to be as lightweight as possible. The software runs on any laptop that has browser support, so it'll use Linux, it'll work on Linux, it'll work on Macintosh, and it could work on things such as Raspberry Pis as long as they can run a browser. That is done through the framework that we use, and it allows us to be cross-platform. Beyond that, you will need exactly the same hardware requirements that you would use for a COTS ground station. That would mean using a receiver, plugging it in, and then just setting up and getting it ready to go. From the software perspective, we have created an interface that is able to support all these different telemetry streams. It is adaptable and completely isolated from our display and our logging. That means that once we have implemented the interface, we can continue to add other telemetry sources as we go. So far, we have implemented 4 different flight computer families, which are Entacore, Altus Metrum, Featherweight, and our own SRED flight computers. We also allow for file playback through CSV or binary file formats, which lets us, like I said, play back old files or run sims. We can also mix and match these sources so that we can have a single ground station application and take multiple sources from a specific flight and feed them into one ground station. To support the display of the application, we have created a display interface which consists of different display objects. These objects are created using JavaScript elements, and we have plots, readouts, and Boolean display values. Because it's JavaScript elements, they're easy to implement, and we have constant expandability and different kinds of sources. We have created a version of this with 3D rocket models that allows us to display the orientation and the attitude of the rocket. We have also done, on the far right there, you can see Boolean readouts, which allow you to display a threshold within the UI. So if you have a specific threshold for a mission that you deem to be important, you can have the square there turn red or green depending on whether you've crossed that threshold. We also support a high contrast mode for all of these elements, since when you're at the launch site, you often can't really use dark mode. The sun on your computer screen will make it extremely hard to read the elements. So to help mitigate that, you can switch to light mode at the launch site, but use dark mode for development and other purposes. When pursuing user interaction, we have tried to increase customizability during the pre-launch stage and try to streamline user interaction during the launch operations. This means that our input devices are put in first. You will essentially say what devices you're expecting during your launch, and you will then move on to creating your display. Your display is divided by however you choose to segregate it into vertical and horizontal lines. These divisions are then filled with those elements that we showed before. This means that if you have a specific piece of telemetry or data that you deem more important than your other values, you can prioritize more screen space to showing it, and you can completely customize for your mission how your data will be displayed. Each element also has its own individual settings, so you can choose what display is on it. Or, oh, yeah, sure, sorry. Thanks. You can also customize each element, including the data and the theming of the element. Once you have customized your entire ground station, you can also save it to a config file so that you have redundancy in the hardware that you bring to the launch site. If you're bringing multiple laptops and the one that you originally set up has some kind of malfunction or you forget it at home, you have that file that you can simply pull down and then load the config so that you don't have to set up your ground station again at the launch site. In an ideal scenario where you are using the same ground station that you set up with, you can simply just reopen it with the same settings from the day before and not have to worry about setting all of those configurations up at the launch site. All of this means that once you get to the day of the launch, all you have to do is plug in your radio sources, and then it will feed telemetry directly into the ground station, and it will be saved automatically. Data is saved both in binary and CSV formats. We save to binary directly after we receive the data, and we save to CSV right before the display. This allows us to have essentially the two ends of like the data saving spectrum, where we have a highly synthesized version of the data that is in a CSV file and a very raw version that is in binary. CSV is obviously more human readable, but binary will be better for catching errors and seeing more and having more to analyze into the future. To test our ground station, we have pursued functional and UI testing. Functional testing was done for unit tests, where we tested what we considered a critical section of the code that had a lot of logic in them. That was our parsers and our data processing modules. For UI testing, we pursued systems tests, where we fed in pre-generated packets and saw that the UI matched what we would expect once receiving those packets.
So for previous use of the Wings software on our team, in 2024, we tested Wings with a IREC recovery test rocket. We had the Telemega on there as our telemetry receiver, and we matched it with the Alt OS software, and it matched almost perfectly, which was really good to see. We also have tested it with our SRAD flight computer. This was both a validation of the computer and of Wings, and they both ran very well. Wings and the computer gave the same data and had the same telemetry receiving, which was good. And Wings was able to run for over 24 hours with the computer, so we know that it can last a while. Overall, Kuba's development for Wings has been very beneficial to our team. It has helped us in recovery consolidate our ground stations to be all in one place and all very easily readable. The customization has been able to help us, identify problems that we want to really make sure aren't there, like continuity or like battery voltage being down. And we also really like the lack of risk. As Kuba said, it is saved two ways, both as binary and CSV, so we know we always have it, plus having it, being able to move it from computer to computer at ground stations is very helpful. Overall, Wings is a great open source project that we have developed, and we hope to continue to improve and hope that one day Rocketeers can use it all the time. Thank you so much. Any questions?
How extensible is it?
Sorry, can you repeat that?
How extensible is the software?
What do you mean?
In terms of incorporating other flight computers and so on?
Because we've done our software through interfaces, is extremely easy for us to develop other expansions in the future. Part of that config system that we didn't mention so far is that you can also input the packets for a direct serial input. So if you have your own COTS flight computer, you can put in the packet format and just use that based off of the config. But for implementing other kinds of flight computers is also extremely easy because they all use the same interface, and it will be easy to build off of. Yes?
Yes. So the you've tested it with 4 flight computers so far, you said?
Yes, yeah.
I assume those are all on relatively the same frequency bands, is that correct?
No, they're both in the 900 megahertz and 420 megahertz bands.
Okay, so
yeah.
how do you do multiple, like the 900 and 400 are very different frequencies, do you have multiple antennas for that? Do you use the same antenna?
Yes.
How do you parse those two signals on the antenna?
We keep different antennas for each radio signal. Yep.
Okay, so still with one laptop you have multiple
Yes, yeah.
antennas plugged in, so you're kind of limited by your USB ports.
Yes, yeah.
Okay.
We typically use a USB hub with the application to keep multiple streams going.
So with the Wing software running,
Mhm.
would you still be able to run the base station's native software in the background? So
I believe not. Most of the devices can only communicate with one software at a time, so you would need a second laptop with a second transceiver if you wanted to do that.
Okay. How hard is it to expand for other manufacturers? Is it something that
Expanding.
users would be able to do, or is it something that you'd have to work with you to develop that?
It is somewhat easy. We have documentation how to do it, and it is, as long as you know how to, like, what the interface is, you add about 2 files to codebase. Once you're, like, experience with it can take about a week or two to implement and then test. So it's not that difficult of a pursuit to add a different kind of manufacturer.
And what programming language is there going to do these types of extensions?
Yeah, here, let me go back to see. We have a little bit of a slide to talk about this type of stuff. There we go. We built this in Rust. It is a framework called Tari, oh yes, I should say next to the microphone. Okay, we made this in Rust. It is a framework called Tari, and we have a JavaScript-based front end. That is what allows us to be cross-platform and display on pretty much anything that allows for a browser. It is simulating the browser from the operating system to display the UI, and the backend is done in Rust to process all of our backend stuff.
So because of that, would this be able to run on any OS?
Yes, yeah.
So why did you pick Rust specifically?
We wanted a low-level language that would just parse stuff faster. Like, you run into issues when using something like Python where, especially when you're dealing with multiple sources like this, stuff can get slow. If we want to include like GNC algorithms or stuff like that into the future, we want to keep the data processing as lightweight as possible. So that's why we went with a programming language like Rust. We simply chose it because there is this framework that works very well with it as an alternative to something like C++.
Yeah, another
Yep.
question about processing rate and buffer rate. So
Mhm.
assuming you have like 4 antennas collecting data at the same time, I imagine as you add more antennas, your sampling rate might go down if you don't structure it properly. So like, let's say, you're a super user, you have 20 antennas, and then one day you have like a Da Vinci setup, I don't know. Then, like, how bad does your performance degrade for each antenna you add?
We actually have never ran into that issue on the team. We've never gotten up to 20 antennas as a use case. We've tested with up to 4 sources like this launch before, and we've done those at about 100 packets a second on each. And we ran into no issues with that. Our bottleneck is actually the display, but because it is independent of logging, we still save all the data. The display just starts to slow down in terms of what you see on the screen.
Can you explain the advantages of saving everything as binary before you save it as a more complex CSV or Excel file?
Sometimes the parsers might not recognize a packet, especially if you're getting very garbled data. You might get a CRC error or something like that. This allows you to, in the future, if you get like terrible data, go back and analyze everything and figure out what happened. Yes?
What does the interaction between your backend and your front end look like in terms of like the interface? Is that like the Rust backend is like there's an interface for each radio module and then the JavaScript framework is calling that, or?
We have an API. Most of our logic is kept in the backend, so what the front end sees is simply updates on what packets the backend has received. It doesn't really see what kinds of radios are connected, but yeah.
So when you parse from different devices, how do you specify like the packet format? Is that like hard coded in like some different functions? You specify what type of device it is, or?
For manufactured flight computers, we keep them hard coded, but for SRAD flight computers, it is editable through the config.
Are you finding for a given manufacturer specific, they may have multiple devices. Are they generally, your backend, is that able to handle all the devices within their nomenclature?
In our experience, most manufacturers tend to keep their telemetry the same and just send different packets. So we use the same parser and just simply feed a different packet into that parser for it to spit out.
You talked a lot about your software capabilities. I'm curious about what your hardware setup looks like in the field and any difficulties you've run into with that, trying to manage all your items and to get them all pointed in the right direction.
That tends to fall about, we tend to use the same hardware setup as what you would use with a normal COTS avionics. So you use a Yagi antenna or a radio tower, depending on what you want for that specific flight.
Okay, so you have 4 team members all pointing the antennas.
Yes.
Have you considered some sort of optimization for that, like a stand or some hardware box you just take with you and it's all compact? Have you built any of that out?
We haven't pursued it heavily. Most manufacturers aren't exactly happy with us making versions of their receivers, so we try to keep them happy so that we can continue using their data, and because of that, we use their manufactured products. Any other questions?
Again, assuming you're out in the field, it's hot, your computer overheats and it dies in the middle of, trying to sample data. Do you have a built-in, constant saving so you can recover data, or is it lost?
Yes, it is continuously saving to a file. Immediately when it's received from the radio, it saves it to binary on a continuous write. So all data will always be saved. All right.
Any other questions? Thank you so much for listening. You want to go get your computer?
Yes, yeah.
My hair was falling out that whole time. So many photos. Thank you,
Yep.
Good job.
Eventually trying to get a job in either that. What are you guys working on?
I was able to
Trying to kill both. I don't even know a mod without like a very
of course, yeah.
get out.
Yeah, we're doing
You someone walk open the door.
Yeah, we got 5 minutes. We have 5 minutes.
No, Paul's got to cook.
Graduated. It's like, oh my God.
It definitely does.
Eric is a spatial health communication. Works on the chips that go in. It's all done, man. Just finished up. If you check that, sits between the radios and the computer programs. Analog digital.
Yeah. We can do the note cards.
Although a lot of the people I used to work with are from Texas. They used to do a lot of really cool stuff. And they also used to do a lot of really weird stuff. They used to do a defense contractor and you just have a script question. I think they still do some stuff. Erickson, and it's E-R-I-C-S-S-O-N. It's backwards to how, like, in English we spell it. There's 2 S's. I didn't find anything the first time I looked at it. Don't tell them this. Labs will have that issue in the video. Everyone knows that. It's on the video. And you'll be right next to Elsa. I guess I will. She's out in Los Angeles. Oh yeah, so you interned here last summer? Yeah. Nice. Yeah.
But it was great meeting you.
It's great meeting you, and hopefully you guys are launching tomorrow.
I really hope so. Fingers
For a
crossed.
few hours.
Yeah, fingers crossed that we do.
Which is very funny.
As far as everybody on our team says, it is interesting. This one right here, you need to ask.
So many questions.
Nothing.
Throw your phone. Get her out of here. What if we do a let's go to the
A little video.
This is just regular.
Oh,
No, those are the previous ones.
yes, they are.
Okay.
Again, give me the song, Phil.
It's Vanessa.
Fill it out, maybe after this, after, your presentation today, maybe tomorrow, we can just fill that out. It's, has a place to submit your slides, and then a couple other questions about just like the types of just fill it out once. Yeah.
That's only me as a judge, technically,
I saw your shirt. I thought that was your shirt. You guys we gotta ding you guys on that or something. You shouldn't be allowed to.
Full color.
I know. You guys gotta have a secondary color or something, right?
Well, it's a goal.
Be shiny.
Oh, hey, it works.
No.
Hey.
Are you open at the launch site? I'll be there for the next 4 days straight. I was studying it. I don't know. A bunch of like shit out of the road. Yeah. It's great. It's a long story. I could talk for a while.
Just turn off.
He's getting the big Ezra paycheck, so he's not really big Ezra. 6 figures. Yeah, it's just like, yeah, 6 figures. Holes your nose. At the same single one of those. I'm paying to be real. I didn't take PTO. It's like a. Took like my PTO. How we doing? Chat, we're cooked.
Are we cooked, chat?
Chat, we're cooked.
It's black screen, but with audio it says chat.
Has audio? W's in the chat for audio?
W's in the chat for audio?
W for audio?
Chat, can you hear me, chat? big L's in the room.
Can we please add video? Video? W video? Is it? Oh.
Are we cooked, chat? We're so back.
We're back?
We're so back. All right.
Hi, so today we're going to be talking about the active drag system, or our ADS, which is a precision apogee control for a sounding rocket. My name's Brady Raykop. I'm on our subsystem sub-team. I worked on the mechanical side of the ADS.
I'm Dawson. I'm the avionics lead for rocketry. I did all of the electronics.
I'm Ben. I'm the subsystems lead for our team, and I did a lot of the CFD and analysis stuff.
Okay, so starting off, the active drag system was developed in response to the Precision Apogee Challenge, part of the competition. It's our way of getting as close to 10,000 feet as possible. So it's our way of dynamically changing the drag force on the rocket so we can, mid-flight, change how high we go. And then this is our third major iteration of the ADS. We've worked on it over the past few years to improve the mechanical side, the electronic side, and the CFD. So this is the overview of the mechanical design. Starting off, we have 4 flaps that are vertical and they deploy at an angle. Each flap is mainly carbon fiber with inlaid aluminum slots in order to use our track and ball. So the pin right here goes in that track, and then it moves up and down so the flap can deploy at an angle, whatever we want it to do. And those are manufactured in-house. And then we also have a rack and pinion system, which is sort of the internal way of actuating the flaps. There's 4 different tracks, and they're on 2 levels, but then the ends are curved so that the pins go at the same plane. And then to actually connect the flaps to the system and inside the rocket, they're attached externally using a lock nut and a bolt. The lock nut's epoxied inside of the 3D print and attached that way. And mainly the structure is actually made of ABS because of the higher melting point. Since we're in such high temperatures, it's all 3D printed.
All right, now to actually control the system, first we need to know the drag force on the rocket and on these flaps and how it changes with how, depending on how deployed the flaps are. So we ran a lot of CFD, or computational fluid dynamics, using ANSYS Fluent. We created 5 different CAD models of a simplified rocket, so just minus like the rivets and some of the smaller details to it to improve the efficiency of the model, and ran it over a range of 25 meters per second to 250 meters per second in increments of 25. We ran those, each one took about hour, 2 hours each, and then made sure to include some error of the convergence. That error increased with increasing velocity, but it was still within a usable range, and the data showed a consistent relationship. You can see in that graph right there, that shows the drag force related to the velocity over the degree that the ADS is deployed at. So as you can see, the more it's deployed, the higher the drag force, and the faster it's going, the more drag force it produces. So using all that data, we then fitted a polynomial to all that data to have a function to use during our active control when we're using the ADS. That we input a velocity and a drag force, and we can get a deployment percentage and vice versa, whichever way we want it. Next slide. All right, so now moving on to how we started controlling it. So we first came up with a way to determine the apogee that it would reach at any point during the flight. This is primarily only used during the coast phase of the rocket, so after the motor's burned out. And that equation up there at the top is what we came up with. It's just a rearranged of work and energy balance. It only uses the current altitude, current velocity, and current drag force of the rocket, as well as the dry mass of the rocket, so after the motor's burned out. This model also assumes that it's a solely vertical flight, which has been shown to be a close enough approximation. In future years, we might try to include non-vertical flights into the model. It also assumes a constant air density. Just because we're doing a 10K flight, the air density doesn't change that drastically, so it's a safe assumption to make for our model. If our rocket was to go higher, it might be worth including a variable density for the air. That graph shows, so in the blue is where the rocket is during flight, and the orange is what's being predicted of where it will be at that moment later for the apogee. That's from data from our second test launch this year, where we launched to 10,000 feet, and you can see that the apogee follows. It does have some oscillation near the beginning, just because it's a little unsteady, and our flight wasn't as straight as purely vertical, but it does predict a 10,000 foot or whatever we're going to be pretty accurately. All right. So now working on how to determine what deployment percentage to deploy the ADS, depending on what apogee we're predicting. So since that formula on the last slide has drag force within the natural log and outside of it, you can't solve it algebraically for drag force. So then you have to solve it numerically in MATLAB, which is what we use. and then we solve it for MATLAB and for the drag force over a range of possible velocities and possible altitudes that the rocket could be at. The results are shown in this gray graph here. So on the x-axis, it's the velocity of the rocket, and on the y is the altitude. And then depending on how closer to the white it is how much drag force is needed to reach exactly 10,000 feet at that moment. So, for example, if it's like 0.25 velocity in kilometers per second and 1.5 kilometers in altitude, you need, depending on where in the grayscale you are, is how much drag force you need at that moment so that you reach later on 10,000 feet. So then we can convert this into also a fitted surface polynomial to then be used in the code to spit out a drag force that's needed depending on altitude and velocity, and then which we can then put from the CFD determine how much deployment percentage of the ADS that is needed for that. So, yeah.
Okay, so of course, all of that analysis was needed to get to the point of actually running this, but these are the electronics that actually controls the servo and the air brakes. So this year, we went with a RP2040 flight controller that we designed ourselves. In previous years, we used a Raspberry Pi Pico development board and developed a pretty established code base using that, so we wanted to remain with that same microcontroller because we knew how it behaved and its capabilities. One of my favorite things about this is that it's a dual core processor, so I can kind of multi-thread actual control events versus data logging. On the board featured is the RP2040. There's 4 different sensors on there. There's a barometric altimeter. There's a 6-axis IMU that has 3 axes of acceleration and 3 axes of gyroscope. There's a high G accelerometer for plus minus 200 Gs. Not really needed for this kind of flight, but kind of future-proofing for if we want to use this flight controller in the future. And then there's a additional magnetometer for initial orientation estimation. Also featured on here, because we're driving a servo for the air brakes, one of the downsides of the servo is it is its own separate control circuit for the motor. So when you turn it on, if you apply power, it's going to have a pretty high idle current draw. So in order to avoid batteries dying on the pad, I have a servo control circuit with an N-channel MOSFET such that I can control with the microcontroller whether the servo is receiving power or not. So the servo is completely off until the launch detect, which I'll go into in a little bit, such that the servo isn't, like I said, idly drawing current. As for other things about it, the USB, I can plug in to the flight controller while also having battery power, so I can debug while running the servo and other electronics, because there's a 5-volt output, because we have GPS and telemetry in the same package of system, just for convenience reasons. So that's the primary schematic, and there's a block diagram, a little hard to see. All the sensors are on one I2C bus. And then there's a couple interrupt lines that are also going to the microcontroller for the state machine. So, next slide. So, with regards to software, like I said, there's a state machine that the flight computer goes through in order to make sure that we're only deploying the air brakes during the coast phase of flight. So, when we initially turn it on, it will start blinking and the flaps will go doo-doo, and to just indicate that everything is on and enabled. And then it will turn off the servo and let off until it detects that we have reached 100 feet off of the pad altitude that it measures on boot up, as well as we have exceeded a 2.5 Gs of acceleration. And then it will say that we are in boost mode. Now, at this point, we set a hardware timer to about 10% above what the expected burn time of the motor is. So for this year, it's an M2500, which I think is about 3.9 seconds of burn time. So we set that to like 4.2 or 4.3 seconds. And then we also have an event for deceleration of less than 1 G for detecting the coast phase. And then during the coast phase is when we're actually actively deploying. Like Ben said, I have several equations that I can kind of walk through to get to what my desired deployment percentage is. The primary ones being the desired drag force to reach exactly 10,000 feet. Like he said, I pump in a current altitude and current velocity to get that. The way I get the velocity is I take the barometric altitude and I fuse that with the accelerometer z-axis reading via a Kalman filter. For tuning the Kalman filter, I basically took the launch data from last launch as well as the variances that are present in the sensor's data sheet, and then just kind of tuned those until I got a response that I wanted with regards to velocity. And then I pump that through to the drag force equation, get a required drag force, and then throw that into the deployment percent equation to also get a deployment percent. Like I said, this is only during the coast phase of flight. One of the big issues with the RP2040 is that it does not have a floating point unit. So I had to do all of this in fixed point math, which I don't know if you noticed, Ben was referring to things in kilometers and kilometers per second. One of the downsides of fixed point is that I can only represent between 32,000 and negative 32,000. So in order to scale the meters per second and meters, which are already in the ranges of like 2 to 3,000 with regards to altitude and like 1 to 200 with regards to velocity, and the polynomial is a third and fourth order polynomial. I had to scale those down and apply that to fit within the fixed point so I don't get any weird wraparound overflow errors. Yeah, and like I said, the RP2040 has a dual core, so I do all of the controls and the sensor sampling. All the sensors are being sampled at 500 hertz. And then all of the Kalman filter and the controls, because the servo can't necessarily react very quickly, just because it's the nature of a mechanical actuation, I set that to 50 hertz. And then the data logging is in 64-byte packages that is logged at about 100 hertz. And when we're sitting on the pad, we're logging to a circular buffer such that I don't actually write anything to flash and take up space until I know that we've launched. And then I log the last 2 seconds of flight data such that I have, if you've ever looked at a recovery altimeter, you know that they have just before flight and then the actual launch itself, just so you know you're capturing the entirety of the flight. And then we stop logging once I've detected the end where the altitude is around where we measured the ground altitude to be originally. And is no longer moving, I'll be like, okay, the flight is done, we're not logging anymore, we'll end all the controls and we'll turn off the servo to save battery power for the telemetry side of the system. So the results, unfortunately for this year, we weren't able to necessarily get the CFD done in time, but a lot of the graphs that Ben was showing earlier kind of show that we are able to pretty stably predict apogee given the conditions of a similar profile flight. It's a little slower acceleration with regards to the M1939 that we flew on in April than the M2500 that we will be flying on. But I'm hopeful that the air brakes will deploy just as planned. This was also a failure mode with regards to the inertial measurement unit did not work necessarily, so I was operating purely on a barometric altimeter, and I was perfectly capable of going through the state machine and not deploying. This was right towards the end of motor burnout, and then this was during the coast phase, and that was apogee, such that these are retracted, deployed. It's a little hard to see just because of the angle, but deployed, retracted at apogee to save the flaps and not damage them as it's descending. So, yeah, that is the active drag system.
Do you have a question for you guys?
Yeah.
Why do you guys decide to design your air brake system with a vertical slats instead of a slats housed inside the airframe that will spin out?
So the thing that I've been telling people is in past we actually did used to have air brakes that were just slots that popped out. One of the things that we've dealt with personally is those just shearing off of the rocket. And while they can be made strong, we found it to be more intuitive with the flap design as well as with integration and not having massive holes in a rocket.
This also gives us a much larger range of controllable apogee than the smaller internal flaps.
I know most teams you've probably seen also have an air brake system where it just pretty much mounts to the body tube, so there's no holes having the airframe. This air brake system just has their holes. But I like the slats.
Yeah.
Different. And then was the velocity, altitude, and drag force chart a published chart or a team-made chart?
That's all team-made on MATLAB.
I didn't hear that part, so I wanted clarification on that. Okay. Any other questions for them?
Yeah, so for your CFD, I know you said you didn't get it in time for the first test, but were you able to collect any data or anything to then verify your CFD?
Not yet. Like I said, the CFD model we used is also very simplified just for right now. With some of the licensing, we're not given as many processors as we could have had. So simulations take a long time and a lot of hours. And since we're trying to get lots of data points, it was simplified. The team will probably work on it more next year to get a better model and maybe a more accurate model. But I think for this year, it was mainly just trying to get that main relationship of kind of what it would look like and then work on accuracy as we go.
I think one of the big things we were focused on was just making sure that state machine works so that the flaps didn't deploy during the motor burn. So our 2 test flights, we didn't really get a chance to do a baseline flight of no flaps and compare that to the CFD model. I think he was next.
In the event of like a loss of power, like a connector comes disconnected or something, what happens to your air brakes?
Well, the servo is kind of difficult to move even when it's powered off. So I imagine that if the brakes are kind of deployed and power cuts, they'll just either remain or be pushed back in. There's not really an issue, like I said, there's not really an issue of it shearing because they're not just a straight thing that pops out of the rocket.
So you guys have fairly large control surfaces. Was there any analysis or looking into like you generating a lot of turbulence with those flaps? Was there any analysis or concerns with that disrupting the airflow over the fins?
Yeah, I was looking into that some. I think some of the reason we were getting some errors with higher velocities is because of some kind of turbulent thing that the steady state fluent can't handle. That's something I think the team should look into next year, is trying to do the transient analysis at higher speeds to try and figure that out.
Did you guys run CFD, maybe I have not caught it, with the flaps, or was it just because I think I heard you mention you ran CFD of the simplified rocket, but was it with the flaps like at different angles, or how did you measure how much drag were your flaps?
Yeah, so we had 5 different models with one all with the ADS on it, so 0, 5, 10, 15, 20 degrees off the side of the rocket. What I mean by simplified is just like some of the holes like were not included, some of the details and around the fins, that sort of thing. So just some things to make it easier to mesh and run the simulation just for a base. And like I said, we'll probably work on getting more precision and accuracy next year.
Let me ask this question. Your air brake systems are located where on your rocket right now?
They're
how far off, or how far from the fins?
They're directly above our motor, which it's very close to our center of pressure, which also helps with us keeping our stability the same. So, but they're
possibly moving your air brake system forward, so it won't disrupt the airflow over the fins as much.
Yeah, I mean, like I said, we'll probably do more analysis on that next year to check, but we haven't had any noticeable issues in flight when simulation or in flight with them affecting how the flight path goes.
Yeah.
So, but definitely something to look into.
Any more questions? You guys are good to go then, right?
Thank you.
Thank
guys.
Excuse me, so sorry.
Let me see that.
I think that's the point. Damn, all the angles all the time.
What's funny is he like not necessarily encodering, but like adding some other feedback mechanism is measuring the amount of power drop that the servo runs through. Because that would be a pretty good estimate of there's probably a spec sheet that this was producing for how much power is required for each servo. And we could convert that back.
Yeah, this room keeps going. That's fine.
What's gonna happen here is go live.
Yeah, we're live streaming.
You want this presentation goes to live?
Yeah, we're already too. Yeah.
Write down everything, I remember what they said. You know what? See, I thought they were saying that one board was like curved because of the shape of the rocket. You can like this one. Yeah. But like, I think that highlights. I think we don't actually know like what the implications are like for it. Like we would never have known that word curved because like we would never know what. Cut that sequence in half. And that's like a kind of problem. Right. Like we're not designing for a rocket, we're just designing for like. Yeah.
I was trying to, like, if there was like more, if there was more agent, I think I would have. Does it have any way of like pulling it this way? Instead of like people pulling it hard, this had any sort of I think the different design is the way that we wouldn't take much. It shows like videos of the like rocket boats. They did like a real rocket. Y'all were the University of California. It's all like turns.
So I was like, so I think that one just means
But like where we're just like standing and watching.
so if you want, you can go to the garage or something. Have you explored one? What? Yeah. It landed in April, yeah. Yeah, it's Oh, I can't. I kind of want to show you.
Do you want to go?
No, I mean, I've seen like that.
I've seen that.
You know, like I've seen everyone's
Like Naruto.
Yeah. Naruto feels kind of more. That feels like sacrilegious, I know. But like, I don't want to.
My best friend tried to get me to watch that a little bit. I guess I said that that's like the cool fight scene. And I just felt like no sense of stakes. Like it just gets weak and thrown out. He's just always going to be fine. You gotta understand. Like, sure, you gotta watch the videos. I guess I should. I'm not even that much of a fanatic.
There we go.
Oh, it's not.
Is the table close to you? Yeah.
Is it reclined?
Yeah.
You got it right here. There we go.
Oh, cool.
Good to go? Yeah. All right, can everybody hear me? This is just for online. That sounds good. All right, hey everybody, my name is Nick. I run the YouTube channel Lafayette Systems, and we're going to be talking about guidance and control systems, kind of under the lens of safety. Can you hit the next slide for me? So first we're going to talk about my background, who I am, and what I do, and then go through a little bit of an introduction into what guidance and control systems actually are. That gives us the same vocab to work with. And then we're going to go through how designing for safety is designing for failure. And then lastly, I'm a new engineer. I hit kind of industry within the last couple of years. So I wanted to share some lessons that I learned hitting industry coming out of undergrad and grad school that I didn't really expect. And then we'll save time for some questions at the end. Next slide. So my background, I'm an engineer in the military. My focuses are on UAS, that's what we call drones, and then also missile systems. That's a lot of fun. Next slide. My projects, I do a lot of work on the side. Doing rockets with active control systems. So this one on the left here, I fired a rocket out of a silo. That was pretty cool. And then the one on the right, that's another rocket with a tail fin control system. And then I had small solid rocket motors that you could kind of steer it around by firing those off at apogee. That didn't work very well, but it was super fun. Next slide. I did another project. This was really fun, where I did basically GPS waypoint guidance with an amateur rocket. This had a tail fin control system. And this is steering to a coordinate in inertial space. And then it recovers afterwards. And I've done a lot of testing with that software. A lot of the work that I do in my free time is not so much on the control side, it's more on the guidance side, figuring out different ways where we can steer rockets to go do interesting things. Next slide. So this is a big project I'm working on now. I call this Sapphire. So this is a larger vehicle. Trying some new things. I'm doing antennas baked into the strakes. So those are giant PCBs that I've made. That should be interesting to see if that works. And then all carbon fiber airframe, trying to do some supersonic control. Next slide. And yeah, new avionics for that. It's going to be pretty tough to get all the power draw that I need on it, but that's going to be a really fun project, so I'm excited to see this guy fly probably towards the end of this summer. Next slide. So let's talk guidance and control systems. When we say guidance and control, really we mean we have some system that has a state vector that is just a list of numbers that defines where it is and how it's behaving. And we're trying to move that state vector to a specific different set of numbers. So if you're viewing that in the abstract sense, your house has a control system for its temperature, that's the thermostat, and the state vector is the house's temperature. For an aerospace vehicle, that state vector is typically much longer, and it has a lot of other things, typically position, velocity, angle of attack, angular rates, sometimes other things that are on there as well. So if you look in the very right side, plant dynamics, this is the kind of block diagram you'll see in a controls class. The plant dynamics is our rockets. That's the physics that are applying to the system. We don't really get to control that. You get to control that based on the design of the vehicle, but once it's built, that's relatively locked in. And that has an actual system state. Now, a navigation function is how we determine what that system state is. So in theory, our measured system state is the same thing as the actual, but it's never quite that way in reality, unfortunately. So when you say you have a GPS navigation system, your GPS system is telling you where you are in space. Sometimes it's also telling you velocity or heading or some other things. That goes up to our guidance function. So the guidance function tells the system where to go. If you have a simple system, like the guidance function in your house is kind of the set point that you put on it. Some thermostats have a more sophisticated guidance function where you can like set the temperature to change over time, so it gets cooler at night and stays warmer during the day. But the output of the guidance system is a desired set of corrections. And the line between guidance and control is kind of blurry a lot of times, but these desired corrections are fed into our control system. The navigation system is a mixture of sensors and then a lot of math. The guidance system sometimes is also sensors, but a lot of math. And the control system is sometimes math, always some mechanism that can interact with the outside world. So in your house, your thermostat doesn't actually change the temperature. It's either the AC unit or it's the heater. In an aerospace vehicle, that could be your thrust vector control system. That could be your fins. It could be reaction jets, something like that. And those impart some force or moment on your system. And that changes the plant dynamics, and that's how you get your system to change what its state is. So with all the vocab out of the way, we'll move on. It might be useful to you guys. How I usually phrase this in videos is guidance is where do you want to be, navigation is where are you, and controls how do you get there. Typically, mathematically, we describe those a little bit differently. You'll see some kind of standard notation. Typically, your guidance input, sometimes also the control input, again, that line's blurry, is the vector u. Your current vector state estimate is x, and then your control vector is delta. That's usually a list of sometimes like control surface deflection angles. So the thesis of this presentation is that safety-centered design, or design for failure, is integrated into your design at every stage. Another way to phrase that is that it's basically a lens through which you can view the design process. So you can't really design a vehicle and then bake safety into it afterwards. A lot of the decisions that are going to inform fundamentally how safe or reliable your system is are the ones that you make at the very beginning. Next slide, please. And a lot of that comes from design for failure. So my opinion is that really good engineering projects aren't just making the system work. That's almost a research project, like, can I make a rocket that flies? We've answered that question. I think a better question is, how do I make the best rocket that flies that meets an incredibly vague set of requirements while also baking in things like reliability, safety, and cost? And we're going to view this from the lens of risk. So risk, I think we intuitively understand risk from a prospect of I want to keep my fingers all on my hands over the course of a rocket day, but risk also applies in other ways. So one way that I see risk applied a lot is in technical risk. So if you're pitching a program to your manager or if it's pitched to the government that is incredibly sophisticated, the risk that we have is we spend a ton of money and then it just doesn't work. And that's wasted time, money, and effort. Another form of risk is risk to your test assets. And I think this is something that you guys probably have experienced in IREC is you want to test your rockets early and often, but if you destroy it in a test because you didn't prepare well enough, then you're kind of back to square one. So we want to take appropriate risks. And for your program, for your IREC team, for some industrial projects you're running, if you destroy the thing you're trying to build in a poorly thought out test, that poses the risk of injuring people. But another risk is that the entire thing's canceled and that the entire thing was a waste of time and effort. So we're going to look at some examples of how you can kind of bake this kind of safety for design into every phase of this design process. So this is our imaginary new rocket we're building. We're building a rocket with a guidance and control system. And I've kind of broken out 5 phases for us here. There's obviously more, but these are just the ones we'll talk about today. And we're going to go through all of these in series and how we can think about reliability and safety and bake it in from step 1. So first is your requirements. For the competition levies requirements on you, and sometimes your teams generate their own requirements as well. Sometimes the requirements are, we're not going to use some material that's annoying to use. If you could use some fancy titanium for your airframe, like, that's great, but can you even afford that? So maybe cost is a requirement that you impose on yourself. Well, there's also requirements you can impose on yourself for safety and reliability, and these are some examples of them. Sometimes they're more broad, and sometimes they're highly focused. So one example I'll have is if you have a canard control vehicle. A huge concern is what happens if the canards stop working. Maybe they stop working because their servos lose power or some important piece of the drivetrain breaks. We want to design in from the beginning that regardless of what fails, if something fails, the rocket doesn't spiral out of control and come crashing down in the parking lot. So one way to do that is if you said we're making a canard control vehicle, I want the canards to feather into the wind if anything goes wrong. You can put the center of rotation of the control surface forward of the center of pressure. So that way if you lose power or something breaks, your fins just feather. And you can bake that in from the requirements phase. If you don't do it here, then when you get to the aero design phase, you might realize that you can't put your actuators in the place they need to be put to meet this requirement. Another one is in your guidance system. If you're flying an airplane and you're looking outside and it's beautiful, and then you look at your instruments and the instruments say you're upside down, clearly that's wrong. Like, clearly you have a ground reference to understand what's true and what's not. Your automated systems, your navigation system on your vehicle doesn't really have that intuition, so you need to tell it that intuition. So if you take off and your vehicle immediately thinks you're several kilometers under the ground, something has gone wrong. I don't know what it is. It probably doesn't really matter what it is, but at least for now, you should probably stop trying to control off of obviously incorrect information. So part of the process is baking in these requirements to say we're even going to look. Like, that's step 1. We're just going to look to see if our guidance solution or navigation solution has obvious flaws in it. In the aero design phase, we get to make some important decisions, like where do our control surfaces go, and then if we lose those control surfaces, either mechanically, like they fall off, or they stop working, what will happen to the vehicle? So I have some recommendations for this, and this is something that if you're designing one, your team should probably look at. So for canard or wing control, so that's where we're putting our control surfaces kind of at the center of mass or forward, then your vehicle should be stable without them, and your failure mode is basically the vehicle just turns off the control system and flies normally. We fly rockets without control systems all the time. This shouldn't be an exception to that. For tail control, that's where our control surfaces are at the back of the vehicle. The failure modes are a little more complicated. So if I lose a tail control surface, that was also probably contributing to the vehicle's stability. one of the failure modes you can design in is that the vehicle will just start to tumble. So if you lose a fin, what we don't want to have happen is the vehicle becomes a ballistic missile and hits somewhere unfortunate. It might be more useful for it to just spiral, lose a bunch of energy, and then deploy a recovery system. But that's a more nuanced design choice than for canard control, where we just say the vehicle's stable with it or without it. If you make the wrong decision, this is a very early rocket I made with canard control, and I had built it out, and I was with my roommate, and it had a stability margin of about 0.15 on launch, which is cutting it a little close. And he was like, it's good, it's got a control system, it'll be fine. And that was a really bad design choice because it immediately spiraled into the ground. So again, we want to assume that our systems aren't going to work and design our entire vehicle around the fact that our fancy control system probably isn't going to work on the first try. In terms of mechanical design, a big part of this is design for failure. We're intentionally going to create a portion of our vehicle that is weaker because we want it to fail first. So for canard or for wing control, one thing that I do is I intentionally make some linkage or maybe some gear that's part of that drivetrain the weak link. And then I know that when it fails, I've sized everything correctly so that my control surfaces are going to feather into the wind and the vehicle will work just fine. There are different ways to do that. For tail control surfaces, it's again a little more difficult. You don't want your system to tumble if the recovery system won't deploy automatically. So there's a little bit more nuance that goes on there. One way that you can bake that into tail control systems is thorough ground testing, and then if you have a intentional drag deploy system, and I have a picture of that next. Just kidding. Let's talk about linkages. So this is one of the linkages in one of my early rockets. That red linkage was made out of PETG, so that was 3D printed, and the rest of it was fancier materials. And what I was planning for here is if this vehicle, falls out of the sky and smashes on the ground, I don't want to break my expensive CFPC control surfaces. So I intentionally broke this stupid little linkage out of PETG that I could reprint in like 10 minutes. So that's way better than breaking and trying to repair some fancy filament. So for tail control systems, the other way that you can do it is you can intentionally have your tail control surfaces deploy against each other. So as the vehicle is ascending, you're basically deploying them as air brakes. We can't stop the solid rocket motor from burning, but we can waste as much energy as possible in drag. So that's something that I've implemented on all my tail control vehicles. For guidance and control design, baking in redundancies is very useful for the fancy guidance modes. So if you guys can demonstrate attitude-only guidance where you just point the vehicle in the right direction, that's a really great safety system that you can apply on the back ends to any of the more fancy guidance modes. A lot of these are very susceptible to small errors. So if you have a single minus sign in the wrong place, or you have like 0.001 versus 0.0001 on a control gain set, your system's going to spiral out of control. So if you have limits set, and then you revert to one of these backup guidance modes that you've already tested, that's one way that you can kind of build on your previous flights, and then you risk people on the ground less. You also risk your test asset less. If you destroy your rocket because you didn't test something very well, again, your program's kind of canceled. Again, the drag recovery configuration is something that I tested a lot, and it's actually saved my flights multiple times. So here's another one in guidance and control design. This is a flight where I exceeded a pitch angle limit, and you can see waypoint guidance, and it reverts to this abort Euler guidance. So this is a case where I built in pitch and yaw lockouts. So as I tried to steer towards a waypoint.
Or would you recommend more just building it into the system itself as you're making it?
I think it depends on what your failure mode is. So for rockets, the failure mode is they smash into the ground and get destroyed. And so a lot of times it's better to be asking the question, like, when this fails, how will it? If you're doing something relatively benign, where if it fails, maybe even you replace a capacitor on like a circuit, that's a lot easier and a lot lower cost. I think when we're building big systems like this, it's the risk of destroying your test asset becomes a huge one, right? If you guys did a test launch a month ago and destroyed the vehicle, like, it's over. So that's something that I think particularly applies to rockets, but it's definitely a balance, and it'll depend on how sophisticated your system is. Yeah.
Have you tested, so you mentioned the canard linkage that was supposed to fail early. Did you test that system actually did fail early? Because when I think of something falling on its fins, for example, like there's a bending moment like in that axis of the airframe, and like I'm not sure if that is really mitigated by not letting it twist. I don't know.
Yeah, that's a good point. And it's important to understand the failure conditions. I tested it by pushing really hard on it, and it's the first thing that broke by twisting the fins, which you're right, is a different failure condition than just dropping it. So if at the end of the day, if I broke a control mount, like that's like a 8-hour print, that's pretty annoying. You're absolutely right, though, that if you have what we call a golden egg in aerospace, like some component that you literally only have one of, and you can't make another one, and that's it, then you would really want to understand those failure conditions before you did it. So sometimes that's like the engine on an orbital launch vehicle, like they don't have an extra. So if you're doing a ground test and you destroy it, like the whole launch is canceled, and understanding those failure conditions is an important part of that. Yeah.
Asking like what priority should safety be in terms of designing like a system? So for example, like our team this year is designing like a canard-based control system. So we sort of designed it so that like first we took into account like other variables, but then like after a while we designed the whole system, and then we were like, oh, let's look at safety, and then we had to like change the whole design to accommodate that. So what sort of I don't know, what sort of priority do you think should safety be in terms of like designing a whole system like that? Should we be like redesigning the whole system, or like try to like fit it in somewhere in terms of like other priorities in list of priorities?
Yeah, that's a good question. Where do you, like, how do you balance the fact you need to build the system versus design it safely? It's going to come down to your tolerance for risk and then what that risk looks like. So this would be like a flight safety review. It would answer that question for you, kind of after the fact. But yeah, it's going to come down to understanding if the system operates in an unsafe manner, how does that work? So if you have a canard control system that's only controlling roll and you only have a single degree of freedom, barring any crazy mechanical things, the failure case there is your rocket spins up really fast, which is a much more benign failure condition than surface-to-surface missile. So the more risk that you hold in your project, given a failure, the more safety needs to be included in it. But for an Airbrakes project, like, I don't know, the worst case scenario there is your rocket doesn't go as high, or it does. Like, it's not as bad. So you can prioritize achieving the objectives versus safety. Yeah.
So whenever I bring the topic of active control to the average person, the immediate question I get is, whoa, you're building a missile, is this legal? And per my understanding from forums and talking to people is that just stabilizing for a vertical flight, that's fine, but different people will tell me different things. A specific coordinate on the ground, that's illegal, or a specific coordinate in space. So, from your research, is there a definitive answer to this?
So the answer is it depends. Depending on your country specifically, it's a big one. So in the United States, the laws are relatively lax, and there's like layers to it. Not a lawyer, and I'm running out of time here for a detailed answer on that. The bottom line is understand what your country or what your like local's jurisdiction will allow, and don't make a weapon.
Like here in the U.S.
Yeah, here in the U.S., don't make a weapon.
Yeah.
Don't shoot a normal rocket at someone either, but don't make a weapon. And you're I don't know, pretty much good. That's not legal advice though. I think we've run out of time for questions. I appreciate everybody's time. I'm going to be hanging around, and I'll be out at the launch site. If anybody has anything else, they can find me there. Thanks.
You see me going like this?
Where are you gonna go to, Ethan?
How'd it go with the judge? You know where the water bottles were? This is the water bottles you can get. But like, it's like, you know, there's like a section of tables next to our table.
Yeah.
If you go like all the way down to the very bottom, there's a bunch of tables. Yeah, it's like really, yeah.
Oh,
it's
okay.
like-
It's just pretty.
Got this,
What do you got?
water bottle.
Oh, baby.
Nice water bottle.
Yeah, I gave her a number and she asked for
I think it's,
something.
I think it was,
I got this from SolidWorks.
So that
Oh,
we
you got
could
that
all
too, yeah.
use. But
I got a t-shirt.
I don't know, she didn't really like ask too many questions about it, so like,
Did you
I
note down what she was? Yeah,
Hey, yeah.
I got the origin. I got the on-sheet bag. I got all the rest. We weren't able to.
Ready, Carl? Yep. All right, everyone. It's the polite way of doing it. Thank you for being here. Thank you to the Ezra team for inviting me. It's my pleasure to show you my model rocket Eagle and the program I went through to make this happen. I run a very small YouTube channel called Project Horizon where I outline all of this, and it's my goal today to show everyone a little bit of everything so you have a top-down version and understanding of how the whole system goes together. So quick little bit about me. I am an engineer. Ironically, I'm a petroleum engineer, so I'm very familiar with Midland, and I've lived here in the man camps for a bit in 2020. I've transitioned more to a controls and systems engineer, largely in part because of projects like this, just kind of doing things like this, more up my alley of interest. But I still work in the energy industry. Subtle brag, I recently got married. As my wife up there, she comes to all of my launches, and as she is my biggest supporter and all that, so very happy to have her in my life. Now, as far as model rocketry goes, this is very important for me to mention. Joe Barnard of BPS Space inspired all of this. I am not Joe Barnard. I followed very closely in his footsteps on purpose. I learned what I could from him. I tried to do things a little differently, iterate on things where I could, but definitely want to voice that out of appreciation for what he's done for the community. And so I was inspired by him in 2021. It took me a year to even start thrust vector control launches, just learning all the prerequisite skills. I successfully ended a model rocket in 2023, which is where I started a YouTube channel to try to give back to the community a little bit, show my version of the problem, and then, of course, had to do high-powered rocketry at that point. And then, you know, it was nagging me a little bit that I thought my project could be done a little bit better, so in 2024 I tried again, and I was able to land Eagle a second time with a little bit of upgrades. So I like a good project objective. So for this project, design, build, and launch a model rocket powered by hobby-grade motors capable of autonomously landing upright using propulsive control. There's two parts to this, though, in my opinion. There is stable thrust vector control flight. You got to get that under your belt before you can move on to landing rockets. So this is a thrust vector control gimbal system. You need to have some simulations for that. And, of course, verify it with real flights. Only then should you move on to landing a model rocket. It's a few more steps. They're complicated, but if you have thrust vector control, it shouldn't be that much more difficult. So let's start with thrust vector control. This, of course, is changing the direction of thrust to control your vehicle. You're going to need a gimbal for this. You're going to need a little bit of control logic in the form of a PID controller, and that's all going to live on your flight controller. So here's my gimbal. We're going to articulate plus or minus 5 degrees in both axes. I use standard Bluebird servo motors. They're really small and really powerful. And then the motor is just friction fit into the bottom well right there. And then most of the plastic parts that you see, actually all the plastic parts on this rocket are PLA printed. If I were to do it again, most would be ASA, but this was a project in learning, so PLA worked actually pretty well for most things, but the gimbal is one of those things I would rather do in ASA because sometimes it gets a little heat intolerant. So let's talk about control theory. This is a generic PID controller, and essentially for a system you'll have some sort of set point. In this case, we could take the rocket's orientation. You'll pull that through a feedback loop, see how far deviated you are from your set point. You'll get your error from that, and then you'll apply that error across a proportional, integral, and derivative gain. These are constants. You'll take your I gain times your error times the integrated error over time, and then the D gain times the error times the derivative of error at that point. You sum those all up, you get a process variable that you control out, or you send off to like a gimbal or something, and then that's constantly feeding back into the system so that it stabilizes. In the form of this rocket, I use a torque out PID controller. So I have torque out specifically so that we can interact and use our moment arm, but mostly for our measured thrust. This is very important because thrust is variable throughout your flight. So it's going to be pretty high at first, likely, and then teeter off. And so by incorporating your measured thrust, you can then, and your moment arm, you can calculate the side force, and then you can use trigonometry to figure out where the servo angle should be, and that'll be shot off to the gimbal. So again, here's a flight profile of one of my rockets. The red and green lines are the orientation angles, pitch and yaw, and then the thrust is blue. So you can see at the beginning you have high thrust, so your control is higher, and then over time it peters off, so you have less control. Now, this was a PID controller where I did not incorporate thrust. Later on when I incorporated thrust, everything was a lot more controlled. So these are the two controllers. I have one per gimbal. You just have those output commands just go into each one of the servos, and that should control your system. But then we have the question, how do you determine these gains? And the reason, or the best way to do this, in my opinion, is to not go out and just lob the rocket off into the air. That's not safe or practical. Instead, you're going to want to build a simulation. And in this case, I built this in Simulink, or a MATLAB Simulink with a little bit of Simscape to show the 3D animations. But I incorporated real thrust data, the moment arm, so the length from the gimbal to the center of mass, moment of inertia, all that good stuff. And by building the simulation, I was able to then calculate or get the gains out. So you've thrown in different gain values and seeing how it flew. That's okay. There we go. So that's what the good simulation will look like. The one before was a little bit wobbly, but we'll roll with it. Go ahead, Carl. Try to go to the next slide. Yeah, you're good. And then one more. You're good. So all of that logic lives on the flight computer. This is my flight computer Mustang, the second iteration of Mustang. We don't talk about the first iteration, but it's a full SMD PCB designed around the Teensy 4.1 microcontroller. That is open source, so you can grab all of the files for that and make your own PCB from it. But this is programmed in Arduino C++. It's more powerful than I will ever need, but that's always good. And it's been active up until about a couple months ago where I redesigned it and have a smaller version, but it has been my workhorse for a few years now. The most important sensor we're going to talk about today is the BMI 088. This is the internal measurement unit, so it's got accelerometers and gyroscopes on it. And then I have other various things for like data logging, and then of course our control outputs for pyro channels, servo ports, LED, etc. So how do we calculate orientation? So there's two steps to this. For your initial orientation, you just want to use accelerometers. This is only for when the rocket's in a static position. Once it's launched, your vertical vector increases, and you don't want to calculate that way, as I've learned. So instead, you want to take your gyroscopic data, integrate that, apply it to quaternions, pull Euler angles out of that, and then you're going to apply those X and Y angles to your PID controllers, and then the flight computer should handle the rest. So if that all works well, I have a feeling since these are videos, it's, yeah, going to take a while to load. It should look like this. So that took about a year. It's really exciting when you do it right. It's not exciting when you do it wrong. But that's the first milestone. So let's talk about Eagle's components. Go ahead, the first one, Carl. Start simple. The nose cone's just hollow PLA, and then I use traditional 3-inch diameter by 1.5 main tubes with a coupler to keep them together. I have front and back run cams for footage on the front, as well as these dead weights to cover the access port and to weigh the rocket down. We'll talk about that a little bit later. Mustang's pretty low on the rocket, as you see here on the right. And then we have a foldable carbon fiber landing leg system that'll deploy. I put these dampening systems or damping systems on the top struts to take in the force on falling. That's another hard-learned system, or lesson that I learned. And we have a 2-motor motor stack. There are 2 Estes F15 motors coupled together. And then, of course, the gimbal we talked about earlier. So how do we light the motor twice? Well, we have 2 motors. And kind of the process this goes is we have our stacked motor, or 2 motors into the gimbal on the launch pad. The launch pad will light that. The rocket will ascend. We'll hit apogee, we'll come back down, the flight computer will send a command down to the gimbal, which will pop the landing motor, which will then hot stage it away, dropping it completely, leaving us with just our landing motor. It's another video inbound, yeah. So right about there, you'll see it fall away. Oop. It's foreshadowing. Let's go one more. I think we're good. No, you're good. We'll leave it here. So the landing legs are spring-loaded. We have a rubber band around the top to hold the legs back, and we have rubber bands that will pull down on each individual leg. And for this, I really wanted a wide base. In fact, I went as wide as I could with standard carbon fiber rods. Usually those come in 400 millimeter lengths. So the very bottom parts of the legs are the longest they can be, and the top are cut away a little bit with those damper systems added. And then it was important for me to have rounded feet on the system. I didn't want anything to bite into the ground, that I wanted it to kind of like sled or skip off best possible. So to deploy them, you can go ahead again. We use a nichrome wire, and that'll break and heat away at that rubber band up top. This is another video. That's okay. We'll all just assume it just broke away and came off. I am running a booth, by the way. I can show you all the physical, like real life example of all this, so come find me afterwards if you like. But now this is a little weird. As far as high-powered rocketry goes, I have the center of gravity below the center of pressure. So we have this rocket in reverse, and that's on purpose. As we go up, we can stabilize with thrust vector control, no problem. But on the way down, we don't have anything to control it. So we want to utilize those aerodynamics to pull the rocket back to vertical so that we're not wasting any energy on keeping it vertical. And so, again, that is why that is oriented the way it is. That's also why I put the dead weights down low. And additionally, I didn't want any airflow getting into the rocket, because I noticed when air goes into that access port on the side where the flight computer is, it'll start to spin. And I noticed that because it always spins the same direction and about at the same angular speed. So by putting the dead weights there, I was able to not only weigh down the rocket so it doesn't go up that high and flip out of control, but also to help keep that center of gravity low and to keep it from spinning. It's another video, but this is an important video, so everyone hang tight. So the most important question with this project is answering, when do you ignite that second motor? And the more I thought about it, the more I thought, well, the rocket more or less weighs the same as it's going up as it's going down, minus, of course, that jettisoned empty engine and the oh my gosh, the engine propulsion. So we can kind of let physics take over and trust that it'll get us pretty close to the ground. And the control system is the same because, again, the rocket pretty much weighs the same. So it's all about answering the question of when to ignite that second motor. So I went back to simulation and I added the physics behind all of that. So what I would do is, of course, I add the mass behind that, I add the mass changing, and then I put a second thrust curve in. And I figured if we can figure out when we're putting that thrust curve in, and then we backtrack that 0.3 seconds because that's the delay between command and when we start to see thrust come up, then we can use that point to figure out when to have the rocket ignite the second motor. But, go ahead. So the problem with that is you can't have a simulation for varying flights. I'm not going to get my nominal simulation every time in my flights. So here are 3 real flights I did, and you can see the apogees are vastly different. I can't throw in 22 meters as a landing burn altitude for all three of these, because by the time they get to 22 meters, they're going to have vastly different velocities down, and that's just going to ruin it. It took me about 15 launches to realize this, but I went ahead and I started thinking, okay, so I need a dynamic, this is a dynamic system. I need to represent that correctly in my flight software. So in the simulation, I started dropping the rocket instead of differing apogees. So this one's at like 27 meters, and I would drop it. I would see when to apply the thrust curve, and then of course backtrack that 0.3 seconds, record that value. And I would do this for different apogees, and you get this beautiful linear relationship between apogee and the landing burn command altitude. And it's a perfect relationship, and it's a very simple relationship. So once I put that in to the controller or the flight computer, everything started happening much nicely. But the last question we need to answer, of course, is, all right, well, how do we know where we're at? How do we know the altitude? And this is my barometric data. It's noisy and not great, but you can see a trend there. So what are we going to do instead? And instead, I'm just going to use dead reckonings. So in the form of, I'm finding my tilt angle, so the angle between the rocket and the ground plane. I then take the acceleration value that the flight computer is seeing directly above it. We'll call that the z acceleration. Apply some trigonometry to that, take off gravity, integrate that. Now we have our vertical velocity. Integrate that again. Now we have our position, and now we know where we're at, which, of course, looks much nicer. Okay, so now how do we program it? My flight computer is structured in a state machine. So the rocket has 6 distinctive different states, and each state is doing a different thing, and each state will have a different set of functions that it's all constantly looping through. We start on pad idle, and then we launch into power descent, coasting ascent, coasting descent, the landing burn, leg deployments involved in that, and then landed. So with microcontrollers, when you turn them on, or at least Arduino-style microcontrollers, you have a setup function that runs once. So this, in my case, was initialize devices, calibrate sensors, etc. And then you go to your main loop, which is this long if statement for a state machine. So if the state variable is 1, you're just doing pad idle functions and looping. If it's 2, you're doing power descent, etc., etc. Each state has a next state function. This is what land ignite is in my coasting descent. And this is arguably the most important state iteration function, because this is waiting for that landing burn altitude when the rocket's flying. When we get to that altitude, we ignite the landing motor, and then state equals state plus 1, and now we're in the landing burn. And that's when the control theory starts up again, and that thrust vector control starts going to keep it vertical. And if you do everything right, you should get this. All right. Oh, thank you. That was 2.5 years of development and emotion just coming out all at once right there. But something was nagging me. That same day, these are 2 other launches, before and after, and these are not that bad, but they don't land. And it was driving me nuts. So I went back to some earlier footage, and I realized my leg design was horrible. It was a rigid body. They bounce, they don't do much for me. And the only reason I actually landed is because one of the legs didn't lock out, and it landed on that leg. So it was like an artificial damp leg, and it landed. So I tried to learn from that. And instead, I added that compressible damper on the top. And you can see in the top right animation there, it compresses and it locks. It's like a ratcheting design system, and it would cause me to manually reset it after every flight. So obviously, that's way better. And I really think this is the key to this type of project. You can only get so accurate with hobby grade motors. And there's a bunch of other variables that you can't always control around. Your motors have a finite amount of energy to them. They're not throttleable. I know BPS Space does some really cool things with throttleable, but you can only throttle down. So my solution was get the control system working good enough, and then to lean upon my legs to finish that out. And this is a chart that I made. It's flight attempts on the x-axis, and we got hover height on the y-axis. And what I mean by that is when the rocket comes down and it starts to hover, whatever that drop distance is. And to me, this is like an accuracy chart. And you can see over time how it got pretty good. And this is in meters. So 1.4 meters down to 0.4 meters up to 1.5, 1.6. That's all within the realm of plausibility for a cardboard rocket this size. So again, that's why I decided to go this route. And I actually didn't even touch my system or my flight software that much at all after I redesigned the legs. And so this is the last flight. Yeah, and there we go. Thank you. So, Eagle landed again. The dirt is fine. Don't worry about the dirt. I get that comment a lot, which is kind of bizarre. But yeah, the legs, they didn't really need to use the legs that time. One of the legs compressed a little bit, but I like to think it worked and helped out the cause. So I really hope you all learned something today. I know I didn't go quite into the specifics of every subsystem, but again, my goal was for you to leave this room and knowing kind of top down how my whole rocket worked and all the subsystems required to do that. So yeah, open the questions when you got them.
I'm running into this as I'm graduating, that we get tens of thousands of dollars of licenses freely provided by our school. What do you do when you use them?
You pay for them.
So you paid for Simulink and not there?
I did. I have a private license, the non-commercial license. If MATLAB's listening, it's just me. I'm not making money off of this, so I think it still qualifies. But you know, the cool thing at least about Simulink, as I understand it, when you buy your license, you buy that year's version, and then you're good. If you want the newer years, that's when you buy those perpetual license, but I think you got to pay every year to like update it. But I have like a 2022 license, and it's still kicking just fine. I do spend like $400 a year on my Fusion 360 and Eagle licenses. Not so bad, but it'd be nice if everything was free. I get you. Yep.
I see in most of your flights that after the rocket reaches like the hover height, it kind of goes up again after that. Did you put in any sort of like safety factor there so it doesn't come down too hard, or like why did you adjust it to burn that second motor earlier so then it goes, you know?
All right, two-part answer. Second part is because it's not perfect. So, and it's actually a really fun physics question because, like I was saying before, your rocket, when it goes up, is losing mass in the form, again, of the, oh my gosh, someone help me with the word, the propellant. That's what I was looking for earlier. So you lose propellant on both sides of the equation plus the expended motor. So your rocket on the way down weighs a little bit less. Now, in a perfect situation, I saw this in my flight simulations, you go up, you go down, and you'll come up a little bit. And that's, you know, I see that second hump as the excess energy you have landing. Now, you can start to do some fancy stuff with that, like maybe, you know, moving the motor to deal with it. I never did anything for it specifically because I figured, okay, if the rocket's not vertical, we can pull from that. And at worst, you just come up a little bit and land. It doesn't come up too much, and again, that's why I was leaning on my legs. But I appreciate you bringing up safety too. It's something I forgot to mention. This is an experimental rocket. There are, in every state, some sort of safety condition we must hit before we can proceed. One of the most important ones is when we're falling, you know, it's looking for that landing burn altitude. But like, let's say I knock the rocket over, and somehow we stage into coasting descent. It actually checks to make sure it's above a safety height. And if it's above a safety height, it assumes, all right, I'm in the air, light the motor. If not, it not only doesn't light the motor, it disarms the entire vehicle and it throws it to the last state where it's blocked. It can't go anywhere else. So, hope that answered your question.
Do you have a specific sequence for calibrating the IREC?
Yes. God, it's been years since I've looked at that. The gyroscopes do have a drift correction factor to it. And if memory serves, I think I sum up the values over like 2 or 3 seconds. And I see how much they deviated per time, and then I have that variable that I apply later when I pull those values.
Is that just every time it turns on, or do you just...
Yes, every time it turns on. Another thing that's interesting too, one of the initial minor issues I was dealing with is that the BMI 088 default setting for the acceleration values is plus or minus 24 Gs, which is, cool, whatever. But if you're integrating to find your position and you need to be really accurate, you want to pull that range down so your bit resolution is a lot higher. So that was, I learned that 10 flights in, and then I pulled that down to plus or minus 3, and that, oh God, things changed like immediately. Follow up?
Yeah, did you ever add those to your cell, like time mechanical?
Oh, to the simulation?
Yeah, in simulation.
No, that would be really cool. In fact, I've started doing some hardware in the loop testing for work, and I kind of want to see if I can connect this to like a digital twin model, and then like simulate. Yeah, I have my simulation, offline simulation for everything, but I could like actually watch this interact with the simulation and see how that goes too.
If you decide to scale up the motors and the actuation plant can't deal with the thrust of the motor, have you thought about what you would do if your center of gravity, or if your center of gravity wasn't below your center of gravity?
That's a cool question. I think if your control system is good enough, it shouldn't allow it to get to that point where it's, the vehicle is changed in such a way to where air is hitting it to like pull it. That's cool. I like that. One thing we kind of skipped over. Sorry about that, Carl. I think we jumped a couple slides. You're totally fine. The limiting factor behind this rocket currently is the fact that you have to use black powder motors, at least for the landing burn, because black powder motors light immediately when you tell them to. And of course, that's important for the accuracy of the landing. Now, I have played around with the idea of putting a larger motor to really throw it up there, and I want to simulate what terminal velocity looks like with this, maybe put some fins on it to keep it vertical, because whenever you hit terminal velocity, you can go as high as you want, because you're always going to hit that velocity, and I think the landing burn altitude for that, it's always going to be the same at whatever terminal velocity. So there's some workarounds to it for sure. Maybe I need to go talk to Estes to get like a longer burn black powder motor. Maybe there's a market for it now, but we're just trying to use what we can, of course.
So those others, when it's trying to land like above the ground, instead of like slamming into the ground first.
Yes.
Have you like purposely tried to get it to up here?
Yes, I have. When I redesigned the legs, I took 2 tries to land it, and that's significant and funny to me because the first try, I thought, man, I want to make this thing hit the ground. I really want to see those legs working. And so I took that linear equation for landing burn altitude and I added a 0.25 offset below to it, which is apparently a lot. And so it hit the ground, in one of these clips hard, did not do what I thought it would, sprung up because, it's still under power, and don't do that. So you want to drop it, is my point. Oh yeah.
How did you find that your simulation aligned with your flight data, and did you find the PID values that you had in simulating work really well for your actual flights?
Yes. The simulation, one of my big milestones was making the simulation actually match the flights. I could do a whole presentation on the small parts about that, but I will tell you specifically, in my simulation there is a PID update frequency that I didn't have matched with my control loop frequency. And man, once those were together, not only did my rockets fly a lot better, but I was starting to take the flight data and throw it against my simulations. And it's not perfect apples to apples, but you could start to see like really similar orientation values from it. And some of my really bad values from early on, I would put into the simulation. And then all of a sudden, oh wow, the simulation looks horrible like that flight. And okay, so I guess it kind of does match up. So I'm really big on simulation. It'll save you a lot of money, but your simulation is only as good as the effort you put into it. So that's the caveat. But they're really powerful tools.
So frail, and I blocked.
Hey Mike, how are you?
Yeah.
Started asking questions about simulation of
Okay, all right. What that is last session. Okay, so you might want to tell them, or I'll tell them. We could out there at
I got them started. Whole 20 minutes for presentation and 5 minutes for Q&A. Yes, I did tell them that. Yeah, I was making sure that they're doing good over here.
Well, maybe you should. He was saying.
Good to go? All right, hi everyone. My name is Patrick Bellamy. I'm from the University of Melbourne, and I'm here to present about lightweight neural compression of pre-computed flight configurations for model-based apogee control systems in high-powered rockets. A bit of a mouthful. Let's get into it. So, as I'm sure you all know, the goal of the competition we are at, amongst many other things, is to achieve an exact apogee. Our team is competing in the 30K COTS category, so we're purchasing a commercial solid motor, and the goal is to get to exactly 30,000 feet. We encounter a few issues with our control surfaces. those being the irreversible dissipation of our kinetic energy. Once we deploy our air brakes, if we over deploy them, there's no way to regain that kinetic energy we've lost. We have no ability to turn our motors back on. We've also got a lot of uncertainty in our environments, modeling the temperature lapse rates, pressure changes, pressure on the day when we're not sure what time we're going to be launching at can actually get pretty difficult. There's a lot of uncertainty there. We also see, variation in the thrust profile of some of the motors we buy. Particularly, we had a bit of an incident, which I'll talk about later, with some of our test launches this cycle. Also things like the launch angle in our rails just not being consistent. So traditional control systems, seem to be a pretty obvious first step into designing your control surfaces, from, I guess, a back-end perspective. But they do have their drawbacks. In your more nonlinear or coupled systems, things like PID controllers can kind of fall apart. They're a lot harder to use in those situations. Tuning those systems can also be really difficult. I actually don't come from an engineering background, so trying to pick those sorts of things up didn't really make sense to me, so it led to the monstrosity I will present now. And there are hardware constraints. We fly microcontrollers on board our rocket. You can only do so much with them, given heat or energy or just the compute power or memory available to you. And even with a really well-tuned classical controller, maybe on a massive rocket with lots of compute power, you can always have more compute power on the ground using, high-powered computing applications. So what this allows us to do is generate lookup tables. If I can, have a super high fidelity simulation model, which I run on the ground, I can pre-compute every possible flight configuration that I might expect my rocket to see. So this is kind of a demo of what one of those might look like. This is a relatively small one. I think it's got 28 million rows. So it's got your current altitude, a forward velocity, a pitch, yaw, and roll angle, and your resulting predicted apogee, given some initial environmental conditions. But there's some issues with this. So there's an example situation here where maybe we're only going to deploy our air brakes between 5,000 and 10,000 meters, at velocities in the x, y, and z direction of 0 to 200 meters per second, highly unrealistic. Extensions, 0 to 100%, roll, pitch, and yaw throughout, 360 degrees of motion. Obviously, these ranges are way bigger than we would expect, and we could optimize them. I could decay my velocities as a function of my altitude, maybe. I'd be going slower at higher altitudes. But also, a key thing to note is I've got a step size there. Lookup tables are tables. They're discrete. And yeah, this kind of introduces a few problems. But a big one is that it's a lot of data. So for that scenario that I just showed you guys, if I were to represent every single value in my lookup table as a 16-bit integer, I would need 334 exabytes of data. That is about 1/600th of the entire world's estimated data storage capability. And it would be as though you downloaded every video ever uploaded to YouTube 10,000 times. In other words, it's a lot of data. So yeah, and that's a fairly limited state space. We're integer rounding our inputs. You can imagine if we were instead rounding to, the 100th place, 1000th place, it would just get insane. So, the obvious next step with a file that is too big is to maybe find a way to compress it. Now, in my eyes, the compression of files is simply a trade-off between, the accuracy of the data you're storing and how big or how expensive it is to kind of query that data. So on our first pass, Serpentine is the launch site we test at over in Australia. We generated some lookup tables with vertical velocities on our y-axis and altitudes in meters on our x-axis, and using a 6 degree of freedom simulation model, determined what extension we would have to apply to our air brakes in order to achieve our desired apogee. Now, there's something off with that graph, and this is kind of a bias that was revealed in our simulation tool, but there's not a lot of those intermittent colors appearing. We decided to use this to our advantage and employed a bang-bang controller, instead kind of compressing it down using a polynomial, and then kind of tracked what stage in flight we were in. If we were, I guess, below the polynomial, we would not want to deploy our air brakes, so they would retract. If we were above the polynomial at any point, for a given x value, then we would fully deploy our air brakes. And you kind of dance along this line. But the issue is, if at any point you've kind of misrepresented the authority of your air brakes, you're destined to undershoot, and there's no way for you to repair that. So moving forward into the next year, we realized we needed a lot more data than simply a forward velocity and an altitude. So sticking to the whole regression of a line thing, obvious next step was maybe to do a planar regression. And then what comes after that? It's a thing called a hyperplanar regression, which sounds way cooler than it is. It's just a plane in a couple more dimensions. So that's kind of what we attempted to apply. The issue we ran into there is that trying to apply a plane to such a complex system is inherently super difficult. Regressions of lines can already get pretty hard. Regressions of planes, trying to fit such vast sets of data, definitely doesn't go very well. And trying to do a plane in 10, 11, 12 dimensions and have that single plane fit your data doesn't really work out. So instead, we thought maybe let's produce a bunch of little planes to, I guess, represent different areas. But what ends up happening is you slowly make smaller and smaller planes until each of them is just like a single data point, and you're back at the lookup table. So it didn't really work out. Now, as I mentioned, I don't really come from an engineering background, at least in my studies. And I'm a bit of a computer science guy. So one thing I thought of was maybe using a neural network to compress the data. So a neural network, it's a bit of a buzzword, AI is a big thing nowadays. And it is a computational model inspired by the brain, which we use to approximate functions and patterns. So it will map, some inputs that you feed to it to outputs through a bunch of different layers, essentially. Now, they act as function approximators, so their goal is to take an existing function, some mathematical system, and to approximate it to the best of their ability. Instead of being manually programmed, it adjusts its kind of internal weightings by comparing the outputs to the correct answers during training. So how that works is you will essentially feed data into the neural network. It will pass through each of those layers. And at the end, it'll calculate kind of an error in that prediction. So maybe my lookup table says I have an apogee of 1,000 meters, and my neural network says 995. And then you do a thing called backpropagation, where you move backward through the neural network, find out how much each layer contributed to that error, and then update the weights to reduce the error in the next run. And what this results in is, the more data you feed it, the better optimized it is to your situation. There is a thing called overfitting, where you kind of feed it data specific to one scenario, and it's really good at that and terrible at everything else. So it's important to feed it the right data. So how does this apply to a rocket? So because a neural network can kind of generalize beyond exact matches, it's really useful compared to a lookup table, which was discretized. If I had a point that was maybe something 0.5 between my 1 meter per second, 2 meter per second, it would be able to kind of generalize between the two of them. It can also learn to map the same input to an output using far less memory, so it's also less computationally expensive. And really interestingly, they are actually mathematically proven to be universal approximators, meaning that with enough neurons and layers, a neural network can approximate any continuous function, which I just think is really cool. So, of course, I do have to talk a little bit about engineering. We've got a pretty simple overarching control architecture powering our air brakes. So we've got kind of two layers. with an inner loop that performs a thing called a binary search using the neural network to find our desired Airbrake extension. What that means is trying a 50% extension, checking what our apogee is. If it's too high, we'll then try a 75% extension. If that's too low, then you'd go like 66%, and it would kind of do this halving behavior until you find the exact extension you need. And as I mentioned before, you get this dissipation of kinetic energy that's irreversible. So the way we tackle that is with this outer loop, which actually dynamically chooses a target apogee. Rather than setting our desired apogee as 30,000 feet constantly, it's actually a function of our current altitude, where we converge to a desired apogee of 30,000 feet at 30,000 feet. So you're kind of, so the way we do that is determine this envelope, through simulation, lots of essentially determining your authority by fully deploying your air brakes at each point and how much can I reduce my apogee by, and making sure you remain within that range, but not, over deploying your air brakes such that you get this irreversible dissipation of kinetic energy. It narrows kind of as you progress. This represents that we have much more authority at earlier stages of deployment. The air is thicker, and we're going faster, so that means more drag. I think I got that right. So where I see this going next is a further generalization of these neural networks. Right now, what we do is kind of generate a bunch of them based on varying weather conditions. But the dream is to really have one that represents a single rocket across really any environment you plan to launch it in. The way I can see this working is to use kind of derivatives of those state variables, things like your acceleration. If I have a rocket who is moving at the same speed as another one, also at the same angle, yet their accelerations vary, there is likely an environmental reason powering that, and kind of the fusion of all of those different derivatives can inform some guesses about the environmental conditions the rocket is in. So I think that'll allow us to generate a generalized network for a single rocket that we can then happily launch in any weather conditions, and I don't have to sit at home looking at the weather all day. Next. Yeah. So how do we validate the system? First one is through test flights. So the team, this project cycle, conducted 4 test flights prior to coming here for competition, all of which were done on M-class motors across 2 different test rockets. Both of them flew the exact same Airbrake setup, but slightly different back ends each time. So I'll call the first one Flight 0, where we ran a stepper function, where after the rocket ended, past its lockout protection period, the air brakes deployed at 10% increments out and in. This allowed us to kind of gauge our authority, validate that the authorities we were simulating were also representative of what was actually happening. Our next flight was then quite a bit later in the year. At this point, we had kind of a first pass at the system working. Unfortunately, that rocket ended up undershooting, and as such, the air brakes didn't come out. They behaved as expected, but yeah, they just didn't deploy. After that, we flew another rocket, which unfortunately, I was talking about before, inconsistent thrust profiles in the motors. It massively undershot by about 1,000 meters. We think it might have been because we left the grains to dry outside in the cold for a little too long. But as a result, also undershot, but also didn't deploy. So it's got a pretty good track record so far. And finally, we test launched that same rocket. And the motor did not underperform, but unfortunately kind of the central CAN bus, which runs through our rocket connecting the avionics bay to the air brakes bay, disconnected during acceleration, so the air brakes did not deploy. Now, what we could do with that data though was retrospectively pass it through our Hootle system. So that is hardware out of the loop, where we kind of pass through the flight data to the now connected CAN bus as sensor data, and saw that the air brakes indeed did deploy as expected in order to control the apogee. Now, I've got a graph here of kind of the system's predicted apogee as a function of its flight time. So you can see that green line along the top is where we predict our apogee will end up throughout the entire flight. You can see there's some slight noise or variation as we proceed, but it's relatively accurate, and we see us converging to kind of our exact predicted apogee. And that is us last night, yesterday, maybe 2 days ago, in our hotel, doing a little testing of the air brakes. Now, we also do some software testing with them. My software friends in the room will be very familiar with Monte Carlo simulations. We vary kind of all expected parameters of the rocket within some expected range. So whether it be, wind speeds, thrust profiles of the motors, launch rail issues, everything we can think of, how can we vary them in order to represent, all possible scenarios this rocket might be launching in. So you can see that results in a whole lot of simulations, and you can see we're able to gauge whether or not, in certain conditions they will overshoot, undershoot, in such a manner that the air brakes can't help it, or they'll get within some target band. So what's next? I think the obvious next step is to kind of employ an FPGA in the system. Right now, we run it on an RP2040, which does the job, but FPGAs are kind of custom built for this matrix multiplication sort of thing, and would allow us to kind of query the network with like nanosecond speeds, which is super awesome. I also kind of see applications in really anywhere where a model-based controls are employed. There's also interesting applications in sensor fusion. I've seen a bit of research on quantized neural networks, which kind of have these discrete inputs and are compressed as small as possible for applications on your edge computing cases in like drones, and they use those and their common filters to kind of filter sensor inputs. Finally, in the aerospace world, there's plenty of model-based control applications. There's lots of boost back applications in your model-based control. They'll fly like a 6 degree of freedom simulator on board, and that's responsible for, I guess, optimizing some cost function, whether it be saving fuel or landing fast or something like that. And maybe taking the ability to simulate the rocket's flight off of the rocket and pre-computing it is maybe another application of the technology. Yeah, I talked way too fast, but I'm done. Anyone have any questions? Yeah.
With the neural network, like, how large does it take up a lot of space in RAM?
Yeah. So it was really interesting. On one of our test flights, we unfortunately weren't able to train the neural network in time, so we attempted to do a lookup table equivalent. All our flight code's written in C++, so we decided to use a map where we'd kind of map vectors of all of our possible input states to some apogee or airbrake extension. And that required, of course, we discretize all of our sensor readings. But what we also found out was that maps were not great given our really, really tight memory constraints. And we could really only store like 4,000 rows of a lookup table. Whereas our neural network, which the most recent one compresses, it's about 100 million rows of data, takes up, I think it's Marcus can check me on this, 0.04% of our memory. Yeah. Yeah, considerably smaller. Yeah, it's probably smaller than like a map with like 5 entries. Yeah, it's just a couple of C++ vectors which hold like 16-bit floats. Yeah, just the weights. Yeah.
What sort of like inputs are you putting into the neural net? Like, what's the most important that you found to like keep accurate or something like that?
Yeah, it's really funny. We've actually found that once you go beyond your kind of current altitude and forward velocity, there's not a lot of gain in the accuracy of it. The neural network does a really good job of, I guess, kind of making assumptions in how these states will propagate, such that, you know, whether I'm moving forward, you know, perfectly vertically or kind of like this, because I then query it again in 100 milliseconds, I'll kind of correct for any error in the difference in angles. So definitely those two are needed, but everything else is, yeah, just kind of a treat. Yeah.
You said you computed different models for different like weather conditions as well?
Yeah.
Is that something that would go into a future model, like trying to account for that? Or
Yeah.
And what effects does the weather, like, how does it change it really?
Yeah, so I guess to answer your second question first, the weather plays, you know, a few roles. You know, high wind speeds obviously affect stability, which is not the goal of this system, but I believe the next talk is on canards for, you know, stabilization of your rocket, so there's certainly applications there. In terms of things like air pressure, you know, we see throughout the day launching the same rocket, you get vastly different apogees, simply because, you know, it might be colder in the morning, hotter in the afternoon, maybe, you know, your humidity is different. Actually, kind of a thing we're seeing this year with our rocket in simulating it is that it goes to pretty much the same height as last year's rocket, even though it is easily more aerodynamic and is about 1 kilogram lighter, simply because, you know, spaceport is about 600 meters higher than we are here. So yeah, things like that. But you know, being able to fly a system that worked at spaceport works, you know, here or back home where we're launching at about 180 meters of elevation is, yeah, really useful.
Which neural network architecture?
TensorFlow. Yeah.
Have you guys considered like physics for neural networks?
Yeah, I think that's you know, pretty obvious next step, especially in terms of, you know, what I was talking about in terms of, you know, the using those I guess derivatives of your state values to inform like environmental assumptions. A physics-based neural network definitely sounds like the next move. Yep.
So what are your goals for this competition with the neural net?
So obviously, goal is to get to exactly 30,000 feet with the neural network. Kind of the overarching design philosophy of this year's rocket was to build one that would overshoot in any expected weather conditions, but only, you know, within some range that our air brakes could control. So the goal is to kind of, you know, fly the same rocket on any day, given, you know, whether it's rained the night before or it's a particularly hot day, and be confident that we can get to exactly 30,000 feet.
Do you use output values like as re-inputs, as in does your current air brake position affect your apogee predictions, and are you assuming that you'll stay at the current air brake extension for those predictions, or go to 0, or what?
Yeah, so the way the model works, I guess, is I think the best visualization of this might be, Ben, if you go back to the one with the serpentine lookup table. Yeah, so you can see on that serpentine lookup table, we've got kind of a current velocity and a current altitude, and then kind of an optimum extension to get to our desired apogee. And you can see it's a single extension, right? So the implication there is that you will deploy to that extension and remain there until apogee. So yeah, and that is kind of the bias that resulted in that bang-bang behavior. Whereas now, kind of, if you can go to this one, Ben, please. Thank you. You can see, with this kind of outer loop, we're feeding through our states back to that guidance controller, and that's informing kind of our new target apogees each time.
I think that's time.
Awesome. Yeah, thanks everyone.
Let's go deliberate.
Sounds good.
Start, stop, 25 minutes. 20 minutes.
You guys ready?
Yeah.
You have a laptop?
Yeah.
Are you guys ready to go?
Yeah.
Okay, great. Just letting you know, it's 20 minutes for the presentation and then 5 minutes for questions.
Okay.
So whenever you're ready.
Okay. It doesn't work, man. Okay. Okay. I'm Lorenzo and I'm Simone, and we will talk for Sapiens Rocket team, and we were talking about our 6 degree of freedom simulator that we developed for this IREC competition. So we need to. We developed this simulator because we need to test software and to describe the rocket flight with proper tools that we didn't find on open source simulators such as OpenRocket and Rosaero, and so we developed this simulator with different features like Monte Carlo analysis or closed loop simulations that can test our subsystem of the subsystem of our rocket. We developed this simulator in MATLAB and Simulink
because it's possible with Simulink to have describe some part of the simulation, because I have different blocks already implemented to the software. So here our best practices. We want to at first to have a modularity for our simulator. In fact, we want to we have different configuration for our simulator. The first one is the standard configuration. That's a nominal flight simulation for our rocket. And the second one is the model in the loop simulation, in which we test all the software of our avionics, and mainly we test also the control system, and then we have done an hardware in the loop simulation. This is the base, the standard configuration of our 6th degree of freedom. The first one we will describe is the environment. The environment calculate all the parameters of all the atmospheric parameters and wind parameters, and it gives to dynamic model and an ideal controller. The dynamic model will solve the differential equation and with these parameters, and gives in output the rocket state, and the rocket and with the updated state of the rocket, we recompute all the environmental parameters. And we will do an ideal control. It's an ideal control because we don't use the parameter of the field thread from the sensors, but we use the actual state of the rocket. And with the controller, we just update the dynamics, the equations. So this is the dynamic model with different blocks. We decided to use a Runge-Kutta fourth order solver, and we decided to use an internal state machine only for the simulator, because it's easier to to switch the differential equation that they depends on the flight phase. For example, in the ramp we should have 1 degree of freedom because we have the ramp, and in the shunt we will less a degree of freedom, and it transform on 5 degree of freedom. So all the blocks calculates the forces, and this is the equation, the vectorial equation we have used, the vectorial form of the equation we have used. The first one is for the forces and the axial forces, and referred in the body reference frame. And the second one is the Euler law with for a variable mass system, and we put in also this empty. Empty is the moment due to the misalignment of the motor, and then we have all the different forces and momentum, but that are the common ones. So here is the aerodynamic modelization. That it's the core of the simulation, because because it's hard to describe a proper aerodynamic model. So we decided to linearize some coefficient, some aerodynamic coefficient. The first three are the aerodynamic force coefficient, and the second ones are the aerodynamic moment coefficient. And we decided to describe it from two angles, and that are the total angle of attack and the roll aerodynamic angle. Yeah. In fact, we can see that here, this is the total angle of attack, that is the angle between the relative velocity and the x-axis of the rocket, and the roll aerodynamic angle that's represented by phi. It's the angle between alpha plane and the other perpendicular plane. So, I was saying that we decided to, at first, linearize the equation, mainly the coefficient moment with the angular velocity that are represented with P, Q, and R. And we have a base term that's pointed with 0, CL0, CM0, and CN0, and a different part that are CLP, CMQ, and CNR, that are the damping moment coefficient. To CMN and CN, we added other two terms, another terms that represent the shifting of the center of the mass due to the rocket burn. So for the force coefficient, we linearize only the Airbrake extension described with the letter U, because in our rocket we have Airbrake control, altitude control, so we describe it with our linearization. So we got a problem because with our computational efficiency, all the CFD takes a long time. For example, for we have some calculation, and we takes to do a proper the aerodynamic database. It takes about 39 years, and it's not available. So we decided to solve this problem. We have decided to represent some coefficients, such as the aerodynamic roll angle and Reynolds number with analytical forms. And that reduced a lot all the different computation, all the time. And now to generate a database, it takes to us about a month or 2 or 3 weeks. It depends on the simulations. So for the environmental block, we decided to focus on the gravity acceleration, to describe gravity acceleration. In fact, there are 2 main terms. The first one is a base term that's compute with a spherical harmonics model, and then we added the centrifugal forces of the Earth due to its rotation. And for the all the atmospherical parameters, we have decided to use an ESA-based atmosphere, but we upgraded it with some features. In fact, we wanted to we changed some parameters in base of the humidity of the air. And for example, the lapse rate constant that describe the temperature, and the Sutherland constant that describe the dynamic viscosity of the air. Another problem we got is the consistency of our simulator, because we noticed that the solution depends a lot on the time step of the simulation. We have shown the graphics on angle of attack of the same simulation, but with different time step. With 0.02 second time step, we have a simulation that have no physical meaning, but the trajectory that we've never shown, it seems real. So we decided to decrease the time step to 0.001. That's the one of the time steps that convert to a solution with the smallest time step. We didn't use a smaller time step because it takes more time to do a simulation, but for advanced closed-loop simulation, we sometimes use smaller time step to fit all the sensor frequencies, because with the simulation of the every sensor in the rocket, we need a small time step. This is one of our two simulation. The blue one represents a simulation without Airbrake control of our rocket here, and the red one represents the simulation with an opening of the Airbrake at 50% in the coasting phase. We've also tested our simulator with a real flight, and all the simulation data fits almost perfectly the data flights.
So, this is our model in the loop, very useful to test the software like the Kalman filter that we also implement in our rocket. So let's start from the dynamic system that takes and gives to the environment to update like Lorenzo explained before. Now, all the dynamic parameters are given to the sensor simulation that adds all the error and noises that the sensor senses and that the sensor create. Then this sensor data is given to the Kalman filter, and then the Kalman filter computes the state of the rocket that then is passed to the controller that gives out the aperture of the Airbrake. Then this aperture is given to the servo actuator that mimics the delay between the command and the aperture of the Airbrake, that then is given to the dynamic system that reevaluates all the dynamic parameters. So here is how we model the errors of the sensor, and there are some specific features to some sensor. For example, the barometer noise that increases as velocity rises, or the softened iron magnetometer noise. But in general, we can describe a lot of sensor with this model right here. So the input that is given by the dynamic model, that it's the real value, it goes to scale and factor misalignment, that is very common on all sensors. But then other noise are added. For example, the random walk if the measurement is integrated, or constant bias, thermal bias, that is another bias added that change respect to the temperature. We also add the bias instability, so a small bias that change with time and that is stochastic. And in the end, white noise that is always present in sensor measurement. Then after all this, we also apply a thermal scaling factor. We also add false, but with false in our simulator is mostly outliers. And then after all of this, we apply quantization and saturation to perfectly mimic how the sensor works. So here is an example of our control system. To work, it needs some parameters that are given before. For example, the aerodynamic force calculated from the CFD, the angular velocity of the servo, and the CAM Airbrake friction modelization. Here you can see a graph that it's a simulated trajectory using Airbrake. As you can see in the dotted lines, there are two reference trajectory that states how much the Airbrake will open. So let's say that my rocket, I confront the vertical velocity respect to the altitude, and if my rocket is below the lower reference trajectory, then the Airbrake will be closed. If I'm above the upper trajectory, the Airbrake will be fully opened. And if I am in the middle, that is the most important part, then the Airbrake aperture will be linearized respect to the difference of the two reference trajectory. As you can see in this example trajectory, that is the one with the triangles, we are in the middle, so the percentage that is done with the yellow line tends to change and to adjust to maintain the middle ground between the two reference trajectory. That is the desired output. So, thanks. Now, the hardware in the loop. Bridge the gap between simulated model and real hardware. For me, hardware in the loop is a really important part of a simulator, and is the part that lets you test the hardware and the software like a final test for your avionics. How it is done? We just connect our board to the simulator. And you can see this in this simple graph. The simulation gives out the sensor data to the avionics, and then the avionics gives to the simulation the state estimate, and also the Airbrake aperture and the control parameters. Of course, with state estimate, I mean the state estimated by the Kalman filter. So, next slide. Before this, no, can you go before?
I'll give you one more minute and then we have to move on.
That is the, we are finished. Okay, so how we communicate with the simulator. We use packet. This is how they're structured, and you can see that we always have an header and a terminator for both. In the one given by the simulation, there are the sensors we have in our avionics, and we also have a checksum to check for data corruption. Instead, the one that the simulator receive are the controls, so the Airbrake extension, also the pyro signal, the state machine, and also the checksum. So, some last acknowledgement for the hardware in the loop. The most important thing is that the avionics should be completely agnostic whether the sensor data originates from actual hardware or simulation. So the avionics shouldn't really know that is being in a simulation. The software should be the same because we want to test everything. We want to test the hardware and the software. And actually, this is the only way to test if everything works before the flight without doing a flight. And to do this successfully, the avionics shouldn't know that is being that the sensors are given by a simulation. So thank you all for your patience and everything. These are our contacts. Also, thanks to Lorenzo, and this is all. Questions. Sorry.
Did you do any tuning?
For the... No, we didn't tune the hardware in the loop, but we tune a lot the general simulation for all the coefficient and parameters relative to our rocket. Maybe Lorenzo can say more.
Not too much.
Yeah, but
what if you have more specific?
Yeah, specific.
More for our Airbrakes. If you can, we have made these two reference trajectory, and the problem of this type of control is that when you have low vertical velocity, the two trajectory are the same. So the linearization is the airbrakes make a lot of noise, and we just put a filter based on the Kalman variance of the IREC of each sensor to decrease this noise. But this is just the only tune we have done. For the sensor simulation, all the parameters of the sensor simulations we have found by calibration procedures, and data sheet.
Any other question?
Yeah, maybe you explained it before, and I'm sorry if you
No.
but why did you, did the spherical harmonics and gravitational model make any difference on your simulation? Because it seems it was really computation intensive to, use the spherical harmonics.
Ti ha chiesto se la discretizzazione funzionava bene.
Can you repeat the first part?
I've seen there was the spherical harmonics in gravitational model.
Yeah.
Right? And does this have any effect on the precision?
Yes, because we are from Italy, and here there are a different acceleration, or gravity acceleration, but here there are not totally different. We are talking about 0.02 meters per second square, but our idea is to find the best to find the best parameters for everything to recreate the flight on a software. So there are some difference on the gravitational model. So yeah.
All right. Thank you, gentlemen.
If you have any question, we are outside. And
Andiamo a mangiare. Si mangia.
we close the door? Or?
Is it on?
We close the door?
Yeah.
Sure.
I don't know. I don't know.
Are we supposed to keep it in the stand or?
I think we're supposed to keep it in this stand, or do we want to pass it?
I don't know.
Here, we can. Never mind, we'll keep it in the stand, I guess. Okay. All right. Good afternoon. So we're Duke Aero from Duke University, and today we'd just like to talk to you about our next step in trying to attain full in-flight control systems, which in this case, at this iteration, is we're introducing active roll stabilization using canard control surfaces. I'm Connor.
I'm Jack.
I'm Megan.
And I'm Graham.
And we're excited to walk you through our journey with this project today. So first off, the question is, why do we want to do roll stabilization? Now, our team has been doing active control systems for 3 years on our rocket. 3 years ago, we started doing our variable drag Airbrake system. And with that, we were doing apogee control. Now that we've been able to deploy that on several different rockets at several different iterations, we've gained a lot of experience in the area and decided that this year it was time to take that one step further. So, roll stabilization. Now the question is, why do we actually even want to do roll stabilization? I know a lot of times people like to talk about the fact that you might get, gyroscopic stability from your roll that might help your rocket generally have better performance. And as far as we've been able to tell, and generally is the commonly accepted thought, is that most typical rolls that you're going to achieve are actually not sufficiently high enough to gain notable gyroscopic stability. And especially once you add fins into a rocket, that can be even more detrimental. And when you consider that against the cases where you have additional loads placed on your airframe from gyration and things of that nature, we find that roll stabilization tends to be better. Here's an example of our launch from a few years ago, and you can see, wouldn't that be a much cooler video if we were looking at a more solid background and we had roll stabilization. So now that we're doing that, the question is, how are we going to do that? Initially, we had two primary mechanical systems that we were looking at. So canards, which we ended up doing, and then also a reaction flywheel, which is essentially where we have a flywheel that's in the rocket, and rocket's rolling one way, we spin it the other way, and your inertia is going to be, or your momentum is going to be preserved. So I personally actually really like this idea initially, and I think it's a really appealing concept. The nice thing about it is it's all preserved, or it's all contained inside the rocket, so you don't have to deal with any added drag, you don't have to deal with any additional aero simulations, things of that nature. The problem is it's a lot of power, it's a lot of weight. So when we did hand calcs using our rocket, or our expected rocket masses from this year, we found that we would need an optimized flywheel of roughly 1.8 kilograms to spin upwards of 5,000 RPM in order to maintain this stability, which not only would that take a lot of power to maintain, which would be difficult to do on a moving rocket, also we were worried about adding the gyrational forces that would be introduced to our airframe from that system. So, canards. Now, once we've decided what we're doing, then we have to figure out how we're actually even doing that. And there were two main mechanical approaches we considered to canards. The main design philosophy with this, and really with all of our add-ons to our rocket's primary goal, which is to deliver a payload to 30,000 feet successfully and uninterrupted, is we don't want any of those additional features to disrupt that goal. So the way we look at this from a failure mode perspective is the worst thing that we want this system to be able to do is absolutely nothing. And that's what we're looking at. So in this case, we wanted to avoid adding any additional pitching moments into the design. Now, we did a lot of things with the development of our canards to avoid the introduction of pitching moments and to keep them as roll only. And one of those is making sure that they're all mechanically aligned. So if one of them's at one angle, they're all at that same angle. In order to do this, it has to be mechanically linked from one central actuation point. And this presents a bit of a challenge from just, transmission perspective. And initially, what we looked at was essentially a belt design, where from one servo you have a belt that weaves throughout the entire system and goes to your three outputs. Problem is tensioning that. Once you tension it, where does that tensioning go? It causes your blades to be misaligned. So we're then left with this next design option, which we ultimately did, which is a combination of bevel gears and 4-bar linkages. What we get out of this is we get roughly a 9-to-1 gear reduction, or 9-to-1 actuation reduction from our servo to our output. We like this because we can get additional control precision within our control regime, which is roughly plus or minus 5 degrees on our output. Additionally, we like this because, and this might sound funny, we like this because the bevel gears introduce backlash. Now, a lot of times, you hear backlash with the system, you're like, oh, that's not good, it's going to be imprecise, that's a flaw, we have to get rid of it. And to an extent, that's true. And to make sure that we were okay with this backlash, we had to do a bunch of vibrational analysis that we'll talk about later. But what we like about it is it allows a little bit more air tolerance into our design. So the bevel gears added a backlash of plus or minus 0.5 degrees. And the nice thing about that is, say our servos align slightly off, we have an issue with our electrical signals, our linkages might be slightly off, that would lead to a little bit of slop. And that's where if we can't get to a perfectly straight neutral angle from a controlled perspective, aerodynamics and this backlash is then going to take us back to that neutral angle. And again, this is going back to the original design philosophy of the project. So one of the other things that we talked about is we want to have dynamic stability with this project, or with the fins. And the way that we do that is we calculated the center of pressure on the blades and made sure that our point of rotation is in front of them. The way you can think of this is kind of like a caster wheel on like a grocery cart. And yeah, we'll talk about more about the philosophy behind that in a bit. And then here you can just see the full stack up of the design, from our servo to our linkages to the beveled gear to the output shafts to the canard blades.
So we used CFD simulation to understand the aerodynamic effects of the canards and make several design decisions. So our three main goals with the CFD were to understand and analyze the downstream flow effects on the aft section of the rocket caused by the canards, find the center of pressure of the canards, and ensure that we can maintain sufficient stability of the rocket as a whole. So after our analysis, we were able to determine that there is minimal downstream effect on the aft section of the rocket caused by the canards. We chose the pivot point based on the center of pressure of each canard fin, and we're confident that we can maintain a high enough stability caliber for the overall rocket. So to determine the placement of the canards along the rocket, we ran simulations for several test cases where the canards were ranging from 55 to 61 inches from the aft end of the rocket and at angles of attack of 0, 3, and 5 degrees. We knew we wanted to keep the canards pretty close to the rocket center of pressure to avoid introducing pitching moments, as Connor mentioned. And the 61-inch location proved to be optimal because it minimizes the overall aerodynamic drag of the rocket as a whole, and it also has the greatest variance in the drag produced by the canards based on their angles of attack. The sims also influence the sizing of the canards, which you'll notice are considerably smaller than the rocket's fins, and it also caused us to lean towards smaller angles of attack for control, both of these decisions in order to minimize the turbulent flow over the aft section. The center of pressure of each fin is at 39 millimeters from the bottom of the canard fin, or 52% of its length. And as Connor mentioned, we added a failsafe by putting that pivot point directly above the center of pressure so that they'll tend towards vertical in the case of a failure, and avoid adding unnecessary instability to the rocket. We chose the NACA 0006 airfoil as the profile for the canard fins. We chose this based on its relatively low drag profile in transonic and supersonic speeds, and also its relatively simple geometries for ease of manufacturing. And finally, the sims show, based on the visualization of the drag contour, that there are minimal effects downstream on the fins and the air brakes caused by the canards. And we were particularly concerned with our deploying Airbrake system because it's positioned just aft of the canards. But even based on our sims, even at our maximum canard angle of attack, we still experience 99% of the drag we expect to be produced by the air brakes, so this shouldn't be an issue.
All right, so we did mention that we wanted backlash, but how about like all the vibration of the free play you get from the backlash? How's that going to negatively affect our system? So at supersonic speed, it can develop, the vibrations can develop into control surface flutter, which is a significant problem that we need to evaluate. So we basically develop a time marching simulation. So that just sweeps the velocity profile of the rocket from launch all the way to apogee. As you can see right there, that's where the maximum roll rate is. That's roughly where burnout happens. And then this first iteration is with our original sort of blade profile. And here you can see this is the vibration amplitude. So the gray region is the backlash region. We want the vibration to stay within that region, because if the vibration gets larger than that backlash region, then the vibration spreads into the gear train and into the other systems, which is bad. So in this case, here we see that's a significant thing we have to worry about, because we have it gets outside of that backlash region. So for our second design, we decided to dynamically and statically balance the blade by placing the pivot point like right on top so that it's aligned with the center of pressure and center of mass of the blade. So we did mention that the pivot point has to be slightly in front of the center of pressure, so that solution is a no-go. And then also we would also have to have a non-uniform mass distribution because we don't want to modify the blade profile. So the only way we can make sure the center of mass lines up with a pivot point is having non-uniform mass distribution. That can be achieved by having like little cavities inside the blade or having little counterweights. But with the small size of our canard blade, that's pretty much very hard to do manufacturing-wise. So that solution is no-go. Well, so what solution we choose? We chose this third solution right here. So third solution is basically a very simple solution. We try to add a certain amount of damping to our system. It can't be too little damping because it won't work. So it has to be a certain amount of damping. We determined this amount by running the sims, and then we chose a high viscosity automotive grade grease that we use to fill in between the teeth of the bevel gear, and this helps take out the vibrational energy of the system and will help make sure that all of the vibration is not outside of the backlash region. So this is the solution that we chose.
Yeah, so on the manufacturing front, all of our hardware was made in-house by us. That includes the housings, the linkages, the shafts. That was all done by us in-house. The main housing was made from billet aluminum 6061 T6 for its good strength to weight ratio and ease of machinability. And that was from a solid billet. And then all of the other operations were either done on a CNC mill, on a lathe, or on a water jet, with various post-processing operations done after that. Next slide. On the left here, you can see our canard housing after the initial machining. This was done on a mill, and it stands at about 5 inches tall. And then after this, we took it to a 4th axis on a CNC mill so that we could finish some holes for mounting the bearings and mounting the connections to the rest of the rocket. On the right there, you can see the lathe-turned steel shafts. These were done to a very tight tolerance because we don't want any unpredicted slop to be present in the system. So these were done to very tight tolerances to ensure that. And then for the blades themselves, we've used a process called forged carbon fiber. So Duke Air has been working on this and perfecting it for the past 3 years, but this basically involves printing a mold from plastic filament. So we use PETG as the filament, and then we take dry carbon fiber, combine it with epoxy, put it into a mold, compress the mold, and then once it's dry, we can take that out and we have our part. After this, we can do the post-processing operations to clean up the part, get it down to final geometry, and that gives you a really strong, lightweight part. And this is the manufacturing method we chose just because it would be tough to mill this part or make it any other way. So the molding technique really lets us get the really thin geometry that you can see on the side there that we wouldn't be able to do with any other manufacturing method. Yep. And so during assembly, we needed to ensure that the blades were lined up with the shafts and the shafts were indexed off of the gears. And so to do this, we made some jigs to make sure the blades were straight up and down so we could tighten all the screws and lock everything in place. And then each of the components individually were match machined. So each blade had a specific shaft that it went to and then went to a specific hole so that as we made each part, we could measure the actual tolerance that we achieved and then adjust on the next part to get really tight tolerances, which would have been infeasible to achieve without that. And then the total assembly stack up, you can see the control stack here with the air brakes underneath the canards, sitting right over there too. And then middle picture is the blade integration on the shaft next to the side of the housing. And then you can see on the far right there the canard plate, which houses the servo, those bevel gears, and then that interfaces with the shafts and the blades as well.
All right, so the final part of the puzzle is writing control for the system. So it's a rocket, right? You can't really just launch it a bunch of times and try to fine-tune the values. So we got to find a simulation software. So we chose Rocket Pi, a 6 degree of motion, 6 degree of freedom flight simulation library written in Python, which has been used extensively by Duke Aero before. But the catch is there's literally no online documentation for aerodynamic control surfaces, for complex control surfaces like canards. There are documentations for other control systems like Airbrakes, which a lot of teams have been doing, but there's like nothing for canard. So we basically had to like build the control loop for that from scratch. So we went through all the documentations and we developed a custom framework to develop a closed loop control system for aerodynamic surfaces. So with that done, time to choose a control algorithm. So since roll control is pretty linear, so and it's pretty sort of not complex to control. First, we chose a very simple algorithm. Here, this is bang bang control. So you can see the flight profile right there. That's burnout, so it kicks in at burnout, and then it holds at the set point of 0 roll rate. So you can see this, it has a pretty good control authority. It holds very well, but then here you see that's the output of the shaft, and you see that's a lot of oscillation right there. So that means the shaft's going to be moving back and forth like really quickly, which we don't want because that's going to impart a lot of mechanical stress on our system. So we move on to our next solution, which is a proportional high gain P only control. So we see that's the roll rate, it kicks in there and it holds. So you see here it holds pretty well. We don't have the output is pretty, it's not as aggressive. So that's a potential solution, that's a potential choice. But then here you can see once it kicks in, that's a very sort of aggressive drop right there. That's a very sort of sharp movement, which we don't want that because that's also gonna cause a lot of mechanical stress. So we chose sort of a ramp down set point here. So it kicks in here and we sort of ramp it down from whatever roll rate it is to 0 within 5 seconds. So it just ramps down and we hold it there. So that gives us this sort of like really nice ramp on the output, which helps mitigate the very sharp control sort of movements, and it holds pretty well as well. But then the problem is, of course, it's only P only, it's medium gain P. So there's going to be some steady state error. So you solve steady state error by adding an integral element into it. So right now we have a ramp control, ramp set point, medium gain P and I control. So here you can see that's the ramp, and you have that hold, it holds pretty well, and the output is not very aggressive, which is good, and that's the solution that we chose. So yeah, now we need to tune P and I. So we ran a step response test because of the inherent stability of the rocket. We can't really tune it using like oscillation method like Ziegler-Nichols because we can't really get good oscillations. So we chose step response, we just tuned P and I to get that good step response right there. So we chose those P and I values, and then we stress test these P and I values in Rocket Pi with different weather and different wind gust condition. So for example, it's going up, we add a wind gust at this certain altitude, see if it's gonna change the roll rate and see how much we can control that. So we stress test that, and we ran a bunch of iterations, bunch of simulations on this, and we find that these values have good control authority, and so we chose them for flight.
We're really excited about this next step in active control of our rocket, and we'll be flight testing the system for the first time when we launch our rocket this week. We'd like to say thank you to the rest of our Duke Aero team, as well as our faculty and advisors back at Duke University and our corporate sponsors. And thank you to you all for your time, and now we'll open the floor for questions.
That's mostly just required by rules. That's primarily done by IREC rules, just because we're required to not do active control during motor burn. But another advantage to that is we are able to wait until we've slowed down ever so slightly. So we have slightly lower dynamic pressure to allow less strain being put on our internal mechanisms.
So, do you have anything to control induced oscillation? Let's say just this, it's inducing oscillation instead of deafening. It can happen after a certain set of parameters are crossed. Do you have anything in the code itself or mechanically in the rocket that would prevent that?
Do you mean by the oscillation within the roll of the rocket, or the oscillation of the canard blade itself?
I mean, what I mean is, it's gaining, like, it's knowing that it's rolling, right? So you have a roll rate. Then you have a response in terms of the angles changing. So it is a possibility that the delay.
Oh, I see what you mean. So it chases. Okay, yeah. Yeah, so we actually limit the rate at which our canard blade can move. So it can move 10 degrees per second, so that's about how fast it can move. So we don't want anything more aggressive than that. So we want slow control, slow movement, because slow movement and the rocket's also inherently stable. So slow movement means it won't chase. And then, yeah, that's basically what we do. We sort of limit the rate of movement of the canard output, so it won't sort of like chase the roll rate.
And you're getting what kind of data you're getting from the sensors? What kind of sensors do you have?
We have a MEMS accelerometer and gyroscope sensor. So that sensor, that's also a reason why we chose PI, not PID, because the sensor sort of it gives you the roll rate based on the angular acceleration that the sensor is experiencing. So that means if we use PID, that means if we have wind gusts that sort of like push on the rocket, that is going to give you very sort of noisy output accelerometer data, and that sort of noisy data is very bad when you're doing PID, because that D element is very sensitive to noise, so you don't want that, so we chose PI only.
What improvements would you add if you had more time?
Yes. Well, I think, you hear canards, people like to talk about pitch, and that's obviously something that we'd love to look at long-term once we've been able to validate that this can work. So that's probably the long-term validation that we would want to do. Short-term, I think, you can always do more analysis, you can always do more testing, and that's something that we would like to do, given more time, is just conduct, additional analysis on some of the different systems. Yes.
You have those pins, they go through the fuselage or something. What keeps them from galling?
Do you mean like the shear pins?
Yeah. No, the shear pins,
Okay.
the drive axles.
The output shaft.
When you say go, what do you, like falling out?
Twist back and forth, and they go through something.
Ah, yes, okay, so,
You want to keep galling.
yes, so the inside is secured with a set screw, and then the outside we have a exceptionally high press fit dowel rod that was run through the blades and the shaft, and then grinded down on either side, so it kind of fuses. Oh, I see what you're saying. Sorry. Yes, we have a bushing on the inside, and then we have a ball bearing that integrates with the housing. Yes.
Are you guys filtering your accelerometer, your sensor data at all, or are you just using the raw data?
Well, we try to filter it like very minimally, sort of like just like a running average. We don't want to like smoothen it too much, but just like ever so slightly filter it so that you don't have too much noise. Yeah.
And with, I know sometimes there's just integral gain to the integral windup. Was that ever a concern or managed in a way, or?
Yeah, so we did see sort of integral windup in when we ran like the Rocket Pi sims. So we chose, well, basically we tune the P and I values so that that doesn't happen. And we have like a pretty like high safety margin that like make sure we don't fall into that region.
What's your sample rate from the accelerometer?
20 hertz. Our control loop is 20 hertz.
Have you thrown
Yeah, so we had plans to run this through a wind tunnel. Unfortunately, the wind tunnel that we have on campus, it peaks at 40 miles an hour, so that's not great. We ran it under a very high flow rate air hose, which is very qualitative data, but it seemed to perform well under that.
That's it?
All right.
Excellent.
Hey everyone, we're RIT, and we're going to talk about how we extended OpenRocket with MATLAB. I'm Yev.
I'm Aries.
I'm Kyle.
Basically, when you're starting out your design, you probably use a graphical trajectory simulator. So that can be OpenRocket, RAS-Aero, RockSim. Then, as you progress, you find that you need more advanced analyses, especially as you evolve in the competition. So you'd switch to RocketPy or something that you made, something programmatic. For us, OpenRocket's really nice, but you can't use it programmatically. We can't do component optimization, parameter sweeps, and it's hard to develop extensions because you have to provide all of them with a user interface. So we made an API for MATLAB
taking inspiration from the Python package OR helper. It basically instantiates an OpenRocket document and exposes its methods to the programming workspace. MATLAB specifically is nice for us because in a lot of ways it's easier for us to use since more of our team members know it, and because its integration with Java is much more streamlined. So we're going to present our first 3 uses. That is to numerically optimize the components of our vehicle, to assess the accuracy of and then integrate weather forecasts into our models, and then to present a sensitivity analysis based on those assessments. Over to Aries for components.
Thank you, Yev. One of our first uses for this API was to optimize mission-critical components, such as our fins. Our fins determine apogee, stability, and fin flutter, which are all important factors for a successful flight. MATLAB's numerical methods let us optimize these metrics, and through creating this optimizer, we have the ability to quickly iterate on designs, which allows us to adapt to changes that happen during a rocket's development. Previously, our methodology was very similar to other teams. We'd have a common fin shape, we'd change it in OpenRocket, and stop when these parameters were satisfactory. However, this was a very long process, and we were unsure if it gave us the most optimal design. This year, we have moved to trying to optimize these components. This is classified as a multiple input, multiple output optimization problem. Our initial solution to this was to create an exhaustive search. This tested every possible combination within certain bounds of an initial guess. However, this method was even longer than our initial process. Despite that, we were confident that this gave us a global optimum as it tested every possible combination. This was too long, however, so we moved to the Nelder-Mead solver method. This worked in minutes instead of hours, but it came with a few different changes. The Nelder-Mead solver method does not always give you a global optimum. Sometimes it can get stuck in local minimums. Additionally, this was a good solver for our problem as it works with non-differentiable problems. Our optimizer setup was as such. We had a total of 6 component variables that we optimized, as seen here, which are fin dimensions, and we also added a stability weight in the nose cone to better tune our mission parameters. Our outputs are as expected: apogee, stability, and our fin flutter. Another thing that we had to consider was stock constraints for our fins. The Nelder-Mead solver method operates on a cost function, and in this cost function, we had to consider 3 different things: normalization, mission requirements and their behaviors, and penalties. Normalization is probably the easiest to understand. Our mission parameters exist on wildly different scales. Consider apogee versus stability. If we simply took the genuine difference between our guess and the actual value, one would get weighted higher than the other in the optimizer. So in order to combat this, we needed to use a percentage error instead, which is seen in the cost function. Second, mission requirements. We created this cost function to better show our general desired behavior for the penalties that we wanted to apply. What I mean by this is generally we wanted to apply a heavier penalty to something below the target and a less penalty to something above the target. As you can see, the graph doesn't have the same cost function for every output, however. This is because we needed to capture individual criteria and modify the cost function to reflect that. The way we did this was by changing our coefficients. So for a between 0 and 1, this affected anything above the target. For a is greater than 1 and n is between 0 and 1, this affected the behavior of the function itself. And for n is greater than 1, this affected below the target. There were some special cases. For example, in the DTAG, fin flutter must be above 1.5. So it doesn't make any sense for us to penalize anything that goes above that, which is something you can see. The cost goes down to 0 after it hits target. Another thing we had to consider was the stability at burnout. We want our stability to be between 1.5 and 4. So in order to capture this, we made the penalty less for below the target and more for above the target. So all we did was flip the sign on n. Last, penalties. The Nelder-Mead-Solver method is an unconstrained solver, so we must manually add penalties in order for this to work. The best example for this we have is apogee. Anything below 98% to the target for apogee immediately jumps up to 100 in the cost value. Here is a solver visualization of it working. On the left, you can see our outputs: apogee, stability, and our flutter margin. This is over time and during the most critical components of the flight. You can see the top one for apogee is as it reaches apogee. Stability goes from launch rod to burnout, and this is our fin flutter margin. You can see as it progresses, it started off in the red, and over time, it comes up to meeting our parameters. On the right, you can see the actual value converging to its target. As mentioned, we had some stock constraints. Our stock came in 1/8, 3/16, and 1/4. With this tool, we were able to optimize each thickness to its most optimal dimensions. And there, we were able to create a trade study based on that. As you can see, 3/16 was our most optimal thickness. The Nelder-Mead-Solver method can sometimes get stuck in local minimums, so we needed to verify that our solution was indeed a global optimum and not a local one. The way we did this is we conducted multiple optimizations starting from different initial guesses, and all converged to the same fin shape, which allows us to believe that the initial guess didn't affect the output as much. Our first method was also an exhaustive search, and comparing the results from the exhaustive search to the Nelder-Mead-Solver method were very similar. And since we know that the exhaustive search gave us a global minimum, that also indicates that the Nelder-Mead has also given us a global optimum. This tool has allowed us to create our final fin geometry and weight for our stability weight. We are confident that this has given us the most optimal results, but most of all, this tool has allowed us to continually adapt to changes that will happen throughout development, which is not something we have previously been able to do before. On to Yev.
Thank you. So, especially at the higher levels, a lot of teams know about using upper air weather data sets produced by NOAA or other national weather services to aid in simulation. Now, it's known that they improve simulation accuracy, and you get them from a National Weather Service. Rocket Pi has ways to pull it in, and the new Open Rocket Beta also has ways to integrate weather data. But what we don't see discussed is exactly the extent to which this improves the simulation's accuracy, or what the upper limit on the accuracy of the forecast itself is. We're going to consider, for this analysis, 6 data products given by the National Weather Service: 3 resolutions of the global forecast system, 2 resolutions of the North American mesoscale model, and the rapid refresh. These have widely different lateral resolutions, publish rates, time resolutions, and vertical resolutions. And normally you would expect that these differences accumulate to large differences in the accuracy of the prediction. Now, these produce 2 different kinds of outputs: analyses and forecasts. Analyses are the best guess of the current state of the atmosphere, published right now. And those are useful if you have a historical record of them to assess typical conditions at the launch site. You pull all of the analyses from a month, average them out, and figure out the spread. Or if you've launched and you have kind of a GPS packet from Apogee, for example, you can run an analysis centered around that time, or you can pull an analysis centered around that time to try and figure out the most likely landing point, given that initial point. Forecasts, on the other hand, are what you would use to tune your vehicle ahead of launch. They're published now, and they are applied to a point in the future. So in order to assess the accuracy of all these model data, we obviously need ground truth data. Ideally, we'd use sounding rockets. But there isn't a database of sounding rocket flights of any size, let alone one large enough to give a sample size that would make this analysis valid. So the next best thing are the raw GPS histories recovered from National Weather Service weather balloons. These are aggregated by a website called SondaHub on an S3 bucket, and these give us the ground truth for our simulation. Every radiosonde begins from its first sample near the ground, ascends up to its burst altitude. Overall, that gives us 3,000 flights over last June, which is plenty to make a significant determination. In order to run the simulation, we need to implement MATLAB tools that pull radiosonde and weather data. And the weather data retrieval also integrates into our MATLAB extension. We initialize the simulation with the first sample, drift it using the wind vector. We assume that the very light and large radiosonde will drift approximately with any air parcel at that given point. And rinse and repeat until you get a simulated trajectory. Do this across all of the radiosondes, then across all of the models, and then across all of the forecast steps that we're comparing, and you have the data set we're using as for our analysis. Specifically, we're looking at the wind vector. On ascent, this is going to drive your angle of attack change. So as your rocket burns, its stability changes, and the change in the angle of attack might cause significant effects to your trajectory. We'll assess exactly the extent to which these are significant and how accurate the wind forecasts are. On descent, you would be interested in how accurate the descent prediction is. So you time integrate the quantity from the previous slide to get where you think your rocket will land. So we find that the wind vector is consistently accurately simulated by all of the models. So we have a 2 meters per second root mean square error for any component of the wind. And just for clarity, we're not showing the other component, but they behave the same. And that's for mid altitudes. But it gets worse at low and high altitudes. So at low altitudes, the models are less able to resolve the planetary boundary layer. At high altitudes, they're less able to resolve the tropopause. Fortunately, all of these metrics have very low bias. So from time instant to time instant, we can just sample, to get a good idea of our uncertainty, we can just sample from a random distribution. For the 12-hour forecasts, we get a broadly similar behavior, but a slightly worse wind. And we ran various depths from 12 to 42 hours. The 42-hour one is the most informative. At this point, the bias in the wind vector accumulates to the point where the prediction is very poor. We can see that even more clearly on this slide. So for analyses, we find that the highest resolution model, as we expect, gives us the best prediction, but not by that significant a margin. It's about a 50-meter CEP, circular error probable difference between NAM and GFS. We get broadly similar results for 12-hour forecasts, so it doesn't super matter which 12-hour forecast you use, but the global forecast system is lowest file size. And when there is a difference during longer integration times, the outputs are clustered by the model. So the model matters much more than the resolution you're using of that model. And the 42-hour forecast, as we saw earlier, the bias accumulates. Overall, they perform similarly. The system is more impactful than the resolution. So we can see the clustering of the different forecast systems. We find that their like worst case wind output you saw there was 20 degrees. So that means that the direction that the wind is blowing is very well estimated. But counterintuitively, while we get the best analysis from the highest resolution system, we get the best forecast from the global forecast system, which is not the highest resolution. So depending on which use case you have, you should use a different data product. On to Kyle for the sensitivity analysis based on these assessments.
So we simulate a rocket in a wide range of environmental conditions to see how it will perform. In the beginning of the year, we used a large set of environmental conditions for design verification, but it wasn't the most plausible set of conditions. So using the data from NOAA and the tool chain that we've integrated, we've created this custom atmosphere that was sampled last year from Midland from late May to late June. We can see here that Midland is not an ISA atmosphere and indeed is custom, and it is consistently different, and that's why we are confident in it. For ascent, we are mostly interested in ground level winds because these have the greatest effect on our flight performance. So how does a custom atmosphere affect our apogee? We have 4 different scenarios, each a modification of the original simulation without the custom atmosphere, each with a different part. We have the baseline, then we have the pressure temperature profile, then we have the wind profile, and then we have the 2 of those together. There is no significant difference between the wind vector. This makes sense because the launch rod exit decides most of the rocket ascent. There is a 10-meter difference between the pressure and temperature profile. And there's a 50-meter difference between the pressure profile between the baseline and the physical apogee. This is really important because the COTS flight computer uses the indicated altitude to calculate the altitude that we are at. So we have to adjust for this in our optimization. And we account for that with a 205-meter offset from 10,000 feet. So because the ground level wind contributes to variability in our apogee, we can break that down into 3 separate parameters that cause the most of the variation. The greatest contributor to the variation is our wind speed, and then temperature, and then wind direction. So we have about 56 meters of total variation that we're expecting due to changes in environmental conditions. So we can cover this entire range with our adjustable stability weights. Prior to the launch day, we will run an optimizer that for every hour chooses an optimal mass to get us to 10,000 feet. Of course, we don't know exactly which time we're going to launch, so across the time window, we will take the average of this mass, and that will be our final mass that we will use. Looking forwards till tomorrow, we have about 790 grams, but we will continue to run this optimization as new forecasts come in. We have 3,000 grams of additional weight that we could potentially add in binary increments from 45 to 1,600 grams. So we've done all this analysis, and now we're comparing our methods. We could see that between the old method and the new method, the standard deviation has decreased quite a bit. And the range of our apogee variability has also decreased. So now looking at the baseline with no custom atmosphere on the left, and then the ground level variation and the upper winds variation, we can see that the recovery point spread becomes a lot larger. And this is really important for sizing beacons and radios, etc.
Thank you, Kyle. Overall, this API allows us to use MATLAB for its quick and advanced analyses while still retaining our usage of OpenRocket. With this tool, we have created an optimizer for mission-critical components that can change over the course of development. We have figured out which upper air atmospheric data set is more useful for analysis versus forecast. And with this knowledge, we have a better understanding of our uncertainty, which can drive design decisions. However, these are only 3 different projects that we chose to make. This is open source and on GitHub for any team to use for their own analysis and simulation. So we look forward to seeing what you guys will choose to do with this tool next. Thank you very much. Any questions?
Do you have more information about Rocket Pi?
More information. So just to expand a little bit more quickly, it's a Python package that is its own 6-degree freedom simulator versus OrHelper, the other Python package we mentioned, just hooks into OpenRocket. It is a very powerful tool. A lot of teams use it, especially because it has a lot of its built-in, like weather data retrieval, and it can simulate sensors for you. But it doesn't have a graphical user interface. So it's really only useful for that late stage in development. And having an API that talks to an OpenRocket model makes the bridge between the initial design and the final analyses a bit cleaner.
If I use Simulink from MATLAB and I do the same thing, is it like is there a significant improvement comparing to that, or you have not tested that?
We haven't tested that. So are you talking about implementing your own 6-degree of freedom simulator in Simulink?
In Simulink.
I would imagine it depends on the implementation. Because the advantage of this is that we don't need to re-implement a 6-degree freedom simulator. We just use Rocket Pi's own engine. There are reasons to do one or the other. For now, the trade-offs for us mean that Rocket Pi is a better choice, just for its simplicity.
Is the component optimizer a function of Rocket Pi, or is that something that you guys homebrew?
No, this is something that I created myself.
Good. And following question into that, the newer standard method that you created that is way faster, compared to the old one that would go through everything sequentially. Did you ever try to give them like the same starting parameters and see whenever it would get stuck on a local minimum on the new one? The way that you got around that was by creating different ones and see if those different ones converge onto onto.
No, so two different things changed. So yes, you're correct in the first one. One of the tests that we did was starting it at several different initial parameters, and it converged to the same shape. But the thing you're mentioning is something we did do. The shape that the exhaustive search gave us was extremely similar, like within 0.01, to the one that we got with the Nelder-Mead method. So we are confident that that gave us a global optimum because of it, yes.
Yeah, that's what I wanted to know. Thank you.
When using the weather balloon data to compare to the weather models, do you take into consideration whether any of the weather models have also used that data?
So they do. This is actually a very interesting point. So for analyses, it's kind of circular in the sense that we're assessing the performance of a model that is trained on the data that we're predicting against. But we still think this is valid because analyses, like we're not claiming that analyses give you better predictive power into the future. They give you a retrospective ability. So for simulating your rocket after the fact, like you have the analysis after the fact. And for assessing typical conditions, the assumption that requires is that the weather is consistent for a given season from year to year, which is obviously somewhat of a strong assumption, but it gives us a good starting point to look from. So and to your point, the forecasts don't integrate the data that we're training on because it was published at a much earlier time than we're training on.
This may be a bit of a dumber question, but is this working similar to like how an MPC system would work conceptually?
MPC, well, we're not controlling anything.
Okay, no.
Oh, yeah.
When you're changing your mass in the nose cone, you said you consider that affects apogee, you also consider that affects stability?
I think the range of variations that we're considering does not have a significant impact to stability. Like we still remain within Ezra's target.
I believe you're asking that since we've optimized it previously and then there's a further optimization afterwards for the nose cone, is that what you're confused about?
I wasn't asking that, but that's also a good question.
Yeah, so to Yev's point, the variation in the stability weight doesn't drastically affect those things, and furthermore, it's more tuned towards apogee rather than stability.
I have a question, please correct me if I'm wrong. Did OpenRocket already have an optimizer method for some components?
Yes, but it's very poor.
Yeah, okay. That was my experience.
I think there are situations in which it's appropriate to use a graphical interface and situations in which it's appropriate to do things programmatically. And numerical optimization is definitely one where you want to do everything programmatically.
Absolutely, I agree.
Sorry.
Yeah, that's fair enough.
Have you gone through multiple like fin shapes due to your optimizer?
Yes. So one of the main points of making this, and one of the things that has helped our team tremendously, is I think we've gone through maybe 40 different fin designs. And that previously was impossible with the current ways that people create fins. This works in minutes. So I can put in different initial parameters, different targets, different weights. I can even change the cost function, and it spits out a fin that hits our mission parameters within minutes. And we can continuously do this while the rocket is in development to adapt to changes like, for example, weight changes after manufacturing. One of the things that we dealt with was we had a big stock change during our development of our rocket, and this was tremendously helpful because we were able to create something that could just instantly create a new fin.
Payload lost 4 pounds too, so.
Yes.
How do you reconciliate the stock material, the fin, with any fin layouts or anything that other people might want to do?
So the way that our fins work is we get like carbon fiber stock from our sponsor Dragon Plate, and we are not able to like pick the dimensions of the stock that they give us year to year. So it's not like a layup or like a composite fin or something like that. It's just a plate of carbon fiber that we water jet.
Thank you, guys.
Of course.
Still got a minute. Or not.
You can actually adjust for fun.
Excellent.
Okay. Good afternoon. We are Team Abhyuday from Indian Institute of Technology, Madras, and we'll be presenting active braking and control system, our podium presentation. So the main motivation behind this project is stemmed from our first rocket we launched in this competition 2 years ago, Chetak 1, which experienced excessive roll. And then last year we launched a rocket that did not have a lot of roll, but overshot by around 4%. Thus, we wanted to explore methods to have more efficient flight profile and flight performance. As well as it's an industry problem and we wanted to explore solutions. So this is not our first time trying active controls. We tried it last year, and last year we tried a roll control system based on a PI controller. However, we did not conduct enough simulations on it, and we failed structurally at launch. That's why this year we are coming up with a more holistic system.
So coming to the structural part, the canards and the air brakes are in a single controls tube of the rocket. The canards are placed in aligned to the fins of the rocket, and the air brakes are placed at a 45-degree angle to it. So the air brake system mainly works on a lead screw mechanism. This is how 3D printers have some of their actuations. So the lead screw is turned using a DC motor. The rotational motion of the DC motor is turned into a linear motion through the lead screw, and this using a push rod mechanism is turned into a flapping mechanism by the air brakes. So you can see that right here. Yeah, go home. Yeah, next page. So also now the servo. The servos, each 4 control surface are connected to a servo inside. Each of them can be actuated individually, but in flight they will be coupled together. You can actuate one of the servo. It's one behind. Yeah. So the servos are attached. So these servos only provide the rotational torque to the control surface. They do not take on any of the other loads that the surface experience. They are actually taken by the body tube. They are connected to the control surface using a bearing, as you can see in the third image. Yeah, next page. Now coming to the electronics. The main microcontroller for our system is a TNC 4.1. This is a chip that can take high computational loads. This is one of the reasons why we chose it. Now for the servo we are using is an 80 kg CM servo. These servos can take 80 kg CM torque maximum, and the DC motor, we are using a simple DC motor to control the air brakes. Now for the sensor, the 2 sensors we have on board are the IMU and the BNO055 and the MS5611. They are IMU and the barometric sensors respectively. They are for getting the altitude, velocity, orientation, and etc. Now we also have a magnetic encoder. This is to calculate the absolute angle of the DC motor inside. This is how we get the angle of the air brakes. And also we have a current sensor for the servos and a motor driver for the air brakes. Now as you can see, the PCB is designed such a way that the IMU is in the middle. This helps us we don't have to account for the offset in the IMU because of this case. Right, yeah. Okay, so coming to structure part. As you know, previously our structures failed. So this time we had to give more focus into the structure part. We did a couple of simulations in ANSYS for the structures. For canards, the fixed surface were taken as the bearing, the surface that the bearing came in contact, and the load were applied to the control surface at a deflection of 8 degrees and a maximum velocity of 0.8 Mach. This is what we got from a predicted engine performance. This would be the maximum velocity. And we found the safety factor to be around 1.5, which we believe should be okay enough. Now for the air brakes also, we actuated the air brakes at a 50-degree deflection and a 0.6 Mach. The simulation showed around 1.2 safety factor. Now coming to CFDs. So For the canards, we were doubtful of how the canards would affect the fins behind. So we had to do a couple of CFDs. And in the CFDs, we found that when canards are actuated, vortices from the canards hit the fins behind. Due to these, some at high deflections, the net roll moment of the rocket is opposite to what we intend. This is something called roll reversal that we found out through simulations. And also we have done multiple simulations with different canard shapes and positioning of the canards. For Airbrakes also we had done simulations, but in Airbrakes case we were more focused on to the data. We wanted to get the drag values from the CFDs so that we can use for the simulations. Also in the simulations we were able to find that there's not much interference that the air brakes provided to the fins. Since the air brakes were positioned so higher up, they didn't provide much interference. At the same time, the fins were large enough that the CP shift that the air brakes made weren't that high to destabilize the rocket by actuation. Next year. So here we have a few points. So the points we got from CFD we used to curve fit to get a CD plot, which we later used to make our lookup table. So we had a linear and quadratic fit. In the linear fit, we found an error of about 15%. In the quadratic fit, we found an error of about 5%. So we went with the quadratic fit. So now the control architecture. As you can see here, this is what we will have inside our code. So it initially detects launch and burnout using the IMU. Once that is done, we have a 5-second canard actuation time period. So for the next 5 seconds, we will be actuating canards only. At that time period, it detects for roll. If there is roll, it checks for the rocket's pitch. If the pitch of the rocket is too high, we do not want the control system to actuate as it's unsafe. So if the pitch is too low enough, we deflect the canards. Also after deflection, we are checking if the canards are working well enough. If in case even after deflection the roll is going up above a threshold, we do not deflect canards and go to the Airbrake actuation commands. If that's not the case, we again go back and check for load. This is another failsafe to ensure that each servo is having equal amount of loads. If it's not the case, that means either one of the control fins broke off or a servo is not working, etc. At this case, for safety, we will go back to the Airbrake actuation. Now once the canard actuation is done, we go to the Airbrake systems where we check for if the rocket will overshoot or not using the lookup table. If it does overshoot, we check by how much it does overshoot, and from that we calculate the error and we put it for actuating the error as well. Here also we have a pitching check to ensure if the rocket is too much pitching, we do not actuate the air brakes. Next. So coming to the air brakes control algorithm. So why we needed air brakes in the first case? We are going with hybrid rocket this year, and hybrid rocket engines are a little unpredictable. We haven't tested it in flight till now, so we are not sure of exactly how much altitude it will go up. So in this case, we needed the air brakes. This is a 6-stop model we made for simulating our air brake, like simulating the drag due to the air brakes. Next slide. So our logic is mainly implementing a kinetic energy approach. So at each point, for a given velocity and altitude, we calculate what the estimated apogee is, and from that we get two errors. One is the error between the estimated apogee and our target apogee. The other is the error between our current altitude and the target apogee. So using that, we calculate the gain. So here, since our air brakes don't produce a linear drag with velocity, we needed a dynamic gain. As a result, we used a dynamic gain based on the velocity. It's given in the function is given here. So yeah, using the gain, we get the control input, which is the function here above. And using the control input, we actuate the air brakes. So in here, we are using an exponential control algorithm instead of a proportional. This is so that during the initial phase or at higher velocity, we have maximum deflection, so that we get the most out of our air brakes, as well as if it is going to an undershoot case, we have enough time to roll back the air brakes out.
Also, we have a band of 25 meters, as in we are only targeting it to bring it around the plus or minus 25 meters of the 10,000 feet target. This is just in case if our system has any error, it doesn't undershoot by too much or overshoot by too much. Yeah. Also, now how we are controlling the angle of the air brakes. We have a magnetic encoder attached to the lead screw. So when the motor rotates, the encoder calculates the absolute angle, and from that we control the motor angle. And the motor angle and the air brakes angles are in a non-linear relation. So we get a couple of points for the both, and we used a polynomial fit to find the relation. Fine.
So moving on, we did a couple of software simulations with our control logic. We did about 100 iterations of variable thrust and drag values to see how uncertainties would affect the performance of our logic. We obtained that the average value was around 3,054 meters, where our target is 3,048 meters. Next. This is a graph on the variation of performance parameters obtained through simulations. And this is for the control parameters. We have kept the band a bit high so that, as he mentioned previously, we do not want to undershoot by too much or overshoot by a lot. Moving on to canards. So canards, as we mentioned, that we experienced excessive roll in our first year participating in the competition, and ever since then we wanted to find a solution to get an efficient flight performance. This is a brief of the internal control flow chart. From our results from simulations, we noticed roll reversal, and ever since then we have tried to mitigate it. So we tried few geometrical variations of changing the control surfaces, cross sections, the position, the number, or even try including split canards or different types of controls. However, we saw none of them provided enough effect, so we had to move to trying alternative controllers. Last year we tried a PI controller, which is a linear controller, and it assumes a constant gain. That becomes problematic when we consider roll reversal, since in that case the sign is continuously switching, whereas the gain is still constant. So instead of becoming a negative feedback, it becomes a positive feedback, adding to the error. That's why we looked into more controllers. Some of them were sliding mode controller and the model reference adaptive controller. The model reference adaptive controller would have given us more control, but it's very computationally extensive. So we went with sliding mode controller. That's a nonlinear controller method that pushes the system to a predefined sliding surface. This is an idealized graph on how you can compare the behavior of a PI controller and a SMC controller. If you have a look, you'll see that the PI controller has a lot of oscillations near the set points, whereas the SMC will try to slowly converge to the set point. Coming to the logic, right after burnout, as mandated by rules, the control systems will get activated. However, we have set a small band of 0.1 radians per second, as we don't want to mitigate all the rolls. If the roll detected by our sensors is more than this band, then only the system will get activated, otherwise it will stay passive. This is the roll dynamics, and this will be our control input. Further, we have also added an FTDO, that's finite time disturbance observer. This is to account for any further uncertainties like wind or something that we cannot account for or model for in the system that can cause chattering in the SMC. Chattering is like various oscillations nearing the sliding surface. This will help mitigate it. Again, we conducted Monte Carlo on this. We had various starting roll points, initial roll rates, and you can see it settles at around 5 seconds. Moving on to failsafes. As we mentioned previously, we have an inclination check, a load check, and an excessive roll check. So concluding, from our previous year, we wanted to focus on our structural stability, and our main focus this year is to gain a lot more data on how the flight proceeds and how our controller responds to it. And going ahead, we would like to conduct more wind tunnel tests and try more adaptive and holistic controller methods. These are some of our references. next year. Oh, yeah, thank you. We'll be now open to questions.
I think my first question for you guys is, you guys said that there is inherent instability or problems moving from a solid rocket motor to a hybrid motor.
Yes.
And this is what kind of was one of the many reasons that you moved to this. What's been your biggest challenge in implementing the system into your current rocket design?
I would say structurally, making the air brake structurally strong and giving less space was a challenge for us. In the end, we managed to do it. And finding the right actuators with the correct settings, that also takes lower voltages, as we can't put a heavy battery inside the rocket, was also a challenge for us.
Okay, cool. My second question I have is, I know you're basing all this off the internal measurements coming off your IMU.
Yeah.
Is that, do you find that you have vibrations that affect that IMU? What are your considerations or assumptions for that IMU?
Low pass.
So we have a low pass filter for the IMU. Also, the altitude is measured from the barometric sensor.
Okay.
So that, other than that, we have done some vibration testings. It doesn't affect to much extent.
How often are you running the control loop for the air brakes?
So we are going with around 10 milliseconds.
Okay.
10 milliseconds.
No
Can you describe again how this thing works again, the activates when it goes up?
Okay, so
I didn't quite catch that.
so once the burnout is detected,
Okay.
there is a 5 seconds time period where the canards actuate.
The what?
The canards actuate.
The canards actuate.
The canards actuate? Okay.
Yeah, and after 5 seconds, the air brakes actuate. We are not actuating both together because we don't want too much interference, or the interference is hard to calculate or predict.
It's very difficult to model.
Yeah.
So we want to individually assess them.
So you activate the canards to straighten it back up? Or
No, to stop it from spinning a lot.
To stop it from spinning?
Mm,
Okay.
yeah.
How do you know, how do you regulate how much angle?
Uh,
I'm confused on that, I'm sorry, I apologize.
No, it's all right.
Didn't quite
can-
follow it.
yeah. So basically, from the sensors we get the current roll rate, the current rate at which it's spinning, and we have like a reference rate we wanted to. We have a reference rate at which we wanted to spin.
Where are the sensors located? Are they,
Sorry,
like,
sorry, I didn't catch.
where are your sensors located?
So there is a PCB inside the rocket where the sensor is located.
We can.
Yeah.
Yeah.
So as you can see, the IMU is located at the center of the PCB. That's what detects the roll of the system.
Thank you.
Yeah.
Could you explain one more time how you're calculating like your expected apogee and like how that's triggering your air brake system?
So our 6-stop model, using the 6-stop model, we calculated the expected apogee with the current velocity and altitude. We got the drag values from CFD, and using an iterative process, we calculated the expected apogee.
Explaining what you said, so is it performing like the integral, like is it integrating forward, like during flight, in real time, to calculate the apogee? Or is it
No,
No,
not
it's-
real time. We have generated the data already.
We will use a lookup table in the code.
Okay, and the second question was, you're not deploying the Airbrake for the first 5 seconds.
Yes.
How much control authority do you have with like the last few seconds?
We have around 700 feet, if I remember. 700 feet. Yes, yeah.
So how precisely does the lookup table work for the height? Do you have like a velocity and then
So
you
it's
put you in like velocity and height and it tells you what your expected height is?
So the system, it gets velocity height and an air brake actuation angle, and then gives the expected final apogee. It takes the air brake's actuation angle also. So it's kind of like if the rocket were to move with the given air brake actuation and the given or velocity at that altitude, at what height will it reach? If it is at 10K, we will stop the we'll stop controlling it.
So you would have to be going the same angle.
Yeah, we'll maintain the same angle.
Yeah, we'll maintain this.
Is there a telemetry system, or do you need to recover the vehicle to have the full data?
We'll recover the.
We'll be storing the data inside. So our system, rocket has telemetry, but the control system is separate. So we don't have telemetry for the control system. Yes.
Is the power system capable, what is the idle power when you are waiting on the pad? Is there concerns about being able to?
We are using we are using around 6000 mAh battery pack. The idle current when we checked was in milliamps. It's not of concern. Yeah, any other questions? Yeah.
Is there any like testing process, like when you, as soon as you arm the two systems on the pad?
Yeah.
Describe what that's like.
After arming, so we only have actuation testings after the rocket is on the pad. Yeah, that we just actuate all canards and air brakes and check if they are able to actuate properly. Yes. Okay then, thank you so much.
Hello, everyone. Hello, everyone. My name is Joseph Hauerstein. I'm on the Terrapin Rocket team at the University of Maryland, and I'll be talking about our project to model and design a custom radio for live video and telemetry. So an outline for the presentation, I'll talk about first the motivation for this project, and then the link analysis that we use to determine our hardware and software requirements. Then I'll talk about the hardware design and software design. Then I'll go through some of the preliminary results that we have and some conclusions. So the motivation for this project was primarily the live video challenge. In the past, we've tried to use some FPV drone cameras, and we haven't had much luck with them. They've been very noisy, and we haven't had a good signal, especially later in the flight. So we decided to instead develop a digital modulation radio to transmit video for this competition. So diving right into the link analysis, this is what we use to basically set our hardware and software requirements. We use this to determine two key things. One, whether we can detect a signal throughout the flight, and two, whether we can decode that signal with minimal error rate, ideally 0. So to do that, first we generated a MATLAB script that we input hardware specifications and a nominal set of flight data into. We feed that into our model of how the signal propagates, and we use that to determine our sensitivity margin, basically a margin on whether or not we can detect the signal, how much power do we have over the minimum signal level where we can detect the signal. And then once we have that received power at the ground, we can determine how many errors the radio will have when it tries to decode that signal. That's our BER, or bit error rate. Once we have that, we can use a error correction algorithm to run a simulation to try to estimate, all right, when we receive that signal, how many errors we'll have and can we correct them? And that produces the overall error rate, which again is ideally 0. So the model that we used for this is basically this equation we want to determine based on our hardware, based on our things like transmit power or antennas. We want to determine what the power is of the signal at the receiver. So to do that, basically we input the transmit power, key attributes of the antennas, so the efficiency of the antenna, basically how much power is radiated versus how much do we give it. And then also the gains, so some antennas can receive better in specific directions, so we want to take that into account as well. And finally, our losses, so path loss, how much loss do we have from the signal propagating over a certain distance, and polarization loss, because when you have signals with certain polarizations, the angle between them can cause certain losses when you're trying to receive that signal. So using that equation, we generated our received power, which allows us to determine our sensitivity margin at different bit rates. So first, that dotted black line that you can see, that's the altitude of the rocket over the flight. That's just to give you an idea of where the rocket would be during the flight for the other 3 colored lines, which are our margins at different bit rates. So you can see as we increase the bit rate, the margin decreases. So we want to find a balance between high bit rate and high margin. So once we have the power at the receiver, we can calculate the next critical parameter, which is signal to noise ratio, but of course, first we have to figure out the noise at the receiver. To do that, basically, we sum up the noise added by each of the individual components, and also the noise due to the system having a temperature. Particles are wiggling around, that gives a bit of extra noise. So once we calculate that total noise, we can calculate the signal to noise ratio. Next slide. And that gives us our BER, but to calculate BER, we need to do that in a certain channel. So the 2 channels that we considered is one, a white noise channel. So basically we just add white noise to the signal, and we can, that makes the radio have a certain amount of error, and that gives us our bit error rate. And the other channel we considered was a Rickian fading channel. So basically that takes into account the possibility of reflected signals from nearby objects and how those could destructively interfere with the signal you're trying to receive. So the white noise channel generated basically 0 bit error rate using the functions available in MATLAB. but the Riccian fading channel generated about 10 to the minus 3, 10 to the minus 4 bit error rate based on the power we were seeing. And that was roughly the same for the two modulation schemes we tested, 2FSK and 4FSK. And you might think, oh, 10 to the minus 3, 10 to the minus 4, that's not a very big bit error rate, but when you're transmitting 500,000 bits per second, that adds up quite quickly. So now that we have the bit error rate, we can try to do some simulation to see how many errors we're actually going to get on the ground. So we basically just generate some random data. We generate error correction codes for that data. We use the bit error rate to apply random errors to the data, and then see how many errors we can correct. And that generates a bunch of metrics we can use to see how effective our error correction was. So this is one of those. Basically, this is the number of errored bytes in a single packet. And what that allows us to do is figure out how many error correction bytes we need in that packet. So the maximum number here was 4 bytes in a single packet that were errored, which means we need double that, or 8 parity bytes in the packet. And then we added, we bumped it up to 10 just to have a bit of extra margin. For the hardware requirements, we went with the 70 centimeter band because that's a band that we're familiar with. We have a lot of hardware for that band. And it also decreases our path loss because it's a lower frequency. We use FSK modulation once again because we're familiar with it and because we can achieve fairly high data rates, like 500 kilobits per second using that modulation. And we needed minus 90 decibels sensitivity and 33 decibels transmit power to achieve the bit error rates that we need. And finally, we're going to use an omnidirectional dipole and a high gain circularly polarized Yagi antenna. And I'll talk about more of the specifics of this on a later slide. So the architecture of our radio receiver board is fairly straightforward. Basically, we have a radio IC. We give that data and it produces a radio wave. We give it a radio wave and it lets us receive data. So on the RX path, pretty simple. We just need to properly connect the radio IC to the antenna with minimal loss, and we do that with a matching circuit. And we also need to suppress any high frequency harmonics that are generated using a low pass filter. On the transmit path, it's a little more complicated. We needed a PA to achieve our desired, or a power amplifier to achieve our desired output power. And we also need matching blocks to connect all those components together with minimal losses and additional low-pass filtering to suppress the higher frequency noise. Oh, and go back one slide. And we used a RF switch so that we can use the same module for both transmit and receive just by switching between those two paths. So in order to determine that our circuit topology and our component values were correct, we used the LT-SPICE simulation tool. So basically, we applied a AC signal, and we used LT-SPICE to verify that the circuit was constructed properly. And the way we do that is we look at S11. It's a little bit difficult to see, but this line here is the one that dips way down is the S11 curve. And so what we want to do is make that dip very low at our target frequency, because that means that a minimum amount of power is reflected. So you can see at the very edges of the 70 centimeter band, we achieved minus 10 decibels and minus 10 decibels roughly, which is rather good, but mostly we're looking at the center of the band where it dips down very low, and that's what we're targeting. For the TX path, we weren't able to do quite as well because of how many components there are in this path. It adds a bit more loss than we might like, but since we're in the middle, since we're trying to operate mostly in the middle of the band, and you can see that we're below that 10 decibel marker, for the most part in the middle of the band, that we figured this was about the best we could do. For the board design itself, there's a couple of key features. First of all is this section on the left, on the red, that's the top of the board. That is the RF section. So we wanted to isolate all of these components from everything else to minimize noise. And then so you can see the blue is the back of the board, so that has our microcontroller, our biasing for the PA, and our voltage protection. And the only other thing on the front of the board is some LEDs, but those shouldn't have a big effect. And also, this is a 4-layer board, so not pictured, there's ground planes in the middle between these 2 layers. For the antennas, like I said, we're using a dipole and a circularly polarized Yagi antenna. So we want the dipole to be omnidirectional because it's going to be on the rocket, and we don't control the orientation of the rocket. So we want it to be able to give us the same amount of power no matter what orientation the rocket's facing. But for the Yagi antenna, we can point that at the rocket. We control its orientation. So we want to use a Yagi because that gives us higher gain, and we can take advantage of that by pointing it at the rocket. We chose this specific combination of circular polarization and linear polarization because it yields a very consistent power received independent of the orientation of the 2 antennas. So if we were to go linear and linear or circular and circular, there would be the possibility for high losses. So that's why we went with this particular configuration. So now moving into the software architecture, we developed the SI4463, what we're calling the SI4463 library for using this radio, and we also adapted a library called RS Code to handle the Reed-Solomon error correction for us. And it's pretty straightforward. Basically, the microcontroller takes in some amount of raw data, and it does Reed-Solomon encoding, and then uses the SI4463 library that we developed to communicate with the radio to pass that data onto the radio so it can be transmitted. And the same works in reverse for receive. And we do that using what's called the Easy Radio Pro API, which is just Silicon Labs, the manufacturer's name for the API used to communicate with the radio. So one of the most important features of the SI4463 library is how we load data into the radio's buffer to be transmitted. And that buffer is called the FIFO. So the process is first we try to read data, and we load that into a buffer on the microcontroller, and then we wait until we receive an entire data block, meaning an entire section of the data that's going to be have error correction applied to it. So once we have that block, then we generate those error correction codes and just repeat that until we generate enough blocks. And then once we reach the threshold for transmitting, we have enough blocks to transmit that data, we then start adding that data to the radio's buffer. So if the radio has space in its buffer, we keep adding data. If it doesn't, then we stop. If the message isn't completed at that point, we know that message is done and we can start a new one. Otherwise, in both cases, we go back and start reading data. And the key part is that both of these processes can happen simultaneously, both reading in data and generating the error correction codes as well as transmitting data. And that allows us to achieve, in reality, achieve those high bit rates that we're targeting. So the next key component of the software is the packet structure itself. So each packet has to contain some amount of bytes that aren't actually data, which decreases our overall usable bit rate. And those are the preamble, sync words, and length bytes, which overall comes out to about 10 bytes total. And then also each payload block contains 10 bytes of error correction. So if you do the math, overall we can transmit 32 data blocks in a single message. So that means we can take advantage of up to 96% or 480 kilobits of our target bit rate. So our results so far, we've been able to test a prototype of our radios over 1/3 of a mile, also varying our antenna configuration. So we were able to use this to test our right-hand circularly polarized Yagi, our radio prototype, and also to compare our SRAD dipole to a COTS dipole that we were using before. So as you can see, the SRAD dipole, which we tuned to interact better with the environment of the eBay, performs significantly better than the COTS dipole. And also qualitatively, these numbers are what we would expect from experience in past years over this distance, since we can't quite model this particular situation yet because it's between 2 points on the ground. So in conclusion, we performed a link analysis to set the requirements for our hardware and software. Then we designed our hardware and software to meet those requirements. And we performed prototype ground testing, which gave us about the results that we expected. So some future work is that we want to do some improvements to our model. Basically, we want to be able to model the effect of the ground during transmissions, because when you're transmitting between 2 points on the ground, some of the signal gets absorbed by the ground. So we want to be able to figure out if we can still receive a signal over a certain distance over the ground, because the rocket starts out about half a mile away on the pad. So we want to make sure we can still receive a signal there. We also want to take into account pointing error, because we might not be pointing our Yagi directly at the rocket, because half the time we can't see it, it's going to 30,000 feet. But that adds an additional loss to our calculations that we're not accounting for right now. And finally, we want to try to look at some more robust Reed-Solomon error correction, because we're doing a very simple algorithm right now, and there's more robust layered algorithms with things like I think interpolation that can be used to improve our performance, and we can achieve higher bit rates and or more reliable signal. All right, questions? Yeah.
How is that video feed being converted to the data that the radio is sending? What is the like encoding or compression look like?
Yeah, so the video comes from a Raspberry Pi camera. It goes onto a Raspberry Pi. Raspberry Pi encodes it using the AV1 algorithm. And then it just it's basically like transferring a file over radio. It transfers that data via serial to the microcontroller, and that it goes through the whole process that I talked about then.
Have you thought at all about the frequency of keyframes in the video? Like if you were to lose a block due to like an uncorrectable number of errors more than you expect, like how long of a video block does that disrupt? Or
So we've looked into that a little bit. Mostly we've been focusing on the design of the radios themselves. But yeah, we do try to make sure in the encoder that the keyframes come fairly often in case we miss a block. Yeah.
Is there any like resources you could recommend for teams that aren't experienced using MATLAB and stuff to simulate radio frequency stuff and music radios that you mentioned?
Yeah, it's difficult because like I also came about this starting last year not knowing much about radios. Mainly I just tried to find people, get in contact with people who do work in the space and try to learn from them and just look stuff up on the internet. And I know there's toolboxes, and MATLAB provides also some resources, I think, to try to give you some information about how to use their tools as well. Yeah, so basically we just kind of use the online calculator to get an initial guess, and then we use the LT-SPICE simulations to verify that all the topologies and the values that we were using were correct.
Have you done any verification with like VNA or any equipment to see whether like the impedances of those networks are what you expect, or was the main empirical testing the like range test that you did?
So mostly we've done only range testing. We also want to look at doing testing with like a scope and a spectrum analyzer and stuff like that.
Are you ever concerned at all about any sort of lockup or kind of infinite loop issue? Or do you have any sort of like watch clocks or anything that can reset?
Not currently, but that is something we're looking at mitigating, because we have had situations where, for example, right now, the current version of the code was very recently developed, not the library itself, but the microcontroller code that handles reading in the data has had some issues where it could lock up if it stops receiving data. So we're working towards mitigating those issues, but yeah, that's something that we also did run into with the SI 4463 library in the past, where it could fail to receive what's called the clear to send signal. So you pass a command to the radio and it says, okay, I'm done. You can send another one. Sometimes when things weren't working, it would fail to receive that and it would just completely freeze. So we added a timeout to make sure that that couldn't happen.
Is there any telemetry uplink over this channel, or is it only a single direction over like these radio links?
So it can do both directions. The video is just one direction, but the telemetry, our current plan is to try to do 3 streams of telemetry, one from our avionics, one from our airbrake, and one from our payload, and then do a 4th stream is a rough word, 4th connection from the ground that contains commands so that we can, for example, tell the flight computer to turn on our video system.
When you're doing that kind of bidirectional over the same frequency, the same length, have you thought at all about how to handle which one can talk? Or that
Yes, yeah. So right now our system is basically time division multiplexing. So we have the avionics transmit the avionics and then airbrake data because airbrake doesn't have its own transmitter. And then the payload will make sure it doesn't conflict with the avionics by listening for avionics and then transmitting later. And the command system does the same thing.
Excellent. Any more questions? Otherwise, great job. Project's
Thank
really
you.
complicated. And, That's it.
All right.
Good job.
Thank you.
We're good to go? Yep. All right. Hello, everyone. My name is Hugo, and this is my partner, Matt. We're from the Royal Melbourne Institute of Technology from Melbourne, Australia. Today, we'll be presenting our design for an N-modular redundant flight computer architecture. To give a bit of context, our mission goal is to provide levels of redundancy in sounding rocketry applications that are not commonly found. Typical flight computer redundancy systems involve two dissimilar flight computers that deploy recovery events when needed. Our system is much more flexible, and it can provide any number of redundancy modes. This can be N-modular or otherwise. There are multiple different modes of redundancy, and we'll get into them throughout this presentation. We'll first get into what redundant systems are in sounding rocketry. Redundancy, its primary goal is to minimize points of failure. It is also responsible for improving the system reliability. There are multiple different types of redundancy. This can be hardware, software, and information. Typical examples of hardware could be duplicated ICs. In software could be anything from CRC checks or parity bits for transmission of data, and information falls under software as well. However, there are trade-offs in redundancy. This is something that we came across a lot throughout our research. Cost is a big one. If you are using redundant systems, you generally have an increased number of parts. This can obviously increase your cost. It also increases the system complexity, more parts, more complexity. And especially for electronics, a greater power consumption is also a big trade-off. Also for trade-offs in redundancy, you've got to sort of select which aspect you want to make redundant. Our research focused primarily on recovery deployment and recovery deployment alone as being the most redundant aspect of our system. You can implement redundancy for other aspects. Say, for example, you've got a very critical system that's measuring a particular type of data that you want. You can duplicate that. You can replicate it in different ways in software, in hardware, to make that particular system redundant. However, our system primarily makes recovery redundant.
Okay, so just to give a bit of background context of different types of redundancy that we came across in the literature, particularly in regards to aviation, I'll just start with cold standby. So this is a form of redundancy, in which case you have two or more systems that are operating together. Only one of these systems is actually operational at a time. So you have an active flight computer, for example, and then the others will remain inactive. They'll be powered off or in a low powered state. When there's a fault in the currently active flight computer or system, then the others will take over, or one of the others will take over, and it will be in charge of your output from the system. Now, this has the advantage of saving on resources because you have systems that are in a low consumption state, but the disadvantage is that they have no knowledge of the system's state at the point of failure. So it's quite difficult to synchronize these cold standby systems. So then we have hot standby. This is very similar, where you have, again, two or more systems acting together, except in this case, all systems are operational in their powered on state. They're essentially acting pretty much identically throughout this. The only difference in this case is that the flight computer will have an idea of the state at any given time. So when a failure happens in the active flight computer, the secondary will take over and it will be able to synchronize to that last known state. Then we come to N-modular redundancy. So in N-modular redundancy, you will have an input that is replicated to multiple flight computers or multiple systems. Each of those will then go towards the output of a voter, or an arbiter, as we will call it throughout this presentation. And that arbiter essentially counts the votes. And when it reads that there is a majority vote of the output determination, then it will pass through that output to, for example, the recovery charges when you reach apogee. So a couple of cases of N-modular redundancy. Pretty much N-modular, you can have N modules. So dual mode, triple mode, these are some common examples of different forms of N-modular redundancy. And even within these forms of N-modular redundancy, you can then extend that even further. So common triple mode redundancy is up here on the left, where you have your sensor inputs going to each of the flight computer units, and those go towards the arbiter. In this case, it's described as the selector, towards your actuation, which is the output in this example. So that's what I pretty much described on the previous slide.
Or you could even extend that into double-voted triple redundancy. So in this case, you have triple redundancy in 2 different stages. So you have the input voting, where you've got the sensors passing to that input voting stage. Those then go to the flight computers as your replicated input, and then those go to a second stage of the output voting towards your actuator set.
So I'd like to introduce you guys to Australis. Now this is our design of an N-modular redundant flight computer. Now we pride ourselves in reducing the size of all of our electronics, and obviously in sounding rocket applications, smaller is generally better. It's lighter, it can fit in a different range of rockets from L1 size all the way up to L3 and beyond. The flight computers themselves, we manufacture them in-house. It takes about 4.5 to 5 hours to load 2 at once, so we can pump these out pretty quickly. They're relatively cheap, and they have about 500-ish components on them, so we're very proud to present this flight computer to you all. I'm the primary hardware designer for this flight computer, so I'd love to run you through a bunch of the features that we have on this board. There are dual microcontrollers on each board. To those microcontrollers connected are sensor suites, and they are both dissimilar in hardware. So one microcontroller is connected to one sensor suite, the other microcontroller is connected to a dissimilar hardware sensor suite. They are LoRa enabled, so we can communicate with our ground systems, GPS enabled, so we know where we are in space. There's also flash memory, multiple different communication standards you can use within the board and external to the board. They are UART, I2C, SPI, CAN. We also have 4 pyrotechnic circuits which allow us to detonate the energetic charges. This is an excellent diagram that I produced to describe the actual layout of our board. It follows in hardware pretty much where everything is laid out. So if you look up in the top left-hand corner of the slightly larger design, you have the sensor suite. Now that involves 2 accelerometers, 1 gyroscope and 1 barometer. The accelerometers are tuned for either a high or low rate, so they can record high G events or low rate G events. Gyroscope obviously does what a gyroscope does, barometer measuring barometric pressure. That is connected to 1 microcontroller. Also connected to each of the microcontrollers is a watchdog circuit. This means that it can hold the microcontroller in reset if it is not functioning correctly. So it's just an additional level of redundancy to mask a faulty piece of hardware. On the left, that microcontroller also has its own flash memory. The one on the right is also connected to the GPS module and its own flash memory as well. The microcontroller on the right also has LoRa telemetry capabilities as well. If we go to the next slide, we also have our main communication method, which is CAN. That is on the left here. Each microcontroller is connected to a primary CAN bus. That allows us to connect multiple different flight computers together to facilitate our interboard communication standards. Now this CAN connection is redundant as well, so there are 2 CAN communication protocols, so if one of them drops out, we have another one to fall back on. They're sort of in the middle to the right, there's the other microcontrollers sensor suite, again the 2 accelerometers, 1 gyroscope and a barometer, and they are dissimilar in hardware to the first microcontroller that I talked about. Finally, we'll just go back one. The left and right microcontrollers are also both connected to their own respective detonation circuits, so they both have recovery deployment capabilities. There's also a whole bunch of other communication stands you can connect to, UART, USB-C, we've got power output, power supply, CAN. Yeah, it's all up there, it's great. We'll talk about the sensors. Dissimilar hardware is a big part of redundancy. If you have a fault in one particular piece of hardware, you don't want that replicated identically across another piece of hardware. So in each of our sensor suites, if one accelerometer, this is a 3-axis accelerometer, if one of them drops out for any particular manufacturing reason, the accelerometer in the alternate microcontroller won't have that similar fault. It very unlikely to have the identical fault. So that is just another aspect of redundancy that we've included in our design. Next we'll get on to communications. I've already spoken a little bit about this, but our primary communication method is through the CAN network, so that's controlled area network. We also have between the microcontrollers different communication standards. So we've got UART, I2C, and more CAN buses as well. So there is a lot of communication that can happen between these boards in multiple different protocols. We have storage. We have 512 megabits of flash storage per microcontroller. That stores accelerometer data, barometer data, gyroscope data, event logs, and event messages, all with timestamps. So this allows us to capture that data and use it for looking at what our rocket did, which is very cool. Our detonation circuit, we also have redundancy built into this one and a lot of safety standards as well. You're able to record continuity checks, so you can check whether there's actually a detonation charge connected to the board. That is on the right, there's a 5-volt supply. That's a low current supply, so you can switch to that supply, measure the continuity without any risk of deploying the E-match or the recovery energetics. Or you can switch to the 8.4 volt, which is our rail voltage, our battery voltage, and that will detonate the E-match at high current. And that is interlocked as well. So there is an AND gate that allows detonation only when 2 inputs are present. So it's a very deliberate initiation of the system. Another level of hardware redundancy that we've implemented into this design. And finally, we have our telemetry. We can communicate all of our sensor data, like I said before, accelerometers, gyroscope, barometers, GPS, there's more, to our custom ground station called Satira. Also there it says startup handshakes, flight state, raw and processed data, and auxiliary data. So there's a lot of different things we can communicate to with this board over the 915 megahertz band.
All right, so the firmware design and implementation has been my responsibility, so I'll give you a quick rundown on its architecture and that design before I get into how that actually enables the redundancy that we've been looking for. So it's a semi-layered architecture here. As you can see, it starts down the bottom with the Australis core. This defines the absolute minimum of what any application that implements Australis must have. So as you can see there, it provides generic interfaces to build upon in your higher level code. It provides internal communications. We use a free RTOS as the base for scheduling and task management. So the internal communications manage messages between different tasks. We also have the state management that keeps track of the internal state that is processed by our sensor data acquisition tasks, and that is including the altitude, the velocity, the stage of flight, phase of flight, as well as a few other key parameters. It also manages the device access, so for your flash storage, your LoRa, and so on. This manages how you access it and what you actually do with these devices. Now on top of that, we have the target layer. So this incorporates Australis Extra that has individual modules that provide specific implementations for certain very helpful aspects of the code, things like different communications, specific driver implementations, which is how you actually interface with the hardware, say your flash chip, your sensors. And it also incorporates a few other fun things as well. And then the target specific code is your actual implementation. This is stuff that is specific for your rocket. This is all the code that defines what your rocket does using the Australis system. So recovery is incorporated in that. GPS acquisition, for example, can be incorporated into that. Yep. So discussing the firmware core for a little bit. So as I mentioned, this is the bare minimum of what Australis is capable of. This is what every Australis system will be able to do. It defines the device API structs, which I mentioned is how you actually interact with the devices. That is the prescribed interface. It provides the peripheral drivers, so for your CAN bus, for your SPI, that is how you actually interface with the lower level device. Data structures, which are very important for your high level code, this is how you interact with the rest of the tasks, and also the core tasks, which you can see up there. So very simply, at its core, it's just a few simple tasks you've got at the most critical. The data acquisition, this is also processing data from each of our sensors. Our inertial data, our barometric data, that processes that into our state. The state management then takes that processed data, and that's what determines what phase of flight we're at and how we actually actuate things at the higher level. And then at the most bottom level of that, we've got the idle task flash write. Whenever there is time on the CPU available, it will be writing to the flash storage. So we keep it very minimal. That keeps everything out of the way for specific implementations. So it's not in the way of your code that you write up in the target layer. Yep. And there you go. There's a few more descriptions of the data structures we provide. So the device and task lists. There's also the publications interface. When I mentioned the internal communications between tasks before, this is a pub submodel, so it provides the communications across all of the tasks so you can pass data through very efficiently. Also manages the global state and an interactive shell, so that's very important for debugging and testing. You can actually interact with the system in real time when you've got it on the ground via a connection. You can do it over USB, you could do it via LoRa. So a bit on the extras. The extras, as I mentioned, are additional packages that you can include into your system. So these are all completely isolated modules, pretty much. So these include the device drivers, which you can see on the right there. This is just a couple of examples of how it's structured in the code itself. Each of those bottom directories for each of those sensors and the flash chip, those are individual modules, and you can just add them to your code and remove them as you please. They're not dependent on anything except for the Australis core, so they're kept very generic. There's also publication implementations. So as I mentioned, that is the messaging system. That is for specific publications. So if you've got, say, a LoRa publication, a CAN publication to pass those messages around your tasks, that's provided in extra as a module. And there's also other fun additions in case you want a PWM synthesizer to play Rocket Man on piezo buzzer. That's also available. So then the question is, how does this all integrate into an end modular system? So that's what we're here to talk about. So this is one of the designs for end modularity that we've been looking at. This is how we look to implement it in our own system and our design. So we start with the nominal operation of triple mode redundancy. If you remember back to the start of the presentation, I described you have the arbiter that collates the votes, and you have the 3 voted devices. Next slide. In case one of these devices dies, we then have the off-nominal operation. So in this case, one of the other devices picks up the slack. It becomes both an arbiter and a voter itself. The system becomes slightly less robust in this case as the arbiter is doing additional work. The chance of failure is a bit higher, but you still maintain that triple redundancy. In case of 2 of them failing, we can then revert to hot standby. So we can have 2 of those devices running in parallel, in which case you can still activate those deployment charges with a form of redundancy. And you can also continue to further implementations of redundancy.
So as we said before, there is also an example called cold standby. Our system can implement that as well. One system is operating nominally, and that is on. The other system is powered off, or in an off-nominal state. In the event that the on microcontroller dies, the other microcontroller can kick in and start deploying the recovery charges. Yeah, this is just one of the other additional modes that the flight computer can operate in. Next up, we'd have 4-way hot standby, pretty much the same as hot standby in general, except you now have 4 individual systems running in parallel. Again, you could implement this even further and go to 6-way hot standby. You name it, we can do it. And finally, we get into the real interesting part of end modularity. This is where you increase the number of modules of your system to numbers beyond just triple mode redundancy. So in this implementation, we have 5. This is where there is a 5-way vote. The majority is 3, obviously, so it can mask 2 faults. So if 2 units die, then the other 3 units can still determine whether we need to deploy the recovery system. Now, our research picked up a bunch of questions about what's the point of increasing the number of units in your system? Does it actually make the system more robust, more stable, more redundant? The answer is yes, however, there are quite a few trade-offs. Obviously, as you increase the number of units from, say, 5 to 7 to 9, you increase the number of faults that can be masked, so the number of units that can be masked, by only 1 each time. So for a much greater system cost, you don't get that much in increased redundancy. That being said, if you don't have power requirements, if they're less of an issue or the system complexity doesn't scare you that much, then you can just keep making it more and more redundant for just greater numbers of units.
All right, now I've looped back to the beginning a couple of times, and this is going to be the last time. I described double-voted triple mode redundancy back in that earlier slide for triple mode redundancy. When I mentioned that we look to implement and have implemented the triple mode redundancy for our system, we've actually implemented it in a way that is even greater enriched redundancy in that we have that two-stage in effect through a firmware stage. So as you can see here, these votors actually have 3 inputs into each of them. These are what are managed by our state management. We've got negative velocity, which is negative vertical velocity with reference to the Earth's frame that's calibrated at the launch stage. We've got increasing pressure, which means your altitude will be decreasing. Or we've got a greater than 90-degree tilt, again with reference to the Earth axis. So if 2 out of 3 of these conditions are true, you've got a majority vote, and one of these voters, when they reach those conditions, will then put its output towards the arbiter in a vote. And then the second stage, this is the standard triple mode redundancy stage. So this is where each of those voters, their output goes towards the arbiter, and in a majority count, they will then activate, in this case, the output is the deployment charges.
So as you can see, we've presented a number of different ways in which we can implement redundancy into our design. Now, this is not an exhaustive list. What might be right for your particular design in terms of redundancy may not be right for somebody else. So if you would like to implement hot standby, 4-way hot standby, triple mode redundancy, dual vote triple mode redundancy, and modular redundancy, dual vote and modular redundancy, you can. It is incredibly flexible. You can increase the number of, you can increase the redundancy in this system and implement it in many, many different ways. I've just been shown that I need to show this because I actually forgot. But here is our actual flight computer in its flesh and blood. It is smaller than a credit card. It's really cool, and I'd love for you guys to come and have a look at it afterwards. But we'd love to take any questions that you guys have. Yes.
You addressed power failure. One of the purposes of having redundant systems was independent power sources. Was that addressed in your design?
Not specifically on the board. You can implement that external to the board, so you can have dual power supplies with an OR ring, so you can have, if one power supply fails, there's another one connected already. The benefit of having 2 boards as well, you still have that redundancy. Even if one of the boards dies, there is the same redundant power supply connected to the other flight computer, so if one of them, if its actual power supply on board the flight computer fails, the other one is still functioning with that equally redundant power system.
The deployment charges, you mentioned it was an AND vote in a hardware
Yep.
controller deployment. So that's an AND vote from the 2 microcontrollers on that board?
It's only from one, so each microcontroller is connected to an AND gate, so there's the 2 GPIOs. It's just a slightly more deliberate way. It's not the best way to implement like a hardware redundancy for that deployment, but it is an additional level of hardware redundancy.
So if one microcontroller were to decide to turn on the pins that activated the charge,
Yep.
it's the only one driving that charge?
Yes.
Okay.
Yeah, at the back, I think you're first.
When you have the arbiter and 3 voters, if the arbiter fails, how does the voter know to take over as the arbiter?
So this is an implementation-specific detail. It's, as we mentioned, it's very flexible, so the details specifically are up to you. In our case, we use the CAN bus with heartbeat messages that are passed around between or from each of the microcontrollers, and that way each of the arbiters and the arbiter and each of the voters, they have a sort of status indication of the health of the system. So in case of failure, they can then determine amongst themselves through a vote which picks up the slack as an arbiter.
Is it possible to run a single board as like 2 independent flight computers with full redundancy in every aspect? Like, I'm not sure about the power, but like in every other way, is it possible?
Yeah, so we can have that, the hot and cold standby implementation. You won't have the full redundancy with the triple mode redundancy as we've been looking to implement it, or further implementations of redundancy, but you still have that hot standby or cold standby or other implementations of redundancy you can look to. Sorry? It's just the...
it's just the one, but
Yep.
with that diode or ring, in case
Yes.
that power system fails, it can still
Yep.
route into the board.
When you guys say that the specifics is up to the user, does that mean that at some point this board is going to be for sale, or?
It's not something that we've been looking towards, more towards internal for us with our team, future teams. We're building this with the idea of we have it sort of set up as we've got now, and then other teams can build off of that, use this in their rocket. With the flexibility, it's not specific to Legacy, which we're flying this week. It can be used on Legacy, it can be used on another rocket by the team, or other teams could pick it up if they would like as well, at least in terms of firmware.
Since you have many sensors working at the same time in a tiny board, how do you avoid, what designs do you make to avoid cross-talking between trials?
Between traces or? Yep. So we do have termination resistors on all the SPI lines, so it's SPI communication. Crosstalk is not a particular issue for these particular sensors. They are spaced quite broadly in their respective units. It's a 6-layer board, so there's plenty of ground planes all around. Yeah, so a 6-layer board, so there are two, there's one dedicated ground plane. There's also another ground plane which sort of acts as another signal trace. It was just the board density required traces on that particular layer. But the amount of ground planes surrounding each of the sensors is quite high. They're pretty robust. Yeah.
How many ground planes do you have?
One main one, and then all of the planes have a polygon ground pore. So on all 6 layers, there is a significant amount of ground polygon around. Yeah.
How much do they
The
cost?
cost in Australian dollars, about $350, I think, maybe 400 all up. A little bit less. It sort of varies depending on the parts availabilities, but around about.
Thank you, guys.
Yeah, no worries. Thank you very much.
Afternoon, everyone. We're from Melbourne, Australia, representing Monash High-Powered Rocketry. I'm Ratchet, and this is Sunny, and today we'll be taking you through how we approach streamlining our ground and rocket avionics. So for a bit of context, our entry into the Student Research and Design 10,000 feet category is Project Zenith, powered by a hybrid engine, Solaris Mark II. It uses a nitrous oxide oxidizer and a paraffin wax-filled ABS fuel grain. It generates 10,000 Newton seconds of impulse, and it has performance comparable to an M3400 motor. A few of the key goals we had in mind when designing Solaris was to have reliable ignition and repeatable performance. As we started developing electronics for the system, one of what we found was that we kept broadening the scope, and so far this system has progressed through the rest of the rocket. One of those tools that we developed was the intra-rocket interface system, or IRES. Using IRES, it has expanded our launch workflows, going from all the way from engine testing to full system integration. When we first started out with engine testing, we only had a few basic actuators and sensors. This was enough to get some static fires and get some data that we could work with. But as the need for more complexity, more control, and more feedback grew, we ended up here. So this system is mostly as it is today, but we're still missing a few key sensors and actuators, but that's okay. You get the idea. The problem that we kept running into as we were developing the system is that how do we make this system expandable and upgradable without making it more complicated as we do it each time? Previously, on other rockets that we've made, it was common for other team members to have their own laptop open, running their own ground station connected to their own RF system. And this was fine for simpler rockets that we've done before, but as with Project Zenith, it was just not sustainable. So our answer to this problem is the unified ground station. The unified ground station aims to coordinate and unify subsystems that have unique hardware and software. And another key goal we wanted to hit with this system is that, again, we wanted to be able to upgrade and add new subsystems without having to rehaul the whole stack. And while we're doing this, we also, because we are dealing with safety critical systems, we can't be interfering with any of their operations. So how do these subsystems communicate? So we turn to MQTT. And many of you who know IoT will have heard of MQTT. It's a lightweight, publish-subscribe messaging protocol that is built around a central source of truth called the broker. The broker basically holds all the latest values for any point of information. These points of information, they're called topics. So clients can publish to these topics and subscribe to these topics. So when you publish to a topic, you update its value, and when you subscribe to it, the broker will notify you when that topic has been updated. So let's say that our engine's pressure transducer is reading 40 bar. It will publish that to the pressure topic. The MQTT broker receives that information, updates the topic, and notifies any clients, such as the user interface, that the pressure has been updated to 40 bar. Then, as the operator sees that the pressure has been updated on their screen, they can decide to open the fill valve. And so the user interface will publish open to the topic position request. And then the valve controller can see that that publish has gone through, and it can open the valve, and as it does, it publishes open into the valve position. What this does is that it keeps the whole system up to date in real time. Some of the key clients in our MQTT network are the user interface, database, hybrid ground station equipment, and the Rocket Avionics itself. One of the greatest strengths of the system is that you can keep adding new clients without affecting the functionality of existing ones. And as you do this, you get more selective access to a growing pool of real-time information. So now let's have a look at how users will interact with the unified ground station. So this is our control station. It uses Inductive Automation's Ignition platform, which is an industrial grade platform, to to deliver a clear, reliable, and highly customizable human-machine interface, or HMI. It gives us the flexibility to make different pages for all our different systems while giving selective access to certain team members. So here you can see one of our main, or the main engine control page. It's aimed to be quick and easy to use, especially in high stress situations like during launch operations. It only shows key data like the position of actuators and the feedback from key sensors. It also shows buttons for filling, arming, and ignition. And it also using like graphics to quickly display important information. So behind the main interface, we've developed out multiple different screens, each showing different actuators and sensors so that we have full visibility and control over the whole system. We also have a set points page. So this caters towards like different physical configurations or different launch configurations that we want to try. And for safety, we implement like software-based arming, as I said before, and then also we have real-time fault alarms that pop up on the screen, slightly out of the way still, but they will alert the user as soon as something goes wrong. So now let's look at one of the main clients of our MQTT network, the pad station, the controller of our hybrid ground station equipment. So the pad station uses a LabJack T7, as many of you already do. And we use it because it's a very flexible device. We can change and upgrade its functionality as we please. We use a Raspberry Pi as the MQTT broker for the entire unified ground station. It also runs 2 MQTT clients. It runs the interface for the LabJack T7 and also for the onboard avionics. Finally, the pad station expands the reach of the unified ground station. It provides power and network connections to other devices located at the pad. For example, the video live stream receiver. So now let's move on to the rocket itself. This comes with a unique set of challenges given with integrating onboard systems. Up until this point, we've been looking at commercial off-the-shelf components that have IoT and networking built into them. But as we move to the onboard systems, there's a unique set of challenges that require bespoke solutions to solve them. So one of those challenges is that we have to fit systems in and around other systems or within the rocket, obviously. And talking about materials, the rocket is full of RF opaque materials like carbon fiber and aluminium, which make like RF communication unreliable. And finally, given that this is a competition environment, the RF spectrum is already very, very crowded. So adding more antennas and hoping that they work is just not a good idea. So in response to this, or using these constraints, we developed the motor controller system, which is the electronics for a hybrid engine. To make our hybrid engine safe and reliable, we have to measure a few key things: temperature, pressure, and the mass of oxidizer within the tank. We also need to be able to actuate the active vent at the top of the tank and actuate the main valve at the bottom. And because we need to be able to communicate with this system, it needs a reliable, wide link to our pad station. We ultimately ended up with 3 different printed circuit boards, or PCBs. So we've got Cerberus at the top, measuring pressure, and actuating the active vent. Hades at the bottom, measuring temperature and actuating the main oxidizer valve, and the capacitive fill PCB, which measures the mass of oxidizer within the tank. As you can see, all of these boards are physically isolated, and they distribute the responsibilities of the motor controller system. So how do they act as one cohesive network and communicate with the pad station? From this, we have 2 different requirements. We need a long-distance severable connection between the rocket and the pad station. And you need a short-distance multi-node connection between the PCBs on the rocket so that it's modular and expandable. So we decided on using RS-422, connecting the pad station to the rocket because of its like long distance requirements and its noise tolerance. CAN bus we use because of its multi-protocol nature, and that just simplifies wiring and it's ideal for our system. But some of you might have noticed that you can't just connect these two protocols together. You need a gateway. So this gateway takes the form of a microcontroller on Project Zenith. It basically just picks up packets from the RS422 line and puts it onto the CAN bus and vice versa. So this allows for a high throughput, low latency transfer of packets between the two communication protocols, meaning that we have effective communication. And then also, using a separate microcontroller to do this allows us to separate the tasks between the microcontrollers. So now, a whole system diagram looks kind of like this, with the gateway microcontroller unifying the offboard and onboard electronics into one cohesive system.
We will now look at how this cohesive system can be used together to create flexible design and allow us to solve some challenging integration problems. So firstly, let's introduce Airbrake, the active control system of Project Zenith. In order for Airbrake to work, it needs to calculate the target pressure altitude it wants to reach before launch. In order to do this, we have to give it ambient temperature data minutes before launch. How do we do this? We can't really use wireless communication, as Ratchet said, because Airbrake is surrounded by metal, because it's surrounded by metal, adding wireless communications will add unnecessary complexity. So what did we do? If you look at the cross-section of Project Zenith itself, you can see Airbrake is really close to the motor, where motor controller is housed. So just by adding one single CAN connection between Airbrake and motor controller, we can go from this system diagram into something more like this, just by adding two simple pairs of wires. Adding a few more lines of code, we can control any variable within Airbrake and any subsystem within Airbrake from the ground in real time in less than a few minutes. This means that this shows the highly expandability of the system and allows us to integrate more systems faster and allows the team to experiment with different systems, giving us a more innovative rocket. However, before we talk about the software, we need to talk about what we've defined already. Currently, we've said we've used RS422 and CAN bus. However, these RS422 and CAN standards only specify how devices are connected together physically and how data is transmitted through these physical mediums. However, these standards don't specify what do each sequence of bits mean and who should care about each sequence of bits. That is the job of the transport layer. And that transport layer we have named the Intra-Rocket Interface System, or IRIS for short, an ever-expanding network of avionics working in harmony. So as a bit of a background, there is a few transport layers for CAN currently. For example, CAN Open and Drone CAN. However, after a few research sessions, we found that these transport layers all have a few limitations. Firstly, there are minimal implementations used for our microprocessors, and they only support specific physical layers. Where, for example, for CAN Open and Drone CAN, they only support the CAN bus, whereas we would like the flexibility to use the RS422 physical layer. They are also restricted to peer-to-peer communications and are exclusive to embedded systems. So what did we do? We looked at all of those limitations and we created IRIS, which supports all processors used in our system and multiple hardware layers. Because of the way IRIS is designed, it's very hardware agnostic. By using dependency injection, anyone can create a new software module to allow support for new hardware layers. This is really important with things such as the gateway, where we can use the same software stack for IRIS to transfer packets between RS422 and CAN. We have also created multiple programming languages with IRIS. So IRIS is currently implemented in C and Python, and it also supports peer-to-peer and broadcast messages. When a sender wants to send an IRIS packet, there are two options, either messages or services. A message is sent from a sender and is transmitted across the whole network, allowing all devices to receive the same message, whereas services are more of a peer-to-peer request-response architecture, where a sender will send a request to another device. So that request could be something like actuate the pilot valve by 90 degrees, and then that device will do the request, and send a response back. So now we've talked about the type of packets that we can transmit through IRIS. Let's talk about how these packets are differentiated and the packet structure itself. So each packet is consisted of the header and the payload, where the header is the data about the data and the payload is the data itself. So diving a bit more into the header data, the IRIS specification defines a standard set of fields to allow for easier decoding. In those two tables, you can see the message fields and service fields. You may notice that the first 4 fields are identical between each of the two. These 4 identical fields will be used for determining whether the packet is a service or a message and some other identifiers. The rest of the fields are for more message or service-specific fields. So now we have moved the tables separated so that the shared fields are in its own table. Let's create an example where Airbrake is requesting orientation data from a flight computer. So in this case, because we're requesting data, we don't need the message-specific fields. And all we have to do is allocate all of the requested fields that we need to allocate. You may notice that event ID is noted down as IRIS allocated. This is because the user doesn't need to allocate an event ID. The IRIS engine will internally allocate an event ID to differentiate between packets with the same header. However, finishing the header is only half the story. We also need to have payload with our packets, which is the actual data that we're trying to transmit. And in this case, our data is 12 bytes long, containing information about the X, Y, and Z rotation. However, as we'll see soon, some physical standards only will have certain limitations that we have to work around, such as CAN 2.0b, which supports payloads only up to 8 bytes long. So how do we work around this? Well, we can split a packet up into multiple transmissions. And however, in order to reconstruct the packet correctly at the other end, we have to add a bit of metadata at the end of the payload to indicate where the transmission goes in the packet. So what does this look like? This will look like something like this. So this is the example of the orientation data split into two transfers, both of these transfers will also be sent off with the same header ID to allow for easier recombination of the packet. So now that we've talked about how an IRIS packet is created, how does the packet go through the software layers? Well, for messages, it's pretty simple. One of the major use cases we have for the messages is sending the current time message. So from our system, the pad station will send a current time message to all devices on our network to sync up all of the times on our devices. This message is transferred to each device, goes through the message filter, and into the message response function. So inside this message response function, it has access to all of the payload and the information about the message packet. So it can internally set variables which dictate what time it thinks it is. Services, on the other hand, require a bit more effort. So when a thread wants to request a service, it needs to create the packet first and pass it into the IRIS engine. When this is done, the thread is blocked to allow for other threads to work simultaneously, allowing for a smoother operation of the whole system as a general. Inside the IRIS engine, it will hash the thread using the packet's identifiers and header information along with the thread ID. Once this is done, it will go through the hardware layer into device number 2, where it will call a response function. For example, if this packet is an actuate motor request, it will actually actuate the motor and then send a response back, which goes through the hardware layer and back into the IRIS engine of the sending device. So this packet will then be used to hashed into the event tracker to retrieve the original thread ID. That thread ID will be then used to unblock the original thread with the packet response. So what this system really allows us to do is it allows us, for any device, we can add a few simple lines of code so that each and every device on our bus can access the data and services that other devices provide, allowing access to a whole load of integration. And that is where the beauty of our software lies. And then now,
Okay, so now that we've looked over the whole system, we can have a look at one of the most important features that this system enables, which is the automatic fill process. This process allows us to have reliable engine performance no matter what the environment is. So Project Zenith, as I said before, targets an altitude of 10,000 feet. So as with all nitrous-based hybrids, the mass and temperature of the oxidizer hugely affect the engine's performance and thus the height that we get to. So as you can see on that graph, that's based on one of our simulations. We are looking for pretty much, we're trying to get to 10,000 feet exactly. So we have that kind of narrow band of oxidizer mass and temperature that we need to get to as we launch. To do this, we have a few tools available to us. We can use the fill valve, which will fill nitrous into the onboard tank. We can use the active vent valve, which will vent nitrous into the atmosphere. And because that's an endothermic process, the tank itself will cool down. We can use the capacitive fill sensor to measure the mass of the nitrous within the tank, and we can use the thermocouple to measure its temperature. All of these devices are spread across different systems. So the fill valve is part of the ground station equipment. The thermocouple is connected to Hades at the bottom of the tank. The active vent is controlled by Cerberus at the top of the tank, with the capacitive fill PCB being beside it. So the key takeaway from our system is that the unified ground station can use IRIS and MQTT to communicate with all these different devices, coordinating them using a finite state machine. The finite state machine continuously takes input parameters from the several onboard sensors that we have, and it can decide to open different valves, sending commands to both the pad station and Cerberus in order to dynamically change the parameters of the tank. This system truly showcases the extent of our architecture. IRIS connects the onboard systems, the gateway connects them back into the pad station, and the unified ground station using MQTT controls everything. Solaris Mark II fills automatically, fast, reliable, and launch ready. Our full stack architecture achieves the project goals of Project Zenith. Through several test configurations, we have made sure that this system is reliable. It leverages scalable and modular design in order to build innovative rockets that are faster to build and easier to adapt. We built an innovative system in addressing the shortcomings of existing solutions, and above all, using well-defined responses, we ensure safety in the system. Using these hardware and software solutions, Monash HPR can build reliable, innovative, and safe systems resulting in competitive rockets such as Project Zenith. Thank you. Questions? Go ahead.
So you have IRIS for your rocket, sending messages and providing services. That sounds like a very similar use case to your ground station. So what's the advantage of using MQTT for your ground station instead of just using IRIS on both ends to kind of simplify everything?
Yeah, so, well, with the ground station, we kind of wanted to look at mostly commercial off-the-shelf products, and obviously commercial off-the-shelf products are not going to implement our custom protocol. And so being able to, it supports our goal of being able to iterate rapidly, being able to just buy a product that can do what we want, just be able to plug that in, start publishing, subscribing, works really well for us.
But there's nothing cost for the rocket anyway, so it doesn't matter.
Yeah, exactly. Yeah, spot on. Yep.
You talked about this unified system for all your electronics. And this is now looped into your Airbrakes, correct?
Correct, yep.
So is your ground station the sort of the hub that's feeding environmental data into the system, or how's that being handled?
Yeah, spot on. We have a field on our front end that we can just input temperature data that we get from our dynamics team, and using that temperature data, it just feeds it onto Airbrake so that it can dynamically calculate its new apogee.
Excellent.
Yeah.
Great work.
Sorry, can I ask a question?
Yeah, go ahead.
So can you discuss a little bit more about, can you discuss a little bit more about the safety features of your proposed software here? Like, because sorry, from my understanding, it sort of encapsulates a lot of the rocket's critical sort of safety features. So how do you like test that what testing have you done in your software, and how do you ensure that your software fails in a safe mode for your system to be reliable?
Yeah. So obviously with developing a hybrid pressurized SRAD system like this, there's several fail-safes that we need to consider. So on the pad station and ground station side of things, we have battery backed up servo valves that safe the GSC if power is lost or a communication signal to them is lost. We also, for the active vent on board the tank, it's a spring return valve so that like if power is lost to it, it'll automatically open. And then Sunny can talk about some of the things that the onboard motor controller system does to safe the system.
On the more software side, we've written unit tests for the whole of the IREC system to make sure that it works, as well as because of the inherent structure that the request response architecture provides, you're expecting a message to be returned back. You're expecting a response, to be returned back from other boards. So you know that when other boards fail, you can react accordingly. And that's how we get like a higher level of safety as compared to other systems. Yeah.
So what would be your like average communication time between the different systems? Like, do you have a metric for that?
Yeah, so if we're transmitting from pad station, from our ground control station, all the way to pad station and onto our rocket, through the gateway, it would be around 10 milliseconds.
You've advertised the modularity. How do you think about validating the shared components, like the single, like the CAN bus that touches all the components, or the MQTT server that interfaces with everything? How do you think about validating that those components can handle some future modularity? Like seems like difficult to define.
Yeah, well, CAN bus is used in the automotive world, so it's going to have to be reliable. And along with that, with our gateway system, we can also separate different modules into their own different networks. And so that separates responsibility a bit. What about for the MQTT side?
Yeah, so for the MQTT, we've also done a bit of stress testing, finding like the limits of like what the broker can actually do. So like there is a finite amount of how much data we can push in and out of the broker, but we found that it's within like the range of like kilohertz. So as long as we're not running that fast, which we don't expect to be, it should be fine. Yeah. Go ahead.
So would you consider changing your protocol if you wanted to go faster? Like, for example, if you use Ethernet as your physical layer, you might go a lot faster? Or?
Yeah, so on our ground station equipment, like it's MQTT is built upon the TCP IP stack. So we are using Ethernet, but it's kind of a limitation of currently the broker itself. So the broker software, we didn't need it to be super fast, so we just picked up the lightest weight, the lowest weight, lowest performance like broker that we could, because at the time we wanted to conserve power. But if we wanted to switch to a more high performance broker, then we could do that.
On the IREC side of things, we were definitely looking into Ethernet for intra-rocket communication. But at the current moment, we don't really have a need for it. CAN bus is good enough for us, and it's also really well tested. So, yeah.
I think I saw another question somewhere.
Oh, yeah.
Yeah.
Does your GUI display valves?
Sorry, can you repeat that?
Does your user interface display the state of your valves?
Yeah. So we have valve feedback because they're just COTS, industrial automation valves. They just give us like digital outputs, and we display that directly on the GUI. Yeah.
How do you ensure that, like in the case of like some sort of like mechanical error, but you still receive the signal from the valve? How do you ensure that there's synchronization between your actual valve state and your GUI?
Yeah. So as Sunny said before, like transmitting like from the ground station to the pad only takes about 10 milliseconds. So, and these valves, they're like, we basically trust them because we bought them as like industrial automation components. So we can't really do anything if they fail, like we'd have to work around it, but we haven't seen that happen so far.
For like developing the intra-rocket communication system, like what were the like primary design objectives? Like was it like power consumption or like to do everything SRAD or like?
Well, as the other side said, we kind of looked at the current implementations like UDS, which are built on top of CAN and used in the automotive network, but they didn't really suit our needs because we really wanted to have like that message broadcast structure. And another requirement was it had to work within all of our like microcontrollers, all of the family of microcontrollers, and it had to work with the hardware layers that we specified. So it just slowly, steadily grew up along there. Mm-hmm.
And then in the state that it's currently built, like, is it modular enough that it works with all of the specific microcontrollers that you currently use on board, or is it like able to be expanded to any sort of microcontroller that you could think to throw on there?
Yeah, so the iris structure itself is like, it's iris and then the hardware layers. So iris itself is fully hardware agnostic, and then the hardware layers can be adapted to whatever hardware you need. Sounds good.
How did you arrive at a call and response structure for the like remote procedure call and return as opposed to just broadcasting off of the data at a regular interval?
Because we needed to be safe and we needed to ensure that it failed loudly. So if another device didn't respond back, we would know that it doesn't respond back, which is really important, especially for a rocket. Yeah.
Sorry, I just wanted to follow up on the question I asked previously, but do you have any other methods of validating that your valve actually works apart from just doing visual feedback? Like some audio feedback from like microphones or valve actuations or something like that?
Yeah, so what we also have is we have like an IP camera that looks into our fill box, and that just gives us visual confirmation of literally where the ball valve is, and so we can be 100% confident. Yep. I think there was one there. Yep.
What's the advantage of the message response over sort of listening to the valve state and reacting loudly if the valve state fails to change?
Well, then if we were to only send messages, we wouldn't really know if there were like a bad thing that happened to the valves. In this message response structure, we can know immediately that something stopped responding, and we can like adjust to that quickly.
Well, I think I'm more saying where the valve is also talking to you. Like the valve is constantly screaming out what it's doing, so that you have that kind of feedback.
Yes.
Wait, so
Well,
like.
wouldn't that tell you whether or not the valve is doing what you want?
Yeah, but in that case, you're starting to flood like the network, and so like to keep the whole system responsive, like let's give an example. So our main valve, if it fails to actuate, so say we're at it's in the bottom position, and we say move to the bottom position, it's the board that's controlling it is going to go, hang on, I'm already at the bottom position, I can't do that, and so it'll send that back, and we know that at the ground station it tried to move down, but it just couldn't because it was already there.
Thanks a lot for your guys' time.